ಮೈಕ್ ಆನ್ ಉಂಟಾ?
ಹಾ,
ಸ್ಪೀಕರ್ ಕೇಳು.
ಅಲ್ಲ ಅಲ್ಲಿ ಆನ್ ಮಾಡ್ಬೇಕಂತ.
ಅದು ಮೊನ್ನೆ ಮೈಕ್ ಇದ್ದಲ್ಲ ಪ್ರಾಬ್ಲಮ್.
ಯೂಟ್ಯೂಬ್
ಯೂಟ್ಯೂಬ್ ಅಲ್ಲಿ
ಅದೇ ನೀವು ಹೇಳಿದ್ರಲ್ಲ.
ಮೊನ್ನೆ ಮೊನ್ನೆ ವರ್ಕ್ಶಾಪ್ ಅಲ್ಲಿ ಮತ್ತೆ 2 ದಿನ
ಹಾ,
ಒಮ್ಮೆ ಹಾಗೆ ಆಯ್ತು. ಅವಾಗ ಕೂಡ್ಲೆ ಗೊತ್ತಾಯ್ತು ನಮ್ಗೆ ಅದು
ಹಾ.
ಹಾಗಾಗಿ. ಮೊನ್ನೆ ಗೊತ್ತಾಗ್ಲಿಲ್ಲ.
ಸರ್ ಮತ್ತೆ ಹಲೋ ಹಲೋ, ಮೈಕ್ ಟೆಸ್ಟಿಂಗ್. ಹಲೋ. ಲೈಟ್ ಆಫ್ ಮಾಡಿದ್ದಾರೆ. ಇರ್ಲಿ
ಹೌದು.
ಇರ್ಲಿ ಅಲ್ಲ, ಇಷ್ಟ
ಇಷ್ಟೇ ಇರ್ಲಿ, ಅದು ಇಲ್ಲದ್ರೆ ಇಲ್ಲಿ ರಿಫ್ಲೆಕ್ಷನ್
ರಿಫ್ಲೆಕ್ಷನ್ ಆಗ್ತದೆ.
ಕಾಣುದಿಲ್ಲ. ಬೇಕಿದ್ರೆ ಆನ್ ಮಾಡ್ಕೊಡು.
ಈಗ
ತುಂಬಾ ಕತ್ಲ ಆಯ್ತಾ? ತುಂಬಾ ಆಗ್ಲಿಲ್ಲ, ಗೊತ್ತಿಲ್ಲ.
ಅಲ್ಲಿ ಈಗ ರಿಫ್ಲೆಕ್ಟ್ ಹೋಗ್ತದ ಅಂತ.
ಹಾ ಹೌದು.
ಇಲ್ಲ, ಈಗ ಅಲ್ಲಿ ಆನ್ ಇಟ್ರೆ ಅದು ಕರೆಕ್ಟ್ ಉಂಟಾ?
ಬೇಕಿದ್ರೆ ಆಫ್ ಮಾಡು. ಸೆಕೆಂಡ್ ಇದು ಅಲ್ಲಿ ರಿಫ್ಲೆಕ್ಷನ್
ಹಾಗಾದ್ರೆ ಇದು ಬೇಡ, ಇಷ್ಟು ಸಾಕ. ಕೆಲವರಲ್ಲಿ 4-5 ಲೈಟಿಗೆ ಕನೆಕ್ಷನ್ ಉಂಟು. ಇಲ್ಲ, ಮತ್ತೆ ಬೇಕಾದ್ರೆ ಪರೀಕ್ಷೆ ಬರಲ್ವಾ? ಎಲ್ಲಿ ಇವತ್ತು ಬಾಪ್ ಕೊಡ್ಲಿಕ್ಕೆ ಹಣ ಕೊಟ್ಟಿದೆಯಾ? ಓಕೆ, ತೊಂದರೆ ಅದ್ರಾಗ ಒಂದು ಕೊಟ್ಟು ಜೈನಿಗೆ ಅವರದ್ದು ಅವರಿಗೆ ವಾಪಸ್ ಇವ್ರನ್ನ ಕರ್ಕೊಂಡು ಬರ್ಲಿಕ್ಕೆ ಏನು ವ್ಯವಸ್ಥೆ ಇದೆ? ಜೈನ್ ಅವ್ರನ್ನ ಯಾವುದು ಕಾರ್ಯ ಎಂತ ಕಾರ್ಯ ಮಾಡ್ತಾನೆ? ಡೇವಿಡ್ ಕೈಗೆ ರೆಸ್ಪಾನ್ಸಿಬಿಲಿಟಿ ಹೋಯ್ತಾ? ಅವನು ಕನ್ಸಿಸ್ಟ್ ಆಗಿ ಏನ್ ಮಾಡಿದ್ರೆ ಅವನ ಮನ್ಸಿಗೆ ಬಂದಾಗ ಮಾಡ್ತಾ ಕೂತ್ಕೋದಾನ. ಅವನು ಮಾನಿಟರ್ ಮಾಡ್ಬೇಕು ಅವನು. ಓಕೆ ಓಕೆ ಸೂರಜ್ ಇಟ್ 8:45. ಓಕೆ, ಇವರಿಗೆಲ್ಲ ಬರ್ಲಿಕ್ಕೆ ಪಾರ್ಟಿಸಿಪೆಂಟ್. ಓಕೆ ಓಕೆ ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್ ಆಗಿದೆ. ಬಸ್ ಎಷ್ಟು ಗಂಟೆಗೆ ಬಸ್ ಮಾಡಿದ್ರಿ? ಮಾಮೂಲಿಯಾಗಿ 9:15 9:30 ಆಗ್ತದಾ? ಏನವ್ರಿಗೆ ಗೊತ್ತಾ ಡ್ರೈವರ್ ಬರ್ತಿದ್ದಾನಂತ? ಅಲ್ಲಿ ರಿಸೆಪ್ಷನ್ ಅಲ್ಲಿ ಹೇಳಲಿಕ್ಕೆ. ಮತ್ತೆ ತೊಳೆದವ್ರನ್ನ ಅಲ್ಲಿ ಫುಡ್ ಕೋರ್ಟಿಗೆ ಕರ್ಕೊಂಡು ಹೋಗಿದ್ರಲ್ಲ, ಮತ್ತೆ ಯಾರನ್ನಾರು ಕರ್ಕೊಂಡು ಬರ್ಲಿಕ್ಕೆ ಪ್ಲಾನ್ ಇದೆಯಾ ಡ್ರೈವರ್ಗೆ? ನೀವು ಅವರು ಇವರೆಲ್ಲ ಬಸ್ಸಲ್ಲಿ ಹೋಗಿದಾರಲ್ಲ ಅಟ್ಲೀಸ್ಟ್. ಹಾಗಾದ್ರೆ ನೆಕ್ಸ್ಟ್ ಡ್ರೈವರ್ ಬಂದ ತಕ್ಷಣ ಪ್ರಜ್ಞೆನ ಕರ್ಕೊಂಡು ಹೋಗಿ ಕೇಕ್ ಅಂತ ಹೋಗ್ಬರ್ತದ. ರಕ್ಷೆ ಇಲ್ಲಿ ಇನ್ನೂ ಬರಲ್ವಾ? ಬರಲ್ವಾ? ಕೇಕ್ ಲೈನ್ ಬಂದಿದ್ದಾರೆ. ಹಾ ಹಾ ಬಾಪಟನ ಹೇಗೆ ಪಿಕಪ್ ಮಾಡ್ತಿದ್ದಾರೆ? ಅವರ ಕಾರಲ್ಲಿ ಬರ್ತಿದಾರ ಏನು? ಸೆಕ್ಷನ್ ಶೇರ್ ಮಾಡ್ತಾ ಇರೋದು.
ಪೂಜಮ್ಮ.
ಗೊತ್ತಾ ಅವರಿಗೆ? ನಿನ್ನೆ ಸಾಯಂಕಾಲ ಬಂದವರು.
ಕಳಿಸಿದ ಪ್ರೋಗ್ರಾಮ್ ಜಸ್ಟ್.
ಮೇಲ್ ಹೋಗಿದೆ, ಹೌದು. ಮೇಲ್ ನೋಡಿದಾರೆ ಇಲ್ವೋ ಗೊತ್ತಿಲ್ಲ ಅಲ್ಲ.
ರಿಪ್ಲೈ ಕೂಡ
ಮಾಡಿದಾರಾ? ಬಾಪಟ್ ಕಾಳ್ಮಿ. Tell me, you tried to call me today, I think. Okay. Maybe Prajna is having it. Okay. Now you are ready, no? 9 o'clock is yeah, 9 o'clock is the session. In fact, ನಾನು ಟ್ರೈ ಮಾಡ್ತೇವೆ. ಎಲ್ಲ ಕಾಣಿಸ್ಲಿಲ್ಲ ಮಾಡಿದೆ. ಇವರಿಗೆ ಹಣ್ಣಿನ ಬುಟ್ಟಿ ಮತ್ತೆ ಇದು ಕೊಡಿ ಆಯ್ತಾ. ಶಾಲು ಆರ್ಮುಗಮ್ಗೆ ಮತ್ತೆ ಇವ್ರಿಗೆ ಕೊಡ್ಬೇಕು, ಜೇನಿಗೆ ಕೊಡ್ಬೇಕು. Yours is with me. Sure. It's not okay. Otherwise it becomes for God we will keep everything and do arti and we eat, not like that. No, you should put it up. ಇವರಿಗೆ ಏನು ಇದು ಮಾಡ್ತಿದ್ರೆ, ಶಾಲ್ ಜೊತೆಲಿ ಏನು ಕೊಡ್ತಿದ್ರಾ? ತಂದಿದ್ದೀರಾ? ಬಾಯ್. Yeah, I know.
If you need anything.
Okay. ಕಿರ್ಕಲಹಣ್ಣಿನ ಇದು ನಾನು ಓದಿ ಹೇಳ್ತೇನೆ, ಏನು ಮಾಡ್ತೇನೆ? ಅರೆ ಮಟೀರಿಯಲ್ ನಾನು ಇವ್ರದ್ದು ಓದಿ ಆದ್ಮೇಲೆ ಬಾಪಟ್ಗೆ ಏನಾದ್ರು ಮಾತನಾಡಿ ಅಂತ ಹೇಳ್ತಾನೆ, ಆಯ್ತಾ? Then later you will be asking Bojan, he is not Bojan, Boyan. Boyan. ಅಂತಿದ್ರು, ಅದು ಬಾಯ್ತಾರ. ಹೌದು, ಇಲ್ಲ ಇದು ಫಸ್ಟಿಗೆ ಇದು ಮಾಡಿ ಆಮೇಲೆ ಅಲ್ಲ ಅವ್ರಿಗೆ ಡೆಡಿಕೇಟ್ ಮಾಡಿ ಅಲ್ಲಿ ಬಿಟ್ಬಿಡುವ ಆಮೇಲೆ ಬಾಪಟ್ರಿಗೆ ಇದು ಮಾಡುವ
ನೀವು ಕರ್ಕ್ಲೈನ್ ಬಗ್ಗೆ ನೀವು
ಅದೇ ಫಸ್ಟಿಗೆ ಇದು ಮಾಡಿಬಿಡುವ ಮತ್ತೆ ಸಪ್ರೇಟ್ ಆಗಿ ಬೇಡ ಇವರಿಗೆ ನಾವು ಚೇರಲ್ಲಿ ಕೂರಿಸಿ ಆನರ್ ಮಾಡಿಬಿಡುವ ಇವ್ರ ಕೈಯಲ್ಲಿ ಚಾಲ ಬಿಡುವ ಮತ್ತೆ ಕೇಕ್ ಕಟ್ ಮಾಡ್ಲಿಕ್ಕೆ ಕೇಕ್ ತರ್ತಾ ಇದ್ದಾಳ ಪ್ರಜ್ಞಾ Yeah, please.
Good morning.
Good morning.
Oh, yesterday we didn't get time to introduce others, no? Yeah, please. That's great. Today's session starts with the Iclaa online now. Yeah. He didn't want to take risk and he did not proceed to. Yeah, I understand. Yeah. Steve, do you hear us? Hear you.
Yes, I can.
He's there. You can. Okay. So, how are you?
I'm well, thank you.
Probably our mic is good. Speak through the mic.
you can
No, it's okay, but it's
I'll just stay out.
the speakers are not. Oh, I see.
But the camera is on the other side or that? Which side are you? Huh?
you can talk to that.
From there? Okay. So, good morning. And should I say good evening for you?
It's actually good evening for me, yeah.
I don't know. Mike,
It's
Mike,
the night
yeah.
of the 19th.
Umashankar? Umashankar? Our speaker is not on.
Okay.
No, he's okay, but the speakers.
No, I cannot hear him.
I get about them and they're saying.
Oh, is it? Okay, no problem. There is nothing secret. Yeah, please. ಸ್ವಲ್ಪ ನನ್ಗೆ ಕೇಳಿಸೋಷ್ಟು ಗಟ್ಟಿಬೇಕು.
Can you hear me okay?
No, he has not made a arrangement. ನನ್ಗೆ ಕೇಳಿಸ್ತಾ ಇಲ್ಲ ಅವ್ರು ಮಾತನಾಡೋದು. Good morning. Bapat is here?
He was taking breakfast actually.
At least put on this speaker.
At the monitor.
No, it's ready.
Yes.
Can you speak? Let
Sure.
me. Now I can hear you. Okay. I should have said good evening to you, isn't it?
Yes.
Not, good morning. Okay. Thanks for coming online.
No problem. I'm sorry I wasn't able to make the trip.
It is our bad.
How are you doing?
Bapat will be coming very soon. At 9 o'clock, we will start this session. Um, today's day will be dedicated to you and Bapat. You know, today is Bapat's birthday.
Right, 69 years young.
Yeah, yes. I heard that you also turned 60.
Yes.
You're also 60 years young. In fact, our Avi, he used to say that he is 80 years young.
Very good.
Some people are young forever. So, how is the weather in your place? Fine?
Fine. So it's just a few degrees below 0 Celsius,
Oh,
and that is warm for us.
okay.
Yeah.
We had nice
Just
for last 2 days,
yeah.
and yesterday we had a conference dinner outside near my place.
Lovely.
Is it time? Getting ready? What?
4 minutes to go.
4 minutes.
Yeah, I'll be back in 2 minutes again. I'll just make sure that things are done again. Let the Bapat also join us. Yeah, but I want to see him here.
So this is off now?
And you'll be able to hear now? Okay. Then we are waiting. Start. Is-
Oh. That means actually I'll give you another one.
No problem. But not all dance can be trained for all schools, like only so much. Because when he's meeting the drum, the step should match the drums. Because enormous practice, they cannot synchronize easily. And that girl was very good. I think she's probably professional. Seconds, they say seconds would. No. ಬಂದ್ರೆ even without any language ಏನಿದೆ ಏನಿದೆ ನಮ್ದು ಓದಲಿಕ್ಕೆ ಪ್ರಿಂಟ್ ಕೂಡಲೇ ತೆಗೆದಿದ್ದಾರೆ ನಾನು ಸರ್ಚ್ ಮಾಡ್ಕೊಂಡು ಓದ್ಬೇಕು ಏನು ಅದು ನಾನು ಇದು ಅನ್ಕೊಂಡು ಎಲ್ರಿಗೂ ಅವ್ರಿಗೆ ತೋರ್ಸದ ಅಲ್ಲಿ ಬಾಪಡೆ ಬರ್ಲಿಲ್ಲ ಬಂದೆ ಅಂತ ಹೇಳಿದ್ರು Okay, let's start. In case it comes fine, I'll ask you to work. Yeah.
Good morning, ladies and gentlemen. So we are in the third day of International Conference on Linear Algebra and its applications. Welcome you all. We will begin with our first session in this plenary talk. We have Stephen J. Kirkland from University of Manitoba, Canada. Now, before we proceed, I request Professor Prasad to felicitate Dr. Kirkland on behalf of Kerams.
Thank you. Want to say something?
Professor Bapat.
Please.
So if you come here,
Yeah, I'll ask you to speak a few words about Iclaa. He was in our association for a long time, so that. ಅಥವಾ ಇಲ್ಲಿ ಹತ್ರದಲ್ಲಿ ಕೂಡಿಸಿಬಿಡಿ ಅವರಿಗೆ ಬರ್ಲಿಕ್ಕೆ ಈಸಿ ಆಗ್ತದೆ. Okay. Today is a very interesting day, and we dedicate today's day for the topic wise for matrix methods in graphs and personalities. Again, today is the important day. Professor Bapat is completing 69 years and stepping into 70th year. So we'll also celebrate his birthday today. And we'll dedicate today's day for our strong pillars for the Kerams. Okay. Professor Steve Kirkland and Professor Bapat. Professor Stephen Kirkland, his sorry, it is Jake and Jake Kirkland. His research interests are, thank you, now you are bringing it. Okay. Theory and applications of non-negative matrices, combinatorial matrix theory, spectral graph theory. His achievements in short are the following. Professor Kirkland is a professor, Department of Mathematics and Associate Dean, Faculty of Graduate Studies, University of Manitoba. He has published more than 130 journal articles and is a author of 4 books. He is the editor-in-chief, Linear Algebra and Multilinear Algebra, senior editor, Linear Algebra and its applications, vice president of ILS conferences, and president of International Linear Algebra Society from 2008 to 2014, editorial board member of SIAM Review, and so on. And it is quite long, and I'm not covering everything here. In fact, as I mentioned on the very first day, Professor Kirkland and Professor Bapat supported me a lot, and they are the strong pillars making me to stand before you and in this academic career. So I thank them very much. In fact, we 4, I used to be there for namesake, but these 3 were there standing very strong behind me. And for ICLA series, these 2 along with the SIMO were in scientific advisory committee, and we traveled along, and now we are in this position. We are in the 5th edition of ICLA. And Professor Kirkland, today we dedicate the entire scientific sessions for you and Bapat. Please, I welcome you for this particular day's activity. Of course, you are there with us for last 2 days also, if I'm correct. Am I right? Yes, I know, I heard through Uma Shankar. And thanks a lot for joining us. Professor Boyan Mahar will be the chairperson for this particular session. I request Professor Bapat to speak a few words about him.
Yeah, good morning. So we are all waiting for the lecture, so I won't take much time. Yeah. So I was going to mention that I'm seeing here a gap of 10 years. I mean, already 10 years senior to me are sitting. My teacher is there, Professor Jain is there, Iwsmga is there. These are 80s. And then we are kind of approaching 70s. and Prasad and Kirkland are the youngest members. So Kirkland just completed 60 years, so, and Prasad also. So they are our young generation in the 60s. And my association with Kirkland goes back a long time, and he has helped me a lot in the sense, not myself. We also work together, and along with Mickey Neumann, whom I remember very fondly, that we worked together and wrote some papers. But he also helped me in getting my students as postdoc. And as you know, Sukantapati was very successful. Barik was successful. I just had to mention just one line that I have this student, I think he is good. And at that time, he had a lot of flexibility. Later on, it reduced. I think Rajesh Kannan also, Rajesh Kannan. So these are already three names I'm mentioning. So along with Burman, Professor Kirkland also, I just had to write them a few lines and it was easy and that helped their career a lot. So I think I thank him for that also. And I don't know how he manages so many things because I was head at ISI once, I couldn't handle it really. But he is head of in his department as well as president of IRS, as well as journal editor. So it really takes a lot of energy. So I again congratulate him and I hope his association with ICLA continue. And thank you very much. I'll let him speak now.
Yeah, please.
Professor Kirkland, if you can share a few words with us.
Sure, I'd be happy to. So I've enjoyed the ICLAA meetings immensely. I'm very sorry I'm not there this time, but it's been a pleasure to watch the series of meetings grow. And I credit Professor Bapat, Professor Prasad, and others for the great growth in attendance and quality and interest in these meetings particularly, and I think in linear algebra in India in general. So well done, everyone. Keep up the good work.
Thank you, Professor. I now request Professor Bowen Mohan from Simon Fraser University, Canada, to chair the next session. Over to you, sir.
Okay, thank you. Welcome again for this session. The first talk is by Steve Kirkland. I don't have to introduce him anymore. It was a lot of nice words were said about him. His talk is entitled Eigenvalues for Stochastic Matrices with Prescribed Stationary Distributions. So please, Stephen.
Thank you, Boyan. I think the screen sharing needs to be enabled, and I can show my screen.
It is enabled. Please try.
Yeah.
Okay, can everybody see?
Yeah.
Very good. Thank you. Okay, thanks very much. Send my greetings to everyone at the conference. Thanks so much for the invitation. As I said, I'm sorry I'm not there in person, but I am glad that I'm speaking on Ravi Bapat's birthday, and let me be, well, maybe not the first, but the first of many to wish him a very happy birthday today. It was mentioned early on that my research interests include non-negative matrices and applications, and that's really the major part of my talk today is going to center on that. And in particular, I'll give you a little bit of spoiler alert that in a lot of ways, the point of the talk today is not so much to answer to a question, but rather to pose a question and maybe give some preliminary results on it that I hope will give some insight, but hopefully to interest other people who might want to take a hand at working on this body of problems. Okay, so I'm going to start by talking about stochastic matrices and Markov chains. Stochastic matrix is just a square matrix in rows and columns, and it has two key properties. The first is that each of its entries is a non-negative real number. And the second property is really over here. I've written it this way. I've written T times the all ones vector. This bolded one denotes the all ones vector. T times the all ones vector is the all ones vector back again. And another way of saying that is that the entries in each row of the matrix T sum up to 1. Okay. So I've got a bunch of, in each row, I've got some non-negative numbers and they add up to 1. And so I can think of those as representing a discrete probability distribution in Rn. Okay. And so just looking at this equation again, I'm gonna restate the equation in a different way. I'll say the number 1 is an eigenvalue of the matrix T, and the all ones vector is a corresponding right eigenvector. Okay, so that's stochastic matrices. And then what's a Markov chain? Well, that's intimately connected with that. So a Markov chain is a sequence of non-negative vectors. I'll call them xk. So the k is the index running through the natural numbers. So that when I look at the k plus first iterate, xk plus 1, and I'm writing it as a row vector, then how do I find that? I find it simply by looking at the kth iterate, written as a row vector, post-multiplied by my stochastic matrix T. Okay, and I also ask that the sum of the entries in each of these iterates of the Markov chain is equal to 1. Okay, well, that's a pretty simple iterative scheme that we have going there, and it's very easy to see that another way of writing out what the k plus first iterate in the Markov chain is just to say, well, it's the first iterate written as a row vector post-multiplied by the kth power of the matrix T. Okay. Next important definition is the notion of what it means for a square entry-wise non-negative matrix to be primitive. So such a matrix is primitive if it has the property that some power has all positive entries, right? And there's an equivalent characterization in terms of directed graphs, if you like combinatorial matrix theory, which I also like. So a square matrix with non-negative entries is primitive if and only if the corresponding directed graph is strongly connected and the greatest common divisor of the directed cycles in that digraph is equal to 1. Okay, so here are a couple of quick examples. Here's a 3 by 3 square matrix. You can check by yourself just by staring at it that it's stochastic. And you can, if you just want to tune out my voice for the next 60 seconds or so, you should be able to convince yourself that this matrix here is primitive. Here's another example. It happens to be a cyclic permutation matrix, but it's also stochastic. It's not primitive. It's easy to see that any power of that 3 by 3 permutation matrix is going to have some zeros floating around in it. So it's not primitive. On the other hand, its directed graph is what we call strongly connected. And so this is what we call an irreducible stochastic matrix. Okay. So, so let me set it up for you a little bit. So first of all, notice that if we want to understand something about the Markov chain, we need to take large powers of our stochastic matrix. Okay, and taking large powers of the stochastic matrix means that we should be thinking about the eigenvalues of that matrix T, because they're going to be influential on the behavior of the powers of our stochastic matrix T. Okay, and there's a fantastic theorem of Perron and Frobenius from the early part of the last century that tells us a lot about these eigenvalues. So let's suppose we have an n by n primitive stochastic matrix T. And so let's label the eigenvalues. We know one of them already. We already saw that the number 1 is an eigenvalue, so I'll label that lambda 1. And then the other ones are just some other collection of complex numbers, lambda 2 through lambda n. Okay, so what do we learn from the Perron-Frobenius theory? Here's the first bit, the first conclusion, that the modulus of the complex number lambda j is strictly less than 1 as j runs from 2 through n. So we have one eigenvalue equal to 1 and a bunch of other eigenvalues, the remainder of them, with modulus strictly less than 1. Second conclusion is that there's a unique left eigenvector W of the matrix T that corresponds to the eigenvalue 1, whose entries sum to 1. And the last bit of the conclusion is that this vector W has all positive entries. Right? And this vector, this W, is known as the stationary distribution vector for the primitive stochastic matrix T. Okay, so I'll just pause and make a quick comment there. To me, this is an amazing theorem for the following reason. So what did I put in as input to the theorem? I said my stochastic matrix was primitive, and it's not very hard to see that primitivity is in fact a combinatorial property, right? Only depends on the structure of the directed graph associated with T, doesn't depend on the particular sizes of the positive entries, just on their placement within the matrix. What do I get out of the theorem? Okay, what I get out as a conclusion is analytic information about the moduli of almost all of the eigenvalues of the matrix T, and a little bit of algebraic information about a particular left eigenvector associated with the eigenvalue 1. So that's amazing. I put in qualitative information and I get quantitative output. Remarkable. Okay, so now we can just do the thought experiment in our heads. I've got a single eigenvalue equal to 1, and all the remaining eigenvalues have complex modulus strictly less than 1. And now I want to take large powers of this matrix T, and you can see what's going to happen. All of the powers of lambda 2 through lambda n, they're going to damp out as k gets large. And what we learn is that the powers of the matrix T converge to the outer product of the all ones vector with the stationary distribution as k goes to infinity. In particular, our Markov chain xk, that's going to converge to the stationary distribution vector W as k goes to infinity, independently of what the initial distribution was. Amazing. Okay. So that's the setup for primitive stochastic matrices. If we have an irreducible stochastic matrix, so the directed graph is strongly connected but not necessarily primitive, then there is a collection of rather weaker conclusions about the eigenvalues, eigenvectors of the matrix T, and about the asymptotic behavior of the powers in T. All right. So thinking about this convergence to the stationary distribution that we saw in the primitive case, what kind of thing governs the rate of convergence to the stationary distribution? Well, it's pretty easy to see that it's the eigenvalues of the stochastic matrix that are going to carry the important information about the convergence property of the corresponding. Okay, and so there's a classic result of Karpelevich from the early 1950s that describes the region in the complex plane that consists of all eigenvalues of all stochastic matrices of order n. Now, the description is quite technical, and so I won't give you the full detail, but I'll just give you an example that will hopefully carry the flavor of what this region looks like. So here's the region for n equals 12, and let me try and explain what you're looking at here. So you can see there's a dotted red line around the outside. Okay, that's the unit circle, right? And then there's these blue lines here. This one's straight, and then there's a bunch of curvy lines that gradually touch one point of the unit circle, and then arc over to another point on the unit circle. All right, and that's the boundary of the Karpelevich region. Okay, and so roughly speaking, the description of the region is it's something like all of the roots of unity of orders 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, those are going to be in the region and scattered around the unit circle. And then these little curves that are described in terms of certain polynomials, these little curves that connect one root of unity to the next one consecutively. All right, so that's the Karpelevich region. And so the other thing I want to bring into the mix here is the notion of the stationary distribution. Now, I described it as an eigenvector, a left eigenvector associated with a number 1, but it can also be understood in terms of the sum of weights of certain spanning directed trees in the directed graph associated with our matrix T. And this is sometimes called the Markov chain matrix tree theorem. If you're familiar with the classic Kirchhoff's matrix tree theorem for the Laplacian matrix of a graph, it's a similar sort of result, but applied to this setting of Markov chains. Okay, and so this is really the question I want to introduce in my talk today. I want to talk about how the stationary distribution of an irreducible stochastic matrix might constrain its eigenvalues. Okay, and so I'll just say it's not completely obvious that any constraints on the eigenvalues would be imposed by an eigenvector. You'd have no reason to believe that that is true. So let me just run through a quick example. So let's look at a vector in R3. We'll take it to be written in increasing order with all positive entries, and we might as well take the vectors to sum up to 1. Okay, and so what does a typical stochastic matrix having that vector as the stationary distribution look like? Well, it looks like this, okay? So it's a whatever that is, a four parameter matrix with parameters A, B, C, and D, and then we have a few constraints that will be imposed by the fact that all the entries in the matrix are non-negative. Okay, so if I just look at the trace of that matrix, well, I can write it out. Here it is. It's not a pleasant expression, but it's easy to see that that the trace of the matrix is bounded below by W3, take away W1, take away W2, all on W3. And I can rewrite that, since the sum of the entries in W is equal to 1. I can rewrite that as 2W3 minus 1 on W3. Okay, so imagine that I had a non-real eigenvalue of my matrix T, then we can deduce from this last inequality that in fact the real part of that eigenvalue would have to be at least as big as W3 minus 1 on 2W3. So as a simple example, if W3 happened to be bigger than a half, then any non-real eigenvalue of one of these 3x3 stochastic matrices that had W as a left Perron vector, any eigenvalue that was complex would have to have real parts strictly greater than minus 1/2. Okay, so already we see in this small 3x3 example that the stationary distribution vector itself is placing some constraints on which eigenvalues can be realized by a stochastic matrix with that stationary distribution vector. Okay, really, that question is the kind of thing I want to explore in the remainder of the talk. Okay, so to do that, what I'm gonna do is I'll take my favorite positive vector W, whose entries sum to 1, take it to be an Rn. All right, I'm going to build two sets. Okay, S sub W, well, I won't tell you, I mean, you don't have to read the whole thing. S of W is just all the stochastic matrices that have that W as a left eigenvector corresponding to the eigenvalue 1. Okay, and sigma S, well, this is going to be the set of all eigenvalues of all stochastic matrices that fall into this set S sub W. All right, so my sigma sub S of W is somehow like the Karpelevich region, but with the extra restriction that I insist that all of the stochastic matrices that we're thinking about have the property that W transpose serves as a left eigenvector corresponding to the eigenvalue 1. Okay. And so in particular, my set SW includes all the irreducible and primitive stochastic matrices that I'm interested in. And in fact, the irreducible members of SW are easily seen to be a dense subset. Okay, so the point is we want to try and understand this sigma S of W because it will tell us how the stationary distribution influences and constrains the eigenvalues of the corresponding stochastic matrix. Okay. So here are a few easy observations. So just take a positive vector W in Rn whose entries sum to 1. Okay, it's easy to see that this sigma sub S is symmetric with respect to the real axis. And that's because stochastic matrices are real, and therefore their eigenvalues arrive in complex conjugate pairs. Okay, if lambda is an element in sigma sub S of W, then so is the convex combination of lambda and the number 1. Okay, and that's easy. It's just because if T is in our good set S of W, then so is the corresponding convex combination of the identity matrix and our matrix T. Okay, here's another one. If lambda is inside our good set of eigenvalues, sigma S of W, then so is T times lambda for any T between 0 and 1. All right, that's a different type of argument, a convex combination now with T and the outer product of the all ones vector with the stationary distribution vector. And then from here, in fact, we appeal to an old but very useful and beautiful result of Brouwer, which describes the eigenvalues of exactly this family of matrices when T is stochastic. Right? If W1 is the minimum entry of the WJs, then we can take an element of sigma sub S of W and do this sort of funny transformation on it and produce another element of sigma sub S of W. Again, it's the same sort of idea as we saw in item number 3. I'm taking a particular linear combination of the outer product of the all ones vector with the stationary distribution and our original matrix T, and then appealing to that same result of Brouwer. And last easy fact, if W hat is a subvector of W, then if I want to know about what the sigma sub S of the subvector looks like, well, it's already contained in sigma sub S of W. And that's because if I have a matrix T with W hat as a left eigenvector and W hat is of smaller order, I can just direct some T with appropriately sized identity matrix to generate another stochastic matrix having all of W with that eigenvector. Okay. So this result here is sort of trying to answer the question, which complex numbers are realizable as eigenvalues of a stochastic matrix with a given stationary distribution vector W for every choice of W. Okay, so it's the intersection of sigma SW as we look over all possible positive vectors W whose entries sum to 1. And that intersection turns out to be the closed interval between 0 and 1. Okay, so it's actually quite a small set. I'm saying everything except for the interval between 0 and 1 is somehow affected by the particular stationary distribution vector. Right? The fact that the intervals between 0 and 1 is contained in sigma S of W follows from observation 3, which I gave you on the previous slide. And the reverse containment is a little bit technical induction proof on the order of the matrix N. Okay. Here's another sort of babyish result. Which points in sigma S of W lie on the unit circle? And the result's a little bit technical, but I can try and trim it down for you. Imagine that I've got a number k between 2 and n, and that one of the corresponding kth roots of unity is in sigma S of W for some choice of W. Okay, and we might as well take J to be relatively prime to K. So that holds if and only if there's a collection of non-empty disjoint subsets, S1 through Sk, such that the values that I get when I sum the entries in W over indices falling inside of a particular Si, that those values are all equal for each choice of I from 1 to K. All right, that follows essentially from a well-known structure for irreducible non-negative matrices that have a sort of periodic structure, and you can draw certain conclusions about the corresponding stationary distribution vector in light of that. All right, here's a corollary to that. Imagine I've got my positive vector W whose entries sum to 1. And if we know that for any pair of non-empty disjoint subsets S1 and S2 of the index set from 1 to n, if we know that the sum of the corresponding W values for S1 is not equal to the sum of the corresponding values for S2, and that's for any choice of those two subsets, then for any stochastic matrix that has W as a stationary distribution, the only eigenvalue of unit modulus is actually the number 1. Okay, and so in particular, if we had such a matrix T, it happened to be irreducible, it would automatically have to be primitive. Okay, so again, maybe the interesting part here is we impose an hypothesis on the stationary distribution, and what we get out is a bunch of information, at least in the irreducible case, about the primitivity of the matrix, equivalently, a bunch of information about the directed graph associated with T. So this is sort of a converse thing. Quantitative information about W implies qualitative information about irreducible matrices T with that stationary distribution vector. Okay, so I want to get on to a sort of a special case here because it has a little bit of extra structure and that allows us to say a little bit more. So if I've got a symmetric non-negative matrix here, call it capital A, and let's suppose we write out the row sum vector of A as W, and I build a diagonal matrix capital W, but by just taking the entries of little w and stringing them out on the diagonal. So it's easy to see then that if I make the matrix W inverse times A, that's stochastic, and it's known as a reversible stochastic matrix because it corresponds to the transition matrix for a what's called time reversible Markov chain. And in fact, the implication goes the other way. If I have any transition matrix for a time reversible Markov chain, it can be built in this way. Take a symmetric non-negative matrix, divide out by the row sums. Okay, and these are an important and well-studied subfamily of stochastic matrices. And so I'm going to ask for the structure of another set. I'll call it R of W. What is that? Well, it's just the same. It's the reversible analog of the set I introduced before. So it's all of the reversible stochastic matrices having our given vector W as a stationary distribution vector. And sigma sub R is just the collection of eigenvalues of all of those reversible stochastic matrices. Okay, so turns out that if T is a reversible stochastic matrix, then this guy here is a symmetric matrix. Okay, well, that's good news. Symmetric matrices have beautiful eigenvalue properties. And so in particular, all of the eigenvalues of such a matrix are real. And so we learn right off the hop that sigma sub R is a subset of the closed interval between -1 and 1. I'll just say in passing that this W1/2 T times W to the -1/2 is intimately related to the normalized Laplacian matrix for a weighted graph. If you know that world of normalized Laplacian, this symmetric matrix that I just showed you is related to that. Okay, so let's see. So we know that the number 1 always lives inside of sigma sub R of W. So in fact, if we want to characterize or describe in some concrete way sigma sub R of W, really, we just have to pull out the minimum entry in sigma sub R of W to describe the region completely, at least in the reversible case. All right, so that one leads one naturally to the following body of ideas. So it's pretty easy to see the reversible stochastic matrices with given stationary distribution vector are a convex set. And of course, an extreme point of a convex set is one that can't be written as a non-trivial convex combination of other members of the set. And so we come up with the following straightforward result. If n is at least 2 and my stationary distribution vector W has been prescribed, then there is an extreme point of this good collection of stochastic matrices such that lambda underscore of W, that minimum value of the lambda, is an eigenvalue of T. And it's an easy argument. Just let lambda min denote the smallest eigenvalue of a reversible stochastic matrix with stationary distribution vector W. Easy to see if T1 and T2 are in our good set, then lambda min, the convex combination of T1 and T2, is bounded below by the convex combination of the corresponding lambda mins. Okay, so I'm just making that connection back with the symmetric matrices that are similar to our reversible matrix. Okay, so that means lambda min is a concave function, and so it takes its minimum at an extreme point. Simple observation. All right, and speaking of extreme points, word to the wise, if you ever start a problem in combinatorial matrix theory, which this is going to turn out to be, the first thing you should do is go back and read what Richard Braldy has written, because he's written almost everything, and that's the case here. So it turns out Braldy has a lovely characterization of extreme points of this convex set, or a convex set that's related, the non-negative matrices with that are symmetric with prescribed positive row sums. And from Braldy's result, we generate the following. Let's see, a matrix T in our good set of reversible stochastic matrices is an extreme point if and only if each connected component of the graph associated with T, which I'm calling G of T, is either a tree or it's a unit cyclic graph whose unique cycle has odd length, possibly a loop. Okay, so this lovely theorem of Braldy essentially tells us if we want to know about extreme points, we just need to know about the graphs and that the graph of the matrix has a particularly simple structure. Okay. And we're able to work with that a little bit to produce the following results. So if I have a good vector W, and if it has the property that for every pair of disjoint, non-empty disjoint subsets S1 and S2, we have this inequality between the corresponding summations of the entries in W corresponding to S1 and S2. And in fact, there's a T inside our good set of matrices, so that lambda min of T is equal to lambda bar, and G of T is a tree with a loop at some vertex. Okay, the idea is straightforward. You show that if T is a minimizer, then G of T is connected. And then you show, and so remember, the connected version means it's a unicyclic, extreme point has to be unicyclic with a cycle of odd length. And then you just do a little technical result to show that if you have an on cycle of length 2k plus 1, then there's another T tilde inside the same set whose lambda min value is smaller than the one that you started with, and that has a cycle of length 2k. Okay, so that gives us then general structure of what the extreme points and hence the minimizers of this lambda min look like in the set of interest. Okay. And so from that, for example, we can develop this not particularly pleasant bound. I don't even really want you to look at the formula. What I want you to observe is its general structure. This number gamma here that I'm defining is built out of the information in the stationary distribution vector. Okay, and I'm saying lambda bar of W is bounded below by minus 1 minus gamma to the n minus 1 raised to the 1 over n minus first power. Okay, the idea is straightforward. Imagine that lambda bar is an eigenvalue of a realizing matrix T, and that T is a tree with the graph is T is a tree with a loop. Then the smallest positive entry in T is at least gamma. You raise up the powers to produce a matrix that has all positive entries. And in fact, it's this all result of power that I mentioned earlier, outfalls the lower bound on lambda underscore of W. Okay, so I'll wrap it up quickly here. I realize I don't have very much time with a couple of remarks on the low order cases. So for n equals 2, in the reversible case, lambda bar of W can be written as minus W1 over W2, or we take this ordering, W1 less than W2. And that one's easy. There's essentially one extreme point to look at, one 2x2 matrix whose graph is a tree with a loop. It's this one, and then you just find the corresponding eigenvalue. The case for n equals 3 is a little bit more complicated. Again, I don't really want you to look at the formulas, but just notice that the formula for lambda underscore of W is built entirely out of information in W, right? The proof is really, going back to this earlier idea. We have 2 candidate matrices to think about, 2 of those extreme points to think about. We just look at the eigenvalues, and now we just determine under what circumstances lambda min of T1 is either less than or equal to or greater than lambda min of T2. Okay, so that's under the hypothesis that W3 is bigger than a half. Then I have another result to cover the case that W3 is strictly less than a half. Again, I don't really want you to look at the details too much. Simply observe I have x1 minus and x2 minus. They're both formulas, excuse me, they're built out of W, and that lambda underscore W is just the minimum of those 2 guys. Okay, and that's because there's 3 candidate matrices we have to look at, T1, T2, and T3. Each of them has a graph that is a tree with a loop at one vertex. T3 turns out not to be a contender because its lambda min value is always bigger than the lambda min for T2. And now you just pick the smaller of lambda min T1 and lambda min T2. Okay, and just to give you a little idea of what that looks like, it turns out for each W2 between 1/4 and 1/2, as long as W2 is not 1/3, there's a unique value W star in this interval that tells you when we take on x1 minus and when we take on x2 minus as our lambda underscore W, right? We take on the value for x2 minus if W2 is in this interval and W1 is in this interval, right? We flip to x1 minus for W2 in this interval and W1 between W1 star and W2, and x2 minus again if W2 is in 1/3 and 1/2, and W1 is in 1/2 minus W2 and 1 minus 2 W2. Okay. The proof is awful, computational, and not super enlightening, unfortunately. And in fact, this W1 star, if you fix the W2, the W1 star is the root of some not very nice quartic whose coefficients are polynomials in W2, and you just slug it out with the algebra. So just as an example to give you an idea of what's going on, if we pick the value 7/24 for our W2 and look at what lambda underscore of W looks like as W1 ranges between 1/2 minus W2 and W2, it's this kind of curve here. Okay, and in case you're wondering, this second part over the curve of the curve over here, it's not a straight line. There is a very, very slight curvature to it, and indeed, if you look at the formula, you'll see it couldn't possibly be a straight line. And so this peak here is this switchover point at W1 star. Okay. So just a few comments to wrap up. I'll just say that in some sense, the question that I pitched is a souped up version of what's known as the perfect Mirsky conjecture for doubly stochastic matrices. So that corresponds to taking W to be a multiple of the all ones vector. Perfect Mirsky conjecture has been open since 1965. It's known to be true for values of n equal 2, 3, and 4, and false for n equals 5, and completely wide open for n greater than or equal to 6. In my opinion, looking at the graph of our reversible stochastic matrix turned out to be a great help with dealing with the problem. There may be more technical results we could milk out of that idea, but it's clear that in the general case, there's a lot to be done in developing a better understanding of what this subset of eigenvalues looks like when we fix the stationary distribution. All right, and for those that want to see all of the details, many of which are awful, I warn you, there's a paper in the Electronic Journal of Linear Algebra that came out sometime in the last month or so. Thank you so much for your attention.
Are there any questions?
Good morning, sir. Am I audible?
Hi.
Hello, sir. So, is there any relationship between the eigenvalue of symmetric non-negative matrix A and its reversible stochastic matrix?
So if I think you'd have to work pretty hard to come up with the relationship between the eigenvalues of A and the eigenvalues of the stochastic matrix that goes with it. The reason is that the stochastic matrix, the reversible stochastic matrix, is diagonally. Let's see. Yeah. Is similar to a diagonal similarity transformation on A. I think that's right. Okay, so I start with A, but then I have to do some transforming of the entries before I understand the matrix T. So as I said, if you're looking at it from a spectral graph theory perspective, the matrix you really want to be looking at is the normalized Laplacian matrix.
Okay, thank you. Sir, so if we start with the very
stochastic matrix, like is those results are done, or is it so obvious? Or, like give any suggestion for the doubly stochastic matrices?
Sorry, can you say it again? I didn't quite hear.
If we start with a doubly stochastic matrices,
Mm-hmm.
so what will be the spectrums of those? Like I said initially,
Um, so let's see. Right, so we start with a doubly stochastic matrix. And now we look, yeah, okay. I think the result is disappointing in the reversible doubly stochastic case. Remember, because what does my graph look like? I have this extreme point, okay, so it's going to be, let's see, each connected component is going to be either a tree or a unicyclic graph with a loop. The double stochastic piece of it actually forces the tree to actually just be a single edge, right? So I got a direct sum of a 2x2 matrix 0, 1, 1, 0, whose eigenvalues are 1 and -1. And then I think again the unicyclic graph with a group with a loop in the doubly stochastic case just turns out to be a 1y1 matrix equal to 1.
okay, so we're getting some obvious type of things.
Yeah, and I mean, if you look carefully at the theorem that I showed about the graph of T, there was embedded in it a hypothesis on the stationary distribution vector W, where I was insisting that I couldn't take two subsets of indices and have them add up to each other when I look at the corresponding entries in W. The doubly stochastic matrices are the worst offenders because I just pick any two entries, and of course the entries in the stationary distribution vector aren't equal in that case.
Thank you.
I didn't get what is it? Lambda underscore W. What is it?
Sure, it's this. So I had the subset of the real line that consisted of the eigenvalues of the reversible stochastic matrices with stationary vector W. Okay. And the lambda underscore W is the left-hand endpoint of that interval. It's the smallest value. The idea being that I can describe the entire set by simply characterizing the smallest entry in that set, the smallest element.
No, suppose can you say anything about the smallest eigenvalue in modulus?
Ah, very good. In fact, that's probably a better question than the one that I posed, because the if you go back to the original motivation, we're trying to understand the behavior of powers of stochastic matrices, right? And so in some sense, I'm kind of agnostic about what the argument of my complex eigenvalue is. It's really the modulus. So yeah, that's a great question, and I think that's also well worth investigating.
No, for the irreducible case, when lambda is 1, the maximal eigenvalue is 1, so they form a group. Okay.
Right. Yeah.
And then even everything underneath also is some kind of is it a concentric circle kind of thing which is happening? I don't know, honestly.
If I had to guess, I think it would be a sort of teardrop shape, right? Because we know that I can take any complex number in that set, and the line joining that complex number to the number 1 is going to be in, right? Yeah. And so what I would guess is it's maybe more of a, maybe more like a teardrop shape, because I've got these convex combinations with the number 1 that come out of it. But yeah, great question.
If W can throw some light on this smallest eigenvalue, that would be really very beautiful thing.
I agree. Absolutely right. Yes. Okay. So great question. Thank you.
Further questions, please? Discussion? So if there are no further questions, I'd like to thank Steve for this nice lecture and hope you stay with us for a little bit further. Thank you
Definitely.
again. Steve, this is for you, but I'll keep it with me.
Very good. Thank you so much.
That should be an electronic way of sending it.
Thank you, Professor. I would like to thank Professor Mohar for chairing the session. Thank you, sir. So we now have a small special session where we will greet Professor Bapat a very happy birthday. I request Professor Prasad to take over.
You want me to read out something for him? I don't have to tell again and again about Professor Bapat. I told you many times that he is a strong figure behind us that made me stand before leadership. But as a part of my okay. As a part of this presentation, I must be able to. I am supposed to read out something about him. Shall we ask him to, Raksha? You can request him to come and to the stage. Okay, on behalf of you, I'll request him to come and sit here. And what about Mrs. Bapat and Sudeep? Mrs. Sudeep is not here.
Just downstairs, sir.
Yeah. You please bring them. Yeah. Just on the other side. They can stand behind. Let's on the other side. Let's on the other side.
Yeah.
No, chair as well as table. Table can come on the little front, no problem. So that we can stand behind him later. Yeah, please, please. Professor R.B. Bapat, he is now adjunct professor at ISI. His research interests are in matrices and graphs, non-negative matrices, matrix inequalities, and generalized inverses. Long back in 1992, if I'm 91, sorry. Am I wrong? It is 1990 or 91? Of what? You visited the ISI Delhi, Bangalore. 89. 89, yes. That's when I started my research career. He came into that particular place and somehow we started working together along with my mentor, KPS Bhaskar Rao. And that's how I started my research career. He published more than 140 research papers in these areas in reputed national and international journals and guided 3 PhD students. He has written books on linear algebra published by Hindustan Book Agency, Springer, and Cambridge Press University Press. He wrote a book on mathematics for general readers in Marathi, which won state government award for best literature in science for 2004. Professor Bapat has been on the editorial boards of linear algebra, linear and multilinear algebra, Electronics Journal of Linear Algebra, Indian Journal of Pure and Applied Mathematics, and Bulletins of Kerala Mathematical Association. He has been elected Fellow of Indian Academy of Science, Bangalore, and Indian National Science Academy, Delhi. Professor Bapat served as President of Indian Mathematical Society during its centennial year, 2007-2008. At that time, he delivered one particular talk, which was published in that particular book volume we published in 2014. Its title is Difficulty of. Can you please help me in recalling that? Difficulty of being mathematics.
Challenges and frustrations.
Yeah, challenges and frustration of mathematics.
Being a mathematician.
Being a mathematician. Okay, you all mathematicians must read it once. You can ask me if you want. I'll provide you a soft copy or hard copy for you. For the past several years, he has been actively involved with the Mathematics Olympiad program in India and served as national coordinator for the program. Professor Bapat served as head ISI Delhi Center during 2007 to 2011. He was awarded the JC Post Fellowship in 2009. With this short note, I congratulate him today for completing 69 years and touching 70th year. And please.
Take a seat.
No, not right.
Take a seat.
Yeah. Now Raksha must take over the rest of the program. Oh, not this. Okay.
I request Professor T.S. Raghavan to honor Professor Bapat.
Yeah. Yeah. Yeah, please sit. Here, please sit. Please sit.
I am really very, very proud of Bapat. I have to say, he brought name and fame to the combinatorics in India, and he has been one of my most outstanding students. I pushed him into analysis. He resisted analysis. He said, I am very much interested in combinatorics. But then if that is the case, try to solve van der Waals conjecture. That's how I was pushing him. He settled up to n equals 6. And then came the Felikman, and I'm forgetting the name. They had just then settled it. And then it was, the entire thing depended on Alexandrov inequality, which was missing even in the most so-called encyclopedia on permanence. And when Alexandrov inequality was, he gave a very ingenious proof of that inequality, Bapat. I said, you should publish it as a separate paper. Then it was included in our book. He never cared beyond that. But later he has been carving out new directions, especially on the connection between the eigenvalues and the graph of non-negative matrices. That direction he has taken to great heights, and he has also worked with Gaubert in France, has several publications on max algebra and things like that, which are becoming quite important for many applications, especially applications in scheduling trains to connect each other so that people don't waste time.
In many such things, Bapat's work will become fundamental. That's my honest belief. I'm really proud of him. That's all I can say. Shatamanam bhavati shatayu purusha shatendriya ayushyevendriye pratitittati rojano rojamana shobano shobamana kalyanaham. I am also concerned that he has to take care of his eye problem, and I will do anything for him. That's all I can say. Thank you.
I now request Mrs. Bapat and Dr. Sudeep Bapat and family to join Bapat sir.
Sorry, ma'am.
Now we request Professor Bapat to cut the cake. And the new addition of his family also is getting the cake. We're very happy for it.
So, to the youngest member of maybe Raghavan and myself also can join. Yeah, please come. No. You are the one who is honored.
What?
Please come. Okay. Yeah. I'm very much here. Yeah.
Then you have to do it.
Now you are.
Thank you very much, Professor. So,
Maybe we want to.
Papa, happy birthday, best wishes to you. And I have
Happy birthday to you.
Happy birthday. Happy birthday to Professor Bapat. Happy birthday to you.
I have to make one more announcement. That 60th birthday of Manjunath. We don't want to keep it quiet.
Yes.
He has done so much for the mathematics and for everybody that we should celebrate his 60th birthday also. So I propose
that there be some kind of a cake and his birthday wishes, which happened just recently, not too long ago. He's 60. So I wish him a long, happy, healthy life. Please. You are the other family member. Come. Back one.
Steve, on behalf of you too.
Happy birthday. Happy birthday.
Happy birthday to you.
Bapat played a very important role in my life. He deserved to have the first.
No, here you.
Yeah.
What's your duty?
For me.
Hello.
Yeah. Thank you.
Happy birthday. Happy birthday. Happy birthday.
It's okay. It's okay. Enough sweet for him.
He plays the role of daughter for sure.
One more announcement. There's a card for Manjunathan. Let everybody sign it for his all the activities he has done for mathematics on his happiest birthday. Please sign this card. I'm keeping it here for everybody.
Maybe Steve like to say something for Bapat. Probably he.
Professor Steve, if you want to speak few words, please.
For Bapat.
For Bapat sir.
And from Manjunathan.
I'd be delighted. So I visited India for the first time in the year 2000, and I had the great good fortune to visit Ravi Bapat ISI at that time. He was a fantastic host. We had a lot of great mathematical conversations, which I really enjoyed. He arranged for me to take a tour of Delhi, which was absolutely mind-blowing for me, unforgettable experience. And as Ravi mentioned, he also visited my very close friend and collaborator, Mickey Neumann, a few years later, and we were able to work together. That was a very enjoyable thing for me to participate in. And he sent me a lot of great people. Lots of great people came from the Bapat school to work with me formally, informally, as postdocs and as colleagues. And really, he said it was good for them, but I think it was also very, very good for me. I have watched matrix theory become an important subject in the Indian mathematical community, and I believe that Ravi has quite a bit to do with that growth, and so thanks to him and congratulations to him.
Thank you, Professor. If anybody in the audience wants to share your thoughts, please.
So let me start by saying happy birthday, Bapat. Though I don't work in matrix theory and I'm more of a functionalist, I have shared a long years of administration with Professor Bapat. And this is another very nice aspect that I want to point out. He's also very patient administrator. When he was head of the Delhi center, I was head of the Bangalore center. And that's probably the time where we interacted most, since our mathematical interests were not so common. So again, wonderful time we all had at ISI, thanks to Professor Bapat.
Uh, we are at ISA Delhi for a long time. We had a very long association. Our research interest, it doesn't exactly match, but it is very close. No? But, in fact, we tried to look each other's research area, and we are associated with many events, scientific events. And when he became the head of ISI Delhi Center, I asked him that, is it okay that this is fine with you? I mean, to take this responsibility. So he said that it is a challenging one, and I want to take that responsibility. Anyway, academic work I have done, so I want to see it, take up as a challenge. Perhaps that motivated me later on, no, that so when my opportunity came, he said, no, no, you must take. So I was very reluctant that to take up that responsibility of the center. And so he persuaded me to take up that. And so I somehow that took it, and then took it as a challenge, and then tried to meet it. And he was a good advisor, and he gave very solid advice, no, that so that and he used to guide us that you should not get into problems, you do this, do that, and all. So I'm really happy and to be associated with him, not only as a colleague, but also that we are very good friends, and we have spent a lot of time together, and we are still continuing that. So I think that every week we try to speak, no, that what is happening, and that what we are doing, and so on, and updating, no, that even though now we are not staying in the campus, we are at two different places, but we are in a good communication. So happy birthday, 70th birthday, 69th to 70th. So it's a good milestone, and it's a good opportunity that it came on at the right time. And I am glad that you are organizing such things. No, that Delhi, that we do not have much of such strength. That but you keep everything in mind, and you are organizing. That's great, I think. And as far as his academic contribution, no, that I'll say that you have enhanced that, particularly that organizing ICLA and many other academic activities. No, that I'm really happy, no, that we are not able to do many such things at ISI, in particular the special matrices. I'm very glad that we are working so long on special matrices, but we could not organize any workshop, and so he could organize that, and perhaps that will give a special flavor to special matrices, and many of the young researchers will be working in this that emerging field, and where there is a lot of scope, and in fact, all of the scientific community, you know, that who are here, they will really that we are really that we will not forget his contribution. That yeah, hope it will continue. I think he wants.
I can certainly say it's very difficult to organize a conference of this size. For you must be very self-effacing person. You must have a great ability to collect a bunch of superb volunteer force, and it is not to promote oneself, it is to promote the field. Yes. Okay, that is the difference. So if I want to promote myself, I start writing a few lemmas and theorems and publish it in here and there. That doesn't make anything significant for the community, for the subject. So when I take, for example, when I think about Professor Mahalanobis, when he built the institute, he could have been working, but he spent all his time, Professor Chandrasekharan of Tata Institute, he sacrificed his mathematical skills for building up, picking up the best of the brains to be associated with the institution, like Professor Seshadri or MS Raghunathan, or you take many of those people, on their own, they would have done research. Seshadri was the first person also tried to build a new institute, Chennai Mathematics Institute. So in that sense, Manjunath's contribution is quite significant, carving out linear algebra, which is becoming quite central to all applied mathematics. In some sense, it is quite central, and to emphasize on that, to encourage the younger generation to get into that area, that is his fundamental contribution. It's not easy to beat it. Thank you.
I am Yegambram, retired ISS officer, that is from the Indian Statistical Service. I did my PhD from Delhi ISI after joining the service. My guide was Dr. S.R. Mohan, and I did my PhD in generalized inverses and linear complementarity problem. The topic generalized inverses, Dr. Bapat was also working on that. That was the topic that drew us together. And since I was also staying in the campus of Delhi ISI for a brief period, I had close association with him. And he used to contact me because this subject is, he is so much engrossed in the subject, and we were all interested in research. That was the environment we had in Delhi ASI, devoted to research. At any time you can meet and see, we will talk about different research topics. That was the only thing we had there. And that drew us together. And that's the way the relationship grew. But when I used to give some ideas or something, whatever was there in my mind, but then Dr. Bapat is very precise in mathematics. So you say, no, you don't make such statements immediately unless you see it correct, whether it is correct or not. So it is, then when I verified, I found it, yeah, it was wrong. There was something wrong, and I used to correct. So that was his stature. And I know his family also. And the relationship, if you say, between myself and Dr. Bapat, I can't say he is my close friend. No, I can't say he is my real guide. But there is a sort of relationship which we can't say, I can't describe. And he is always helpful, such sort of amiability, that sort of relationship we had, still we continue to have. I wish him good health. He should continue with his research, though he may not now feel like that, but he should continue with his research because that is the food for us. There is nothing else left for us. So wish him good health, and let him continue his research, and let him help people like us. Thank you.
Hello, sir. Happy birthday. So I am a scholar. I'm from IT Bhubaneswar. So whenever I start like reading this area spectral graph theory, I actually came out with your book. Like I started reading by your book Graph and Matrices, and thanks to my supervisors, Dr. Susmita Barik, she suggested that, and that book actually helped me to like get interest in this area. And I'm very happy to be a part of your this birthday celebration. I'm so amazed and thank you and happy birthday, sir.
I don't need their friends. I need my friends.
Well, thank you, professors, and thank you all the participants. So it is indeed pleasure to witness such a rare event. Thank you, Professor Bapat, for joining us, and once again, a very happy birthday. Thank you, Professor Steve Kirkland, for joining us. Thank you. So we shall now have a short tea break. And I request all of you to be back exactly at 10:50 for the next session. Thank you. Thank you for joining.
Yeah, okay. Then I cannot do them.
No. You also. Back one. I was telling him to worry about it. The only he can do. Nothing comes out. You join together and I've seen some others. So that's why I say happy birthday to you also. So thank you for saying. When are you leaving?
No, my flight is at 6:40.
6:40.
Oh, they postponed it. It's maybe no activity.
Everybody thanks. Everybody thanks to the. No, it is not my birthday. It is your. It is the. Yeah, organizing. So can you make it sign? Some idea. Everybody's important here. And those who are in the association
don't know him better. They can write something about him.
Yes.
Those who are seeing him for the first time.
So it's going to we have an ocean pearl.
Yeah, sure.
Not sure. Okay.
It's up there, right?
Because here a couple of plants. I don't know which one is like. Okay.
Yeah, right. All You mentioned 6 o'clock, no? Sorry, 7 o'clock, no?
Coffee is downstairs. Hello, sir. What do you want? Yes.
Mega, this is our
I'll bring the pen, okay?
Should go around the pen.
Yeah, she's bringing a pen. We'll give it during deep breathing, give it to everyone.
I give my pen.
No, she's bringing a pen. You'll give it to everyone during the tea break.
Yeah, just go to everybody's sign.
Oh, very good. Big boy.
Thanks. Wait, just one more. Just one more.
Just text only. For my son.
ನಾನು ನನ್ನೊಟ್ಟಿಗೆ ಅವಳು ಯಾರೋ ಒಂದು ಹುಡುಗಿ ಇದ್ದಾಳೆ. ನಾನೆಂತ ಮಾಡಿದೆ ನಂಗೆ ಅಲ್ಲಿ ಅಂತ ಫೈನ್. ಆಯ್ತು, ರೂಮ್ ನಂಬರ್ ಹೇಳ್ತೀನಿ.
Marathi. Congratulations to you. That's the 70th birthday. You brought it to this level.
Every year, you people always celebrate. No, 6 years we are
Correct. Very happy.
because both at you. How you think? Because I mentioned now question number 1 is So all set will also.
Like wherever. Because one is partially different. One is oil and steel.
Now I regret.
Partially different is
So
what are doing the. You is the exercise like in short and it's a next question. Like that. Then what? Let it be considered as only conductor because if you ask it will be there. In segment two also. Then segment one, therefore consistency is the common. Maybe you can do beginning to rank. Otherwise you can ask only rank. If it is a big, four by four. This item you are. I try to ask. What is the sleeping mind? Can manage it.
Correct. You are chairing one session today. Two.
Two chair I No, something he said.
She'll be sitting on two chairs.
Yes. Yes, come on, you do. I go. If it's today, sir, I said, in the time, ಐದುವರೆ ಇಂದ ಏಳು. ಐದುವರೆಯಿಂದ ಏಳು.
ಮತ್ತೆ ನಿಮಗೆ ಯಾವ ಟೈಮ್ ಅಲ್ಲಿ? ಬೆಳಿಗ್ಗೆ 5:30 ಅಂತ ಹೇಳಿದ್ರು.
ಹೌದಲ್ಲ?
ಅದಕ್ಕಿಂತ ಇದು ಮುಖ್ಯ.
6:10, 6:30. 6:10, 6:30. These two people are parallel. Yeah, okay, okay. So, okay, that's what I was saying. Now, what time now? Next software.
Okay, there are no more. He's also not there.
He cannot. But he cannot understand my proper English.
No, it's okay.
According to me,
Yeah.
it's okay. My beautiful face came. No,
No, not video, audio, only audio.
Audio.
Your beautiful voice.
Waste.
Your beautiful voice.
It is not recording.
You had been.
Yeah. Submitted to.
Embedding such as this, like many things. Yeah. He likes the students working. Many places people are there working lots and maybe you are trying to do something. Like other
Okay, okay.
you increase I'm just sign the market with a fund does not circular side. They were doing loans using that for that.
Yeah, but it's not mine.
Welcome back, everyone. So we will have the next session of invited talks. In this session, we will have speakers Bowen Moher from Simon Fraser University, Canada, S. Arumugam from Ramco Institute of Technology, Tamil Nadu, and Balaji Ramamurthy from IIT Madras. I request Professor Rajesh Kannan from Indian Institute of Technology, Hyderabad, to chair this session. Sir, please.
Good morning, everybody. So the first speaker of this session is Professor Bowen Moher. He's a professor in Department of Mathematics at the Simon Fraser University. So he'll be talking about extremal trees for eigenvalues combinations. So Bowen's research interests include topological graph theory, graph minus, graph coloring, algebraic graph theory. So he published more than 272 journal articles, and he wrote a book and 7 book chapters and 52 conference papers. He's the editor-in-chief of the Journal of Combinatorial Theory Series B, and then Electronic Journal of Combinatorics. And he's an associate editor for the journals Discrete Math, LAA, and so on. So he was awarded as a fellow of Royal Society of Canada. Then he's a SAM fellow. He's an AMS fellow. He got Euler's. Yeah. With this brief introduction, I request Bowen to start. Over to you.
Okay, thank you for the introduction. They're still checking some technical issues here, but let me just start briefly. Okay, so it's working now. Thank you to the organizers for including me in the speakers list of this interesting event that unfortunately I only had to miss the first 2 days, more or less. So this is a joint work that I'm going to present with some of my students and a postdoc. So Hitesh and Shivaram, they both came from this country. So Shivaram is actually here in the audience. And Harmony Jean was a postdoc, my postdoc last year. The talk is on spectral graph theory. So you will see more graphs than matrices, but basically what I say, I view a graph like this one on this whiteboard as a 9 by 9, is it 10 by 10 matrix? So it's I just view its adjacency matrix in this graph form. So it's basically I will be speaking about matrices, but instead of showing matrices, I'll just show you graphs. So it will be 0, 1 matrices corresponding to these graphs. So so let me start the presentation with some motivation. So here is an invariant W of G. For given graph G, you look at all pairs of vertices U and V, and for each such pair, let's say this one and this one, you compute the distance in the graph. So here the distance is, I guess, 1, 2, 3, 4, 5, 6. So for all pairs, unordered pairs, you sum up these distances. You take this sum, and you can express it as a summation in this formula. It's called the Wiener index. You can, if you normalize it, you can also view it as an average distance in a graph. So now, why is it called the Wiener index? Actually, there was more than 60 years ago, there was a paper by Harry Wiener, chemist in Austrian chemist at that time, who found out that if you look at graphs which correspond to molecules of certain compounds, more closely paraffins, then the boiling points of those molecules are in perfect correlation with this number, with this graph theoretic number that you get here. So the bigger the number, the bigger the boiling point. And here is a plot of different trees and corresponding to these paraffins, and you see it's almost perfectly linear correlation between the two things. So what does this tell you? So it tells you that you can somehow, instead of first making the molecule, you can just compute this simple number and then predict what will be its boiling point. And this type of thinking grown up into a big area, especially in pharmacy. So in pharmacy, they try to look at a graph of a molecule. Maybe it's a weighted because it's not only carbohydrons, and it's in a graph. And then you try to, based on this graph, you can try to say, well, maybe this molecule has certain properties. Maybe healing, it's good for cancer, or it's good for that, and so on. And because the chemists today, they can produce more or less anything, but there are zillions of possible choices of chemicals that they can produce, and so they have to make a good prediction what would be useful for them. That comes, that's a kind of some motivation behind that. Now, this doesn't look like spectral graph theory so far, but if I go to the next slide, you can actually express this quantity by eigenvalues. So what is the theorem here is that if you have a graph which is a tree, and then you compute this sum of the distances, this sum of the distances is essentially the sum of the reciprocals of eigenvalues. And here it's not the adjacency matrix, here is the Laplacian matrix of that tree, of that graph. So the smallest Laplacian eigenvalue is 0, so that one wouldn't have the inverse, but then the next one is positive, and so on. And so you take the reciprocals of all of them, and it's exactly the same as the sum of distances. This is a kind of a famous looking formula. It's the proof is not difficult. It's actually, you see it here on the slide. The proof is basically that just you look at the inverse of this Laplacian matrix. Well, Laplacian matrix is singular, so it has a zero eigenvalue, but once you quotient out to the subspace, you get this so-called Moore-Penrose inverse. And then this holds for not only for trees, but also for general graphs. This inverse of the Laplacian is essentially the resistance matrix. So the inverse, the entry in the inverse is the resistance. If you would think of the graph as the electrical network, and then you measure the resistance between 2 points in this, made of wires, all the same resistances, right? So that would be giving. And you see, if you have a tree like this one, you take two vertices, U and V here. So if you think of this as what would be the resistance, it's just resistance 1 for each edge, so the resistance will be just the same as the distance, right? So that's how you get this inequality, basically. Okay, so we're approaching eigenvalues a little bit. There is another, of course, classical application in mathematical chemistry relating eigenvalues with chemical properties. Namely, in this Hückel theory, you can model the energies of electrons as being proportional to the eigenvalues. So this, for the adjacency matrix of a graph of a molecule, the eigenvalues are somehow correspond to the energies of electrons. Okay. Maybe you can do the next slide.
Can you change right? Can try to.
Yeah. Okay. So let me make some more comments while they settle up this technical issue. So one thing that comes out of this, I want to say, is that eigenvalues of graphs are interesting, and maybe they correspond to molecules like here. And this gives us a view what a mathematical question would be interesting for us. So, for instance, if you look at trees which have vertices of degree which is bigger than 4, they will not correspond to such molecules where carbon atoms appear, because carbon atoms are 4-valent. So that's kind of wouldn't be chemically significant molecules. Okay, so to start with, I will look today at the problems of the following kind. So we look at some family of graphs, and I will assume always connected graphs. So all families will be connected graphs. Maybe trees. So this could be all trees on n vertices. Okay. And then we wonder what is the maximum possible eigenvalue of trees in this family, or the minimum possible. So this is my notation, lambda 1 of G, or just lambda 1, I will omit G, will always be the largest eigenvalue, the spectral radius of the adjacency matrix. Lambda 2 will be the second one, and so on, up to lambda n. And n will always be the number of vertices. So it's a kind of easy to follow. I'm not mentioning this everywhere. So I'm going to speak about the adjacency matrix all the time. So take a family of graphs and then ask what is the largest or smallest possible eigenvalue in this family. So in graph theory, we would be in chemistry, they would be interested in chemical graphs. They would have maximum degree 4 and so some restrictions. In graph theory, we would be interested maybe in planar graphs. Planar graphs are graphs which you can draw in the plane without edge crossings. Do they have some kind of special properties or not? And so on. And today I will speak mainly about general case all graphs. This will be basically just two families that I will be dealing with, will be all connected graphs on n vertices or all trees on n vertices. So two kind of extremes there will be in the discussion. But just remember, we want to find a graph in this family so that its spectral radius is as large as possible. I call this lambda 1 maximizer. So lambda 1 maximizer. We can also talk about lambda 1 minimizer, or you can talk about lambda 2 maximizer. So that's
what is lambda 1 minimizer?
Lambda 1 minimizer is which graph in this family has the smallest possible lambda 1, right? So
Smallest possible, but
lambda 1 is the maximum. Yeah, sure, exactly. So it's min max and or max max and so on. Yeah. So some of these questions about these maximizers are kind of easy to answer. For instance, if you can always say what's the lambda 1 maximizer in all n-vertex graphs, because the spectral radius is monotone to adding edges, so you would add as many edges as possible, so you get a complete graph. But so this is in Gn, like all graphs. And if you look at all trees on n vertices, what would be the lambda 1 maximizer? You want a vertex of big degree. That's and it's kind of easy to show that. Yeah, it doesn't show here. So it's kind of easy to show that the star, so a vertex, a graph with one vertex adjacent to everybody else, gives the largest spectral radius, which is square root of n minus 1. That's for the stars. So this is a kind of easy to do. Minimizers, when you ask, so you see on the trees, the path will have the smallest possible lambda 1. It will be actually smaller than 2 because the path has eigenvalues strictly between -2 and +2, right? So this is the result for the path. But now if you go for the lambda 2 for the second eigenvalue, so you don't care how large is the first one, but you want the second one to be large. You see, this is not a good example because a complete graph has one huge eigenvalue and all other eigenvalues are -1. So it's very small. It's even smaller than 0, right? But you can get a graph, and it turns out this is the maximizer here. You take a graph which consists of two complete graphs and joined by just a single edge to make it connected. So you wonder, why don't you add more edges? Well, that will increase lambda 1, right? If you add more edges between these two parts, left and right, but it will decrease lambda 2, right? So that's the interesting effect. So this is a kind of less trivial.
So if we specify lambda 1, lambda 2, lambda k, I specified numbers lambda 1, lambda 2, lambda k as the maximum eigenvalue.
Right.
Will you be able to construct the graph which will correspond to that?
Not exactly. So I mean, this is like the inverse eigenvalue problems, right? So it's not exactly, but of course there are many. I think there are quite complicated constraints, right?
Yeah.
That you need to have. So but the maximum is kind of maybe achievable. So yeah. I will discuss a little bit later the sum of two eigenvalues, so lambda1 plus lambda2. This will be, so you cannot specify what they are, so they cannot be too big, but it's what is the maximum possible value? This you can do, right? So for trees, if you look at the trees, what's the maximum possible lambda2 on trees? It turns out that the graphs get this nice structure in the theorem. So Neumeier proved it back in '82. There was a mistake in one of the, I think in the odd case, there was a mistake. So he missed these three families, which was cured by Hofmeister, kind of almost 15 years later. But let's say that the number of vertices is even, then this looks like a double star, right? Two stars and then maybe a vertex in between. So you can view this also as two stars. This is include this vertex in the star, so two stars which are maximizing lambda1, and then an edge between them, right? So that's a kind of similar structure as for the maximizing lambda2 on all connected graphs. And you see, I just want you to understand. So if you maximize lambda2, the lambda1 should go down, because you have this. This is just intuition is that there is this basic obstruction that the sum of lambda I squared. So you take all squares of all eigenvalues. On the trees, this is just twice the number of edges. So this is fixed. So if you want lambda1 large, then the others will somehow have to be small, closer to 0. That's the kind of extreme question which becomes of interest. Now, so these are the old results, and I'm not going to go into the proofs, and also won't be able to. Oops, sorry, yeah. But I will discuss a more general question, what I call combinations of eigenvalues. And in particular, I will, just by the time constraint, I will focus on the question when I take a convex combination of lambda1 and lambda2. So maybe I take lambda1 plus lambda2, which in this setup with a convex combination, so when I normalize the coefficients, I would say 1/2 lambda1 plus 1/2 lambda2, or alpha times lambda1 plus 1 minus alpha times lambda2. So that's a convex combination of the two. And so for every alpha between, so let's say beta is always alpha minus 1 minus alpha, and it's positive. So for every alpha, you can discuss what is the maximizer for this convex combination. So which tree will give the maximum value of lambda1, alpha lambda1 plus 1 minus alpha lambda2? So we know the result from the previous slide when alpha is 1 and when alpha is 0. We know the two extreme answers, but what is in between for every alpha? And then you will see later also the normalized value. So with this hat, I will denote the same maximum. So what is the maximum possible value of this combination? But normalize it, divide with square root of n roughly, because then this will be between 0 and 1. So it's kind of normalization. So it will show that you can then compare these things for different n. It's not necessarily the same n. And to mention, I'm not only interested in small n, I'm mainly interested in what happens in the limit. So that's a kind of phenomenon. So what is the limit? So can you see the limiting behavior somewhere? Okay, so this you have to remember. So phi will be n will be on n vertex graphs, and then with the hat will be normalized. So it's this maximum possible value of this sum of the eigenvalues. So here is the sum. I should mention that a very interesting question is also a difference between, so the spectral gap, the difference between lambda 1 and lambda 2. So what's the, again, minimum or maximum on trees? And it is even on trees, it's kind of challenging. So it's kind of challenging to get the exact results. Okay, so here we are. So you look at this function phi. Now you can think of phi as well as follows. Take any tree. Take any tree on n vertices, compute lambda 1 and lambda 2, and then you compute alpha times lambda 1 plus 1 minus alpha lambda 2. So you get certain values. So for each alpha, for each tree, there is a line like that. So it goes from lambda 2, where alpha is 0, to lambda 1, where alpha is 1. And it's in between, it's just a straight line. It's just a linear convex combination of the two values. So these are the values of this function phi n. Well, phi n would be the maximum. So you take all possible trees, you get these lines, and then you wonder what is the maximum here, like this yellow line that I wrote. So of course, there are not just 4 trees. I just draw an example of 4 of the trees, but it's this upper envelope will be actually the answer. What is this phi n? So this is a kind of analytic view to this function phi sub n. And we wonder what happens. So it looks like it's piecewise linear function, but how many steps are there or whatever? So this becomes interesting, and then also it becomes interesting on the negative side, but I'm not going to speak about that today. So one result that we got, I can show what is happening asymptotically. So when n is very large, think of n being very large, we can actually show that this function, this normalized phi, converges pointwise. And the convergence is actually going to a curve, which is like this red curve here. It's interesting that this curve is flat for all alpha between 0 and 1/2. So if you just maximize lambda 2, you get this, that double star that I showed you. It will have eigenvalue roughly square root of 2 divided by 2 times square root of n. So this normalization constant, right? But even if you go to 1/2 alpha, 1/2 lambda 1 plus 1/2 lambda 2, you still get the same maximizer. So it's the same, but things become interesting just after that. So after 1/2. So that's the kind of result. And you see, this is a limit. And then for every fixed n, you have something which is below, like this green line below. Here, the result is a little bit different. You can get maybe 1 or 2 steps just between 0 and 1/2. So it's a kind of strange situation. And the reason that you get this in between steps, that's kind of okay. The reason that you get in between steps is that you sometimes, when n is even, you don't know what is the maximum. So one of these 3 may occur in between when you go with alpha from 0 to 1/2. So it may change a little bit. So which one of these 3 will give the maximum? Okay, so that's a pretty well behaved function. How do you prove that? So you look at this function phi. Well, it's sub n, but it's and then you look at the tree which maximizes this function. So and then you compute this alpha times lambda 1 of that tree and this. So you get this maximizers. And what we show is in the proof, first it's combinatorial part. Combinatorial part, you show that the maximizers will look like these double stars, more or less. So anybody can, I guess some of you can see motivation. Why would you get double stars when you consider lambda 2 to be large? You see, if you have just a single star, like in this example here, so think of this being of a huge degree. So this will have largest eigenvalue, large spectral radius. But the second eigenvalue will be small. So, and the reason here is it's much easier to show it with a graph than with a matrix. So the reason here is that you can delete this vertex and then just apply Cauchy interlacing theorem. So you see, you get the submatrix corresponding to this, and you see it's a union of paths. So the largest eigenvalue will be between -2 and 2. So it won't be very large. It will be very tiny, right? So if you want lambda 2 to make a contribution, you want that after you delete one vertex, you still have another vertex of big degree, right? Okay, so that's the first part. Then you do, and then the second part is that once you have that, you try to see, well, what kind of stars, how large this star would be and how large this one would be. You can just say I take a fraction of n vertices here, so t times n, and I want this t to be more than 2, so this is the bigger part. And I take the rest of the vertices on this side, and then you can just say t goes from 1/2 towards 1, and you can just do the optimization computations for the eigenvalues. So that's how you get roughly how you get this red function, the phi hat. Okay. So this is this answer gives more questions than answers. So you can answer what happens for a particular n and so on, and you try to classify the exact values. Okay, now let me finish with a little bit different question. And so, yeah, this is eigenvalue minimization. Maybe I won't go with this one, but let me just go to the next slide. Let me ask the following question. Let's take, instead of all trees, people looked at all trees which have certain diameter. So you see, you maximize lambda 1 and you get a star. This has just diameter 2. The largest distance is 2. Now, if you want to get the diameter d, you will get a different answer. But what it turns out is you get something which I consider as a naive or stupid answer. So you just get, basically you get the same. If you maximize lambda 1 on trees which have 2 vertices at distance, let's say distance 100 or distance 10 in this case that I draw here, you would need such a long path, and then the maximizer of lambda 1 will have just one big degree vertex in the middle of this path, and and making a large degree then. So that's so this is a kind of answer which doesn't say much. So this, you know, when I come to this, it looks like my starting point was that you should look things which will be interesting for someone. So why would this be interesting for someone? Because you get such a strange outcome. But in fact, actually, we worked on this, and it with my students, and I actually got quite happy with the final results, because the proof methods were challenging. This was one thing, so there was no clear proof method. But let me show an interesting outcome that we got. So here is we get that you minimize lambda 2 on, for instance, just minimize. So now not maximizing here, it's minimizing. So if you minimize lambda 2 on trees and you have diameter d, you will have such a path of diameter d, and then what you show is you will have somehow in the somewhere in the middle you will have a vertex of bigger degree, and there will be some trees hanging out in there. And what would these trees be? So it turns out that the result is actually pretty nice. So if you minimize lambda 1, you actually can, lambda 2, sorry, you can actually achieve that it is smaller than 2. So it's smaller than 2. What does it mean it's smaller than 2? Again, by interlacing, if you delete this vertex, what remains, every graph is basically a path. There are a bit more general graphs. I don't know if, I guess people working in combinatorial matrix theory know that trees with maximum, or even graphs with maximum eigenvalue less than 2 are classified. These are so-called Smith graphs. They are kind of related to this root systems and some geometric applications, but basically look like paths, and maybe a path with one vertex of degree 3, and that's basically what you get. So these graphs are classified, but it turns out that the structure here is not just a star, but you get this kind of a nice variety of, and then you want to know that this half of this path, the spectral radius of that will be actually equal to this lambda 2 of this graph. You see, if you have an eigenvector where the value at this vertex is 0, so that's what you show in the proof, that normally you would get a vertex where the eigenvector for lambda 2 will have 0 here in this vertex. And then if it is 0, you just look at the submatrices corresponding to these components when you delete the vertex. They will have the largest of those largest eigenvalues will be actually lambda 2. So because this lambda 2 vector will work for all of them. So so that's a kind of interesting outcome. And the second outcome of this is that it might lead to some more insight of interest. So I'm interested what happens when the structure becomes large. Maybe here basically when the number of vertices grows to infinity. So can you say some limiting behavior? What comes out? So if you think of these graphs, and then just d grows, so n would be just d plus some constant number of vertices, then basically this path, the bottom path, will extend to an infinite path. So what you get as a limiting structure will be an infinite graph, and then you consider the spectrum of that infinite graph. So it's you can define a spectrum of infinite graphs. It's no longer eigenvalues. It could be continuous. So it's it's a more complicated, it's a little bit more complicated one, but it's that's a limiting structure. So this kind of simpler setup already shows that maybe there is some way that we can describe such things, and this is something I'm looking forward to do. So
in the case of infinite graphs,
yes.
So you have the eigenvalues. See, it is more to do with certain compactness conditions.
Right. For
And
infinite graphs, you would like to have degrees wouldn't go to infinity, so degrees should have to stay bounded.
And then the sequence which you choose itself must go to zero in some sense.
Right, because you for infinite graphs, I didn't define that.
Yeah.
You don't consider the space. So for you have R to the V for finite graphs. So it's for infinite graph you have L2 space.
Yeah.
L2 of V. So this V is infinite now, and then you look at vectors would be all vectors which are square summable. So you want the sum xv squared is finite. So you have a linear operator on this, and then you look at the spectrum of that in a sense.
The only compact operators are well understood in that sense.
Yeah, compact operators are only graphs with finitely many edges, actually. But bounded, they are bounded, actually.
Yes.
The trees, if you have bounded degrees, they are then bounded, but not compact. Yeah. So that would be kind of limiting in terms of operator theory, right? You get to infinite graphs maybe, but there are different possibilities of graph limits. So there is an extensive research in graph theory, so about graph limits, which has also tight relationship with algebraic and eigenvalues. Yeah. So that's it. I think I should stop here, and thank you for your attention.
Thank you, Boyan, for the interesting talk. Yeah. Any questions?
Sir, while describing the molecule, first you have shown, is there any particular reason for considering the carbon bonds only, not the hydrogen bonds?
Yes. So this goes back to this Hückel theory, and basically the hydrogens are so much smaller that it doesn't really make much sense. But it's if you look at the molecule, let me just give this simple one with 5 carbon atoms, okay, and then there will be the hydrogen atoms here. So, but you have electrons which somehow circle around this. So there are electrons which circle between the two adjacent carbon atoms, but there are also electrons which circle all over this, what is called this carbon skeleton. So, and they don't go to the hydrogen because it's kind of chemically it's small. So it's essentially they circle around there, and then that's why you get only so this comes from this Hückel theory, is that you take the adjacency matrix of this, and then you get an eigenvector. So AX equals lambda X. So X has X is a vector. So here is XV, here is XU, and so on. So at every vertex you have this value, and it's somehow like the quantum theory. It goes that this electron, in quantum theory you don't really know where the electron is, right? So once you measure it's a phenomenon of this. So you measure the speed, then you don't know where it is, or you can measure where it is, you lose other characteristics. But what you get is, so for Neumann, this interpretation was that the xu squared, so the sum of x squared or xv squared is, you normalize it, it's 1. And this is a kind of probability distribution then. So you don't look at its values, but the squares of the eigenvector entries, and they give you the probability that the electron is somewhere here. So not here, but here. So maybe probability 1/10 is here, probability 3/4 is here, and so on. So it's that's the reasoning, and that's why. But this is kind of approximation. Of course, it doesn't. So that's normally in this organic chemistry of they look at this thing. Instead of no hydrogens are just neglected. Yeah.
Since it is associated with the energy of the molecule,
right?
Because hydrogen not much affect the.
Right. Yes. Okay. Yes. So this energies of these electrons, this additional, which behave strangely, right? They go all over the place, so that's not affected by hydrogens, right?
Okay. Thank you.
Sir, the benzenes are not like related to this boiling point of benzenes and the Wiener index of benzenes. So
what is it, benzenes?
Benzene, that 666, that cycle.
Oh, the cycles. Yeah. Yeah, it is. No, that's this was just a particular case. So you can also look at the in the chemical graph theory. You can look like molecules like this. So this is all carbon atoms, and then hydrogens are missing, right? You have 10 of them here, and then you saw of course these double bonds pictures, right? But this is not accurate. So there are no double bonds. So this electron, so you would think that a bond means that there is an electron somehow bonding them. But the double electron would be 2 electrons, but it's not. So this 5, which would be double bonds, they go all over the place. So these are of these kinds that I mentioned here. So there are these electrons which go all over the place. It's called pi electrons. So.
Also, that in this question, like when you're taking d tends to infinity, so for different d, this lambda 2 values, they are always distinct. Like, are you like if some cases if lambda 2 is coming like in a repeated way, so are you like consider that sequence like the constant sequence as convergent or not? That's I want to link.
Yeah. So this is a kind of structural. You see, here you get an answer. What is the maximizer? It looks like this, right? This is the answer. I can also tell you how the vector will look like. So basically, the vector mostly will look like eigenvector here will be positive, here will be negative, and it will be lambda 1 of this component, and maybe here it will be just 0. So in the rest. So I can also tell you how the eigenvectors corresponding to this maximizing look like. And then if you look at the limit, yeah, it's I'm more interested in describing how instead of this is very simple. You can just say looks like this, right? But maybe in more complicated situations, you will get something different.
When Hopman started the like limiting condition of spectral radius of symmetric matrix, he considered that the eigenvalues, like you want to take those matrices which has the spectral radius are different. So like the sequence must be a distinct sequence. Like it cannot be constant sequence. Like as just Hopman started the limiting eigenvalues of the spectral radius.
Right. Yeah.
So in your case, like, are you also considering that distinct sequence or the constant sequence? Like,
no, it's not important. Not important, right? Yeah, but you can think differently for different problems. Like Hoffman's work is a type of work, right, that I consider. So he would describe a lot of these things like graphs with smallest eigenvalue -2 or whatever. So between sorry, the smallest eigenvalue is at least some negative number, so maybe -2, right? So, yeah.
If we have a molecule which contains atoms other than carbon, hydrogen, then how we will decide whether we have to change it into vertex set, like to convert the molecular graph into its chemical.
So it's you see, once you get out of this realm of nice hydrocarbons, you can have oxygen atoms and there is a similar thing, but then you have to consider a weighted graph. So if you have a mixture, more complicated molecules with let's say nitrogen and oxygen atoms and so on, you end up with a weighted graph essentially. So maybe it's not the 0-1 matrix anymore, but maybe the edges have weights. So
there will be some variants of edges.
Yeah, and then chemists could, for different applications, I think they can somehow approximate what those weights would be. Yeah.
Thank you.
Okay. So thank you, Boyan, for an interesting talk. Thank you.
I request Professor Kannan to honor Professor Mohar on behalf of CAREMS.
Okay, our next speaker is Professor S. Armugam. He's an adjunct professor in the Ramco Institute of Technology, Tamil Nadu. So he'll be talking about the nullity of a graph. His research interest includes network analysis, graph theory and applications, topology, geometry, visual cryptography, and so on. He has published more than 250 research articles and then more than 20 books. Most of these books are textbooks for many of the undergraduate courses in Tamil Nadu. So he has organized more than 25 international conferences. He has delivered more than 350 invited talks. Okay. So he is an editor-in-chief of AKC International Journal of Graphs and Combinatorics. Yeah, with this brief introduction, I request Professor Armugam to start it. Thank you.
At the outset, I would like to thank the organizers, especially Professor Prasad, for having invited me for the workshop as well as the conference. My previous speaker has given a good outline of how spectral graph theory interacts with chemistry. Nullity is another parameter that comes from spectrum, which also has very significant impact in chemical applications. The nullity of a graph is simply, these are already known, so it's a skip. Algebraic multiplicity of 0 as an eigenvalue. How many times 0 appears as an eigenvalue? That is called the nullity of the graph. So obviously, if nullity is 0, the corresponding adjacency matrix is non-singular, and therefore we call G a non-singular graph. And otherwise, it's a singular graph. Okay. For a bipartite graph corresponding to alternate hydrocarbons, nullity is greater than 0 implies that the molecule is unstable. The molecule is unstable if the nullity is positive. And therefore, they are very much interested in graphs with nullity 0. And this problem was first posed in 1957 by a group which graphs have nullity 0. We don't have a necessary and sufficient condition for the graph to have nullity 0 as of today. Sachs gave a very classical theorem, which most of you may know, gave a very graph theoretical way of computing the characteristic polynomial of the graph. So given a graph G, a subgraph is called elementary subgraph if every component is either a cycle or a single edge. So such a thing is called an elementary subgraph. We do not CH the total number of components and RH the cyclic components. For example, this is an elementary graph with 6 components and 3 cycles. And Sachs proved that if you take the characteristic polynomial of the graph, then the coefficients can be computed using elementary subgraphs. That is, to get the coefficient of n minus lambda over n minus I, take all elementary subgraphs of order I and take summation over all elementary subgraphs of order I, the expression minus 1 power number of cycle components, 2 power total number of components. Okay. So this gives a method of computing the characteristic polynomial without going to the useful determinant. Of course, the computation complexity is not much reduced, but it gives some information. For example, if the graph is bipartite, you see that there is no elementary subgraph of odd order. Because in a bipartite graph, all cycles have even length. So odd cycles are not present. Therefore, all the elementary subgraphs are even order. And therefore, all the odd power coefficients in the characteristic polynomial go away. Therefore, only even powers are sitting. Therefore, whenever lambda is an eigenvalue, minus lambda is an eigenvalue, which is called pairing theorem. In particular, it shows that if the bipartite graphs are odd order, since the sum of the eigenvalues is 0, pairing shows that 0 must be present as an eigenvalue. So at least for bipartite graph, we know that the nullity is positive whenever it's of odd order. Okay, so it's a very simple consequence of the Sachs theorem. Once you know the spectrum, these are all graphs for which we know the spectrum. Therefore, we can get nullity directly. This is obvious that nullity is here equal only if it is the total disconnected graph. For paths, it is 0 if it is 0 mod 2 and 1 otherwise, and so on, because we know the exact spectrum. Okay. Coming to the bounds, we have already seen that it's n if and only if k n bar. Nullity cannot be n minus 1, obviously, because sum is 0, so nullity cannot be n minus 1. So its upper bound is n minus 2 and lower bound is 0. And nullity is n minus 2 if and only if it's a complete bipartite graph.
I just want to know, this one is one component or what? I didn't get it fully.
See, for example,
because I'm not a specialist in that area, I know nothing.
Suppose this is my graph.
Okay.
I take the subgraph. B1, B7, okay, and then I'll take not V7, I'll take V1. I don't take V1 better. Okay, I have put the number here is 7, 8, 9, 10. Okay, so let me take B8, B9. Let me take this triangle. This is an elementary subgraph of this graph of order 5. From the graph, I collect subgraphs such that every component is either a single edge or a cycle.
So suppose if a graph has each vertex has only 2 edges at most.
Okay.
Then what can you say about that graph? Does it mean it has
what are the elementary subgraphs? That's the only question.
Okay.
If it is a star, any element such a single edge. In a star,
yes,
elementary graph is just a single edge.
Just a single edge.
Right.
So is there a situation, because I'm trying to see why it is related.
Right.
It is related to the linear complementarity problem also.
I see.
And where the key idea of Lemke was to compute something, whatever it is, some fixed point or whatever it is. And the basic idea was the graph consisted of an unbounded edge, and then others are cycles. So there was exactly one unbounded edge and the others were cycles.
Okay.
So if I started, the answer must end with one end somehow.
Okay.
That was the crux of the whole argument for the algorithm.
Okay.
So now you are taking a very general graph and then you are computing separate places. See, that's why I was curious. Is there, what is your graph when there is exactly only one edge and the rest are all cycles? That's the kind I was thinking.
Right. It can happen.
Yeah.
I'll take cycles and single edges as components. That's all.
Yeah. And,
even if there's exactly one cycle, it's not the problem. I will take this edge and this edge as an elementary subgraph. It's an elementary subgraph 2 times K2. I need not use the unique cycle that is present, right?
Yeah.
For example, in a tree, every elementary subgraph will be components of K2.
Anyway, we'll talk.
Yeah.
Because I don't want to fully interrupt.
Okay, fine.
The ideas are fine.
That's fine. The nullity is n minus 2 if and only if it is complete bipartite graph. And this n minus 3 if and only if it's a complete tripartite graph. Only when nullity is n minus 4, we got some problems. In fact, I came across this paper by Chang and Huang, which gives a characterization of graphs with rank 4 or equivalently nullity n minus 4. It appeared in 2011. And surprisingly, in the same journal, in the same issue, the next paper was on graphs with nullity n minus 4. So in this graph, in this paper, all graphs with nullity n minus 4 are characterized. And in this paper, all graphs with rank 4 are characterized. But both are same. Both appears two consecutive papers in the same journal. And I came across this paper first. Okay.
Do they have the same result?
Huh?
Is the result the same for both?
Yeah.
Okay.
Both gave the same results, but in two different languages, and appeared in the same journal and same volume as two consecutive papers. Okay. And the language used by these authors was so complicated initially, and they said the proof is a sequence of 10 lemmas, and every now and then saying we are omitting some computational details. So I thought it was very difficult to read it. So I thought I'll compare the two theorems. Sun Huang result is basically the proof is, first they identified all graphs of rank 4 on 4 or 5 vertices. Completely fixed it. Okay. That is the 8 graphs. These are the only graphs of order 4, 5 or 6 having rank 4. This has been verified and then verified through computers, and they proved it. And then they introduced the concept of multiplication of vertices. Given a graph and take a vector of positive integers, replace each vertex by an independent set of cardinality mi, and if vi, vj are adjacent, you take this independent set and take this independent set and make it a complete bipartite graph. This is what they call multiplication of vertices. Every vertex is replaced by an independent set of cardinality mi, and two vertices are adjacent. The corresponding is a complete bipartite graph. So this is denoted by the symbol G dot M. It's easy to see that multiplication of vertices does not affect the rank of the graph. Because after all, it's only going to repeat the same row or column again and again. And with this background, they were able to prove that for a connected graph of order n, rank is 4 if and only if it can be obtained from one of these 8 graphs by multiplication of vertices. It's a very elegant proof. Fine. Now the next paper, they're more or less writing the same thing in a different language. See, they had dealing with R-partite graphs where partite sets are x1, x2, xr, and they are defining so many graphs. A chain like R-partite graph means you take the partite sets, join x1 to x2 as a complete bipartite, x2 to x3 complete bipartite, and xr minus xr complete bipartite. That is what they call chain like R-partite graph, and denoted it by the symbol P, M1, M2, M1. Okay. Then the next family comes from the chain like R-partite graph together with edges joining x2 to x4. They denoted it by the symbol. And then again, join x1 to x4 and x5. Like that, they defined so many types of chain like R-partite graphs. But it's very trivial to note that this is nothing but PR multiplication M. It's saying like R-partial graph is nothing but path where each is multiplied. And similarly, the second P, M1M to M1R, that means he is joining apart from the chain, the path for x1, x2, x. Is joining each vertex of x2 to x4. That means he is putting one more edge like this. And this graph is nothing but multiplication of this graph. So ultimately, I found that the 8 graphs, which they are also giving a family of 8 graphs. Okay, as if and only here. And this family of 8 graphs is nothing but the multiplication of these 8 graphs. In other words, they are proving the same theorem using 2 different languages. But the proof in the second paper is extremely complicated, almost impossible to read. Whereas the first...
But there should be.
Right.
If there is complication of the other one.
Right.
This any other graph is only a combination of this. That should have a complication also.
Right. No, you have completely proved that rank is 4 if and only if it comes from one of these graphs by multiplication of vertices.
No, they have to show only by multiplication of
Right.
vertices. It is
Right. That has been proved.
That has to be
That has to be proved.
That part of the proof is easy.
Right. That's sticky. Right.
So you
That's
have to
sticky.
pay.
Right.
Any good theorem, you have to pay a price somewhere.
Correct.
Whether you pay it in bananas or apples.
Right. Correct.
They're the same editors. Again, who are the editors?
So we were writing a survey on this nullity of graphs. And only then we found that on n-4, some half a dozen papers were there. But we found that all of them are simply can be deducible as a corollary of this particular result. For example, a paper says a tree has nullity n-4 if and only if it has a morphic one of this. Okay. But a tree of nullity n-4 rank 4 can come only by multiplication from G1 and G2. You can't multiply a middle vertex. Because if you multiply a middle vertex, a cycle will come. So only possibilities n vertices have to be multiplied. That shows that these are the only graphs. And similarly, there's another theorem which says that a unicyclic graph has nullity n-4 if and only if it's one of this. Okay. So we unified all the results and put a survey of graphs with nullity n-4, saying that from the one theorem of Chung, all the published papers can be deduced as a corollary. And this was a joint work with Manjunath Prasad and Raksha and appeared in the journal Match. Okay. It's about same thing. We shall skip this. This is our all bicyclic graphs with nullity n-4. Like that, so many scattered theorems were there. This is nullity of graphs with n-4 with pendants. Okay. Graphs with nullity n-5 has also been done along similar lines. That is, they identified all graphs are rank 5 up to 8 or 9 vertices, and they proved that nullity, all graphs with nullity n minus 5 or rank 5 can be obtained by multiplication of vertices. So beyond that, nothing is known. So from the top, n minus 2 to n minus 5 is over. But from the bottom, everything is open. Which graphs have nullity 0, which has nullity 1, we have no idea. Okay. Fine. There's some interesting bounds on nullity.
Only with 4, is it?
Huh?
The successful part starts only with 4.
Yeah.
I see. 3, 2 are missing.
Right. So the interesting bounds for nullity in terms of other graph theoretic parameters. In terms of the click number, girth, and diameter. See, all these things are actually unified. You can be unified. See, click number is the maximum order of a complete graph sitting inside a graph G. And we know that nullity of the complete graph is 0. So you have maximum complete graph sitting inside. So it is that much. Girth is minimum order of a cycle sitting in the graph. That cycle of girth G will appear as an induced cycle, an induced subgraph. For that I know the nullity, so just put it here. Similarly, diameter gives a diameter path. The shortest path is an induced subgraph of the graph G. I know its nullity 1 or 0, so I get this one. So all these 3 theorems just depend on the fact that the subgraph coming out of the parameter is an induced subgraph whose nullity is already known. Okay. So from that, these bounds we were able to get quickly. But we have no idea of where the graphs, where the extremal graphs are sitting inside. For example, for which graphs nullity is exactly equal to n minus omega, are equal to exactly that bound. Which graphs attain the bound? That extremal problems are still unsolved. And there are some interesting graph operations which do not alter the nullity. For example, if a graph has a pendant vertex, remove the pendant vertex and its neighbor, you get another graph. These 2 graphs have the same nullity. Okay. So this immediately tells us that a tree has nullity 0 if and only if it has a perfect match. Because if a tree has a perfect matching, start from a pendant vertex, remove the matching edge. Keep removing a matching edge, ultimately the whole graph will be destroyed. Therefore, the graph is not singular. Whereas if you take a star, apply this operation, remove a pendant and its support, I get n minus 1 pendants, so nullity is n minus 1. That's all. So removing a pendant and its neighbor does not affect the value of the nullity of the graph. Okay, this is one operation. Another transformation is take a path of length 4 where the internal vertices have exactly degree 2. Replace this path by a single edge. This operation also preserves nullity. The nullity doesn't change if you have a structure like this. Anything here, I don't worry. Now you remove this, simply put this edge alone. That is the operation. Okay?
Already there is an 8 between this.
Right.
What is it?
No. Just remove the path and change H V1, V4.
There is already an H, like
Huh?
V1 and V4.
Yeah, it's already existing. That next transformation will tell you what to do. Okay. That's your question, right? If you have a cycle of length 4, where the two vertices have degree 2, you remove the whole cycle. This operation also preserves nullity. So there are 3 operations that have been developed in the literature which preserves nullity. Each of them gives some information. For example, a unicyclic graph is non-singular if and only if you can transform that graph to one of these by a series of operations of type 1 and 2. Let's keep on removing pendants and its neighbors and cycles of length 4 if the two vertices have degree 2. Keep on doing this operation. And if you end up with C3, C5, C6 or empty graph, then this graph is not singular. So as far as unicyclic graph is known, we completely know when eta is 0. Correct? When the graphs of cut vertices, if there is just one component of G minus V, where if you put back the cut vertex, the nullity is related by this, then that's we can get the nullity of the whole graph. Okay, if you have a cut vertex in a graph like this, okay, then take the components G1, G2, Gk, go back. Okay. Suppose there is one graph, one component, say G1, satisfying the property that its nullity is, you put back that vertex in the component, nullity of that minus 1. If one component satisfies this property, the nullity of the entire graph is simply nullity of that component plus what remains. Okay. Well, if there's a component satisfying this, then you see that nullity can be completely determined from the nullity of the components. The nullity of the whole graph can be completely determined from the nullity of the components. And this is a very interesting class of graphs. It has been proved that if you take the line graph of a tree, its nullity is either 0 or 1 for any tree. In other words, if you take G to be the set of all line graphs of tree, then its nullity set is 0, 1. Okay. So nullity of line graph of a tree is either 0 or 1. So they call, for a class of graphs, nullity set is all nullities that can appear in that family. So nullity set of line graphs of a tree is 0, 1. And it is 0 when the order is even, otherwise it is 1. Energy of a graph is defined by sum of the absolute values of the eigenvalues of the graph. And the following has been posed as a conjecture It comes from some argument from quantum chemistry. It says that if nullity goes up, energy will come down. That's what they're expecting. If nullity goes up, energy comes down. I thought it may not be true in general. It may not be true in general. Because even if nullity goes up means more zeros are coming in the spectrum. But there will be some large eigenvalue that will still see that the energy doesn't come down. Okay. So this is an observation posed by or coming from quantum chemistry in 2016, and Gutman verified that statement is true for the so-called banana trees. Okay, but this is not a good support for the conjecture because the banana tree already has a large nullity. The banana tree by definition is you take a set of stars, any size, no problem. Then take one vertex, join it to a leaf of each star. That's a tree they call banana tree. It looks like.
Doesn't look like a banana.
I don't know why they call it.
Why they call banana?
Okay. See, such a tree has already a high nullity because if you remove a pendant and its neighbor, so many isolates are going to come. Once that number of isolates come, nullity is that much. So nullity of the graph is already very high, and therefore it's not a very surprise that this happens for the family of banana trees. So I had a discussion with Professor Gutman, and we came to the conclusion that this theorem is really not a good support for the conjecture that if nullity goes up, energy will come down. So I posed this problem in the workshop conducted here last week. And I'm extremely happy to say that one research scholar, S.S. Shetty from MIT, came up with counterexample. He gave me 3 graphs. All of them have order 16. Two of them are bipartite. The third one is a split graph. And he proved that if nullity goes up and energy also goes up. For all these 3 graphs, for any pair of graphs here, for any pair of graphs here, nullity is going up, energy is also going up, thus giving an interesting counterexample to the observation coming from quantum chemistry. Now you're more or less moving towards generalization that given any integer of the form 8k, we can construct families of graphs of that order such that for any 2 members in that family, nullity is going up and energy is also going up. So we are more or less at the point of completing a research paper coming from the workshop and one of the participants of the workshop. I'm very happy about that. Yes, Shetty from MIT and working with Aarti Bhatt, who is already my collaborator. Okay. But so now I wrote it. Now this is not open. Yes, we have proved that the conjecture is in general false. So only we have to look at the graphs that come from quantum chemistry that force them to make such an observation. If for those graphs we prove that the conjecture is valid, that may throw some light from in the organic chemistry point of view. So we are now trying to interact the quantum chemistry people as to what graphs are coming from the quantum chemistry perspective that made them make such a statement. So at least for those families of graphs, if you prove that if nullity goes up, energy comes down, then that may be a support for the statement. But in general, the statement is not true. So in general, computing nullity for graph classes bounds in terms of other graph theoretic parameters. So far we have bounds in terms of click number, girth, and diameter. This can be generalized if you have a graph theoretic property P such that the minimum or the maximum P set, the induced subgraph, nullity is known, definitely a bound of this type will come. Any graph theoretic property for which the minimal or maximal P set is an induced subgraph whose nullity is already known, then we shall be able to get a bound for eta in terms of that parameter. I am now searching for such graph theoretic parameters. Okay. How nullity behaves with respect to graph operators like Cartesian product or join? You have done that?
No, 2 minutes.
2 minutes. Okay, no problem. So not much work has been done on how nullity behaves with respect to Cartesian product or strong product or join of two graphs or corona of a graph, like that. For example, if you take one graph G, at every point attach a copy of H. This is called G corona H. Possibly the nullity of that can be determined in terms of nullities of the base graphs. So nullity versus graph operations. The characteristic graphs with given nullity, especially for 0 and 1. This middle problem, especially for 0 and 1, is extremely significant from the chemical perspective. So I think I'll stop. 2 minutes overside. Okay, it's not a problem.
Thank you, Professor, for the interesting talk. Yeah. Audience, if you have any questions.
So is there any relationship between the non-zero eigenvalue of graph and its vertex multiplication graph? Graph and its vertex multiplication graph, non-zero eigenvalue relationship.
Okay.
So is there any relationship?
I don't think nullity has to.
For non-zero eigenvalues?
No. Possibly not.
So you give the transformation 2 where the nullity doesn't change.
Okay.
Are there issues for larger paths, meaning paths with length greater than?
Take any path where the middle vertices have degree 2.
Okay, works for any path.
That's all.
Any path.
Any path where the middle vertices have degree 2. Internal vertices have degree 2. Then remove the path, simply join V1 and V4 by single edge. So 3 edges are removed, 1 edge is put back. That is the transformation. For third transformation, all the 4 edges of cycle are removed.
But I think, sir, the question is, I think the question is that the path can be of any length or only of 3.
Huh?
The path can be of any length or the only of length 3, and that's what the question.
You can repeat. What is that? Suppose you have a big path. So I read middle verse and DU2. So what happens? I will remove this and make it a single edge. Repeat. I will remove this, make it a single edge. If the wrong path is available, when verses have DU2, you can repeat the operation any number of times. That's not an issue. Okay?
So does it say that the minimum should be 4 vertices? Meaning the path should be minimum of length 2, length 3.
Huh?
The minimum length should be 3, sir.
That we need minimum 4 vertices to apply this operation.
Yes. Yeah,
It's an induced path.
I can verify the proof later, but I just want confirmation.
An induced path on 4 vertices.
There is no other questions. Let's thank Professor Iwsmga.
Thank you, Professor. On behalf of KRMs, I request Professor Kannan to honor Professor Iwsmga. Thank you, Professor. Thank you, Professor Kannan, for chairing the session. So we will now have a lunch break, and then afternoon session will start at 2:30. Thank you.
You mentioned they can also be proved by find very simple way of
using DFS. And then we start to set up.
I think the graph to the whole here is going to be different. It's going to be different. With the math, rate of the action. Collapse.
Yeah, ability for trees, it seems that you just find about matching more.
But then you got to open that laptop chart.
They will have large,
Contributory talks.
yeah.
It's the same time.
Contributory talk will 5:30
it will start.
5:30.
Okay, okay. No, actually there was supposed to be another timing. Generally, launch start 1:15. Today is so.
Yeah, today is little early because one speaker has not arranged.
Oh.
What transformations of this time? What transformations? Quickly, this answer.
So where is lunch? Oh, with the box. Okay. Yeah, to see what which trees maximize or minimize it, right? Yeah. Is there any one from oh, next is very good.
Just a minute.
Yeah. I check my stuff there. Going up and down. I did
We are
that.
adding,
Previous
increasing the number of same part, we are removing, then only we adding the first and last.
That's important.
That's where
Remove the
people-
path, put singulars.
Yeah,
The graph becomes smaller and smaller.
smaller.
Repeated application
Yeah.
can.
Yeah, not the number of
That way we
parts.
are able to finish the tree quickly.
Yeah.
It's not saying if only there's a perfect match. If you keep on removing, you'll get empty graph. Isolated vertex will never come. So it's not singular if and only because a perfect match.
You can compare it immediately.
Transformation is very powerful. I am now trying to find more transformations of this type. So that preserves
So
my
they
life.
can be reduced.
Then to add the
That
more
will be-
vertices in the path.
That will be
then-
big breakthrough. Getting some more transformations, preserving nullity. That is a good topic. Nullity,
Yeah,
preserving
everybody
transformation.
looking for the, we are looking the linear algebra and everything, rank is.
If
we
I
are-
come see the cholesterol graph, it is 80, 85 vertices. We repeatedly apply this operation and put that nullity zero.
Then we can think.
See, there is a large graph of 80 vertices. Just two vertices are present. That was the number. Only when delta minimum is greater than or equal to 3, none of these operations can be applied. That's why you want to find some operations.
No, these three are not
that
exhausted.
doesn't- huh?
These three operations are not exhausted.
No, minimum degree itself is 3. I won't get a path of this type.
Okay. Then
I was of that type. So, if the minimum degree is at least 3, none of these operations can be applied. That's why you want to find some operations which doesn't depend on the minimum degree 2. Some graph operations that will preserve nullity.
Here also are using in the
Yes, this-
internal vertex we are.
Essentially wants 2 degree vertices. Not there. That is the problem. It's very interesting. Hello. Do you have the this one sometimes there's some good families of non-singular graphs. And for Iwsmga they have completed. This they have completed.
Bicyclic.
Just that present they're able to complete the whole thing.
Unicyclic, only unicyclic with some other
That's what,
things are.
after transformation complete C3, C4, only that much. So it's completely solved. Which unicycle is also nullity 0 completely solved. Which trees are nullity 0 completely solved. If you're only just a perfect match.
Move to the bicycle person.
So finding more nullity preserving transformations is the crux of the problem.
ಗೊತ್ತಿಲ್ಲ ನಿನ್ನೆ ಅವರು ತಾಯಿಗೆ ಹುಷಾರಿಲ್ಲ ಹೇಳ್ತಿದ್ರು.
Two operations basically we are working on. After taking the operation also, that whether this property can have a we try to one of the products for trees. Also unicycling.
But whenever we are touching them, we will, because not all type of clubs.
Observing something and
We can keep in our mind also. But to write how to proof is very difficult.
Nowadays you can observe the things with some complication. Then you are writing the proof and then you get some counter example that yes, one set of graphs. Go to this type of thing, you actually get some insight that okay, the way you are doing it is not. Basically, apply something else and then get the proof.
This is going on.
Some transformations. I used to do in the highest, yeah. Yeah, I go. Well, now I know you. Because yesterday I was going to you.
Oh, yes, yes.
But I did not
Yeah,
know.
yeah. Nice to meet you.
So you are I go.
I am.
Yes.
Yeah, he is a student of public.
I know, I
Yeah.
know.
Yeah, it's over.
In fact, he's the one who had that special.
Yeah, he's okay.
Yeah, how did you come over here? I could not come.
Yeah, yeah, did go. Did go. Sikkim yeah, and Sikkim campus because they have a campus in Sikkim. They have a campus.
So you are in Sikkim?
That's a good question. They have yeah. So,
hello.
ಎಲ್ಲಿದ್ದೀರಿ A has to be, determinant has to be of the inverse.
ನಾನು ಕೆಳಗೆ ಬರ್ತೀರಿ ಇನ್ನೂ ಸ್ವಲ್ಪ ಗಾಡಿಯಿಂದ
By zero.
Point. Which one? I did. He did. Yeah.
Airport ticket. Pick up.
Okay, we go. Yes, sir.
Which
way? This way, sir. Let's be careful about it.
Airport ticket.
And
You are leaving? Yeah, now maybe in the next day. 1 hour. I don't know. I don't know. I see that lunch. Sometimes 6 PM ಗೆ ready ಇರ್ಬೇಕಾ? Okay. Thank you. ಹೌದು. ಇವರು ಶಿವರಾಮ್ ಕೃಷ್ಣ. ಓಕೆ. ಅದು ಶಿವರಾಮ್ ಕೃಷ್ಣನ್ ಅವತ್ತು ಇಲ್ಲ ಇದರಲ್ಲಿ ಇಲ್ವಾ ಮಾಡಿದ್ದಾರೆ? ಕೃಷ್ಣನ್ ಆಲ್ಸೋ ಇದೆಯಾ? ಫುಲ್ ಹೌದಾ? ಅಂದ್ರೆ ಓಕೆ. ಅಲ್ಲ ಅವ್ರದ್ದಾಯ್ತು, ಅವ್ರದ್ದು 4 PM ಗೆ ಅಲ್ಲ? ಅದಲ್ಲ. ಶಿವರಾಮಕೃಷ್ಣನ್, ಶಿವಸುಬ್ರಹ್ಮಣ್ಯ. ಹೌದಾ? ಸರಿ, ಆಯ್ತು. ಒಂದ್ ನಿಮಿಷ, ನನಗೆ ಭರತ್ ಅವರ ಮೊಬೈಲ್ ನಂಬರ್ ಒಂದು ಕನ್ಫರ್ಮ್ ಮಾಡ್ಕೊಂಡು. ಮೊಬೈಲ್ ನಂಬರ್ 2 ಹೇಗಿದೆ ಇಲ್ಲಿ ಬಸ್ ಅರೇಂಜ್ ಆಗಿದೆ ಬಸ್ಸಲ್ಲಿ ಬರ್ಬೋದು. ಅದು 6:30ಗೆ ಮುಗೀತದಲ್ಲ. ಹೌದು ಹೌದಾ ಹಾಗೆ ಬಸ್ಸಲ್ಲಿ ಓಕೆ ಬರ್ತೀನಿ ಹೌದು ಇಲ್ಲ ಇಲ್ಲ 6:45ಗೆ ಆಲ್ಮೋಸ್ಟ್ ಬೈಕಲ್ಲಿ ಬರ್ತೀನಿ ಬೇರೆ ಎಲ್ಲ ಹೇಗೆ No, I was thinking with it.
Because I was already invited.
Maybe you can, but you also make them on the one
Parking is there. Same hotel where we had dinner other day. Yeah. Okay. Yes. Okay. Thank you continue.
Value zero, and then again, zero is just the number of supporters. So it's not. But, this would be just shrinking of that thing so that the quantum can be met. For this normal, would be the same for regular round.
Before, so
I'm just coming from here. Yeah. So. Show them. Show them.
The wrong way,
Go for a play. Not now, after graduation. 4 days automatically comes up. Yeah. Where the brain is, body. Yeah. Okay. Suppose no pain in the body. Right? This is some time. Because we finished on you are serious because we from this I have to be no, it's
I don't. I don't know. It's not really. It's something. So I don't know how to use One gap in the game. Is there a Wi-Fi here?
Yeah. Yeah, I will give you a credentials. Just if I give.
Okay.
No, I don't. But now
Oh, it will finish.
No, he is the second of course there. This was there. He is young. Yes, and also there is something not sure on the way. I just was already yes, day by day. Yeah.
It existed even now it exists.
Maybe you would speak this.
Elementary, 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 14, no, 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 no. That kind of geometry, but Brahmagupta. And they were using Chennai and they don't get like that. They're using under they're not saying diet. So they know something. If I had known, you can combine mathematics and computing. It's still something. Yes. Yes, yes. He's my one of the best friends. Very no. He's not Chennai. Yes. His son is in. Yeah, good Chennai. I try to see the ball. Yes. And the specifically when he said, not out. Whenever I go by, I totally something separate. I read some scholar in the book. That's what very normal. Like I traveling with no laptop. Yeah, unfortunately, he does not use email. Yes, that's a problem. So I left the call him and we should get it's very yeah, and you told me now. I was in fact no, then one second. Will have one. Yes, sir. Is it looking at before or after the site website? I go SKJ, but I can. That's fine. SKJ is. I don't know. If we write the wrong one, when I'm excited. Problems to education of children. It's very development, education. The new strategy that you will do, they are going to come to then after directly involved with the not to research level, you know, research level. Oh, I know. All the people I used to go to church. Abhyankar also contains. Abhyankar. Yes, yeah, I know. But I think what particularly what you're mentioning to me, that's maybe only that kind of. There are three other approaches. I asked him, I said, I called he's also after chairman from in Chennai. So they asked me around. That's why when I go, I will be able to find him. Let me find him. No, they're not. Certainly about I in fact cover the book which doesn't exist in any explanation book. That always I know RC Gupta guy. RC Gupta. No, this guy, every guy, his father is so many I need to form with because math is not so he has that would be how the person he develops all these processes. 6 minutes, two current more. Now we're talking about something. No, what we're talking about. What I'm talking about is shift. These are the points. And we have done a lot with it. Please, I can talk about you can keep on talking about me. And this, tell me when will this request me? Tell me that. And compare with that. So that was my point. Okay, give me the period and the references and the authentication. Words don't have authentication of the Shastra. It gave me What do you do? Yeah, that's what they watch it with it. Oh, I think Correct. You can start.
No, I have a plan to visit some place tomorrow, so during lunch time I'll be back, so I'll take after lunch. Okay. Okay. By that time I hope it will be ready. Yeah. It will be ready.
After tea break, after tea break.
Welcome back everyone to the afternoon session. Speakers of this session are Professor Rajesh Kannan from Indian Statistical Institute, Hyderabad, India, and Professor T.S.S.R.K. Rao, Adjunct Professor, Mahe and Shivnadar University, India. I request Professor T.S. Raghavan from University of Illinois to chair this session. Sir, please.
Welcome back to this afternoon session. Professor Rajesh Kannan from the Indian Institute of Technology, Hyderabad. He is going to talk to us on the eccentricity matrices of trees, inertia, and spectral symmetry. His research interests are algebraic and spectral graph theory, matrix theory, combinatorics, and functional analysis. He is an assistant professor in the Department of Math, IIT Hyderabad. He has published more than 25 research articles in the areas of linear algebra, combinatorics, and graph theory. He was awarded the Excellent Young Research Teacher Award in 2020, postdoctoral fellowship in 2015 to University of Manitoba, Canada, postdoctoral fellowship under German-Israeli Foundation for Scientific Research in 2014, ISI Visiting Scientist Fellowship in 2013, etc. Without taking much of the time, let's listen to him. Thank you.
Okay, thank you. Thank you, Professor, for the introduction. Yeah, good afternoon, everybody. So I'll be talking about, first of all, I would like to thank the organizer, Professor Prasad, for the invitation and nice hospitality. Okay, so I'll be talking about eccentricity matrices of trees, in particular about their invertibility, inertia, and spectral symmetries. Okay, so I will explain all the terminologies. Okay, so this work is based on these following two articles, one with my PhD student Ishwar, which appeared in Discrete Math, the other one is in Llama. Okay, so start with the basics. So throughout this talk, we'll be discussing with the simple undirected graphs and connected graphs. So most of you may know the adjacency matrix. For given a graph on n vertices, one can naturally associate a n by n matrix whose rows and columns are indexed by the vertex set of the graph. Okay, whose UV entry is given by UV is equal to AUV equal to 1 if the corresponding vertices U and V are adjacent. It's going to be 0 if they are not adjacent. Okay, so since the graph is an undirected graph, it's easy to see that this matrix is a symmetric matrix. So the distance between any two vertices in a connected graph, it's denoted by d of u comma v. Okay? It's the length of a minimum length of a path between them, okay? Or length of a shortest path between the vertices u and v. Okay, and the distance from the vertex to itself we define it to be equal to 0. So, so using this distance, one can define the notion of distance matrix. Okay, so distance matrix is it's again a n by n matrix whose rows and columns are indexed by the vertex set of the graph G, the U with entry is just the distance between the vertices U and B. Okay. So eccentricity matrices are defined like it is closely related to distance matrices. So first let us define what is eccentricity.
How do you describe this?
Okay, so we are dealing with a connected graph.
I don't know the graph.
Okay, so you take a graph. Okay, so suppose this is a path connecting.
Small example.
Yeah, small example. So if it is U and B, so this is the, let's say this is the shortest path between U and B, then shortest. So yeah, count the number of edges in that path.
Sure.
Yeah, sure. Okay. So the eccentricity of a vertex V is defined in this way. That is, fix the vertex U and measure the distance between the vertex U to rest of the other vertices. Take the maximum among all this distance. That's called eccentricity. Okay. So the diameter of a graph is nothing but just take the maximum of all the eccentricities. Okay. So in other words, maximum of distance between any two vertices. Take all the distances, collect all the distances, and take the maximum. Okay. So this is the definition of eccentricity matrix. Okay. So this is defined. So eccentricity matrix of a connected graph. It's again an n by n matrix whose rows and columns are indexed by the vertex set. Okay. So U with entry is distance between the vertices U and B. If distance between U and B is either minimum of it's equal to minimum of EU comma EU. Okay. So one can easily reinterpret it in other words. Okay. So you look at the distance matrix. Okay. The distance matrix, look at a non-zero entry. If the non-zero entry, if it is either maximum in the row or maximum in the column. Okay. So for a given entry, you can find a row and column. Look at the entry, non-zero entry. If that particular entry is either maximum in the row or maximum in the column, then you keep the entry as it is. Okay. If it is neither maximum in the row nor maximum in the column, then replace that entry by 0. Okay. From the distance matrix, this is the way to construct the eccentricity matrix. Okay. So both are same. Okay. So this is quite recent notation. Okay. So this was introduced by Rantage in 2014. So he called this matrix as Dmax matrix. Later in 2018, Wang and Bellardo Rantage again. So they have studied the spectral properties of this matrix. They gave a name like eccentricity matrix. And this is also called the anti-adjacency matrix. Okay. So we will see the reason why it's called the anti-adjacency matrix. Okay, so I gave a simple example. You consider this graph on 4 vertices. Yeah, who read Bobbert's book, you may remember. This is the example from Professor Bobbert's book. Okay, so you take this graph on 4 vertices. Okay, the distance matrix is given by this. Okay, so the difference between distance and eccentricity you can see highlighted. Only this entry is 0. Okay, you look at the entry 1. This is not maximum in the row. It is not maximum in the column also. Okay, second row contains a 2 and second column as well as contains a 2. So we'll replace that by 0. Okay. Okay, so now we are defining a square matrix. It's again a symmetric matrix. So its spectrum is real. So can you say something about the structure of the graph? Okay, using the eccentricity spectrum. Okay, that was the idea. And yeah, so what is the relation between adjacency matrix? So adjacency matrix also can be we can get the adjacency matrix from the distance matrix by keeping only the minimum distances. Okay, so that is in every row and every column, you look at the minimum distance, you keep only those minimum distances, make rest of them equal to 0. Okay, since it's a connected graph, the minimum distance, like I mean in that row, it will be always equal to 1. So you're going to keep all ones and rest of them you will make 0. Okay, so it's a kind of you're doing opposite process. Okay, so that's the reason some people call this as anti-adjacency matrix. Okay, eccentricity matrix and the anti-adjacency matrix both are the same. Okay, so I listed some properties, basic properties. Okay, so yeah, I think most of you may know this. So for a bipartite graph G, the spectrum of the adjacency matrix is symmetric with respect to origin. That is, whenever lambda is an eigenvalue, minus lambda is also an eigenvalue. Okay, and for connected graph, this property characterizes bipartiteness. Okay, so that is, if you have a graph which is connected, for which the spectrum is symmetric with respect to origin, then the graph should be a bipartite graph. Okay. And in terms of distance matrices, the distance matrices of trees are always invertible. Okay. In fact, the remarkable formula given by Graham and Pollack, okay, that says that the determinant is independent of the structure of the tree. Okay, it depends only on the number of vertices. If you take a tree on n vertices, then the determinant is given by this formula. Okay, so by looking at it, you can say the determinant is always non-zero. So determinant of all the trees determinant of all the trees are different from zero. Okay, and if you take a connected graph, then both the adjacency and distance matrices are irreducible. Both the matrices are irreducible. Okay, so why I'm listing all these properties? Just these three properties, we will see what will happen for eccentricity matrices. Okay, so first of all, for a connected graph G, the eccentricity matrix need not be a irreducible matrix. Unlike the adjacency as well as distance matrices, the eccentricity need not be a irreducible matrix. Okay, but it is known that if T is a tree, then for sure eccentricity matrix will be irreducible always. Okay, and the eccentricity matrix of trees need not be invertible. Okay, so in this talk we will see like what are the trees which have invertible eccentricity matrices. We'll completely characterize it. Okay, and then in case of adjacency matrices, the spectral symmetry implies the bipartiteness. Okay, in fact it characterizes the bipartiteness. In case of eccentricity matrices, even for trees, the spectrum need not be symmetric. Okay, then we will characterize the class of trees for which the spectrum is symmetric with respect to origin. Okay, so this is the idea of this talk. So yeah, so first we'll see the invertibility. Okay, so eccentricity matrix of a tree, if it is invertible, okay, so that is invertible if and only if we have only two choices. Either T should be path on 4 vertices or it is a star graph on n vertices. Okay, so all other trees are singular trees. Okay, the proof. Suppose if T is a star on if T is a star graph on n vertices, then both the distance matrix and the eccentricity matrices are the same. Okay, for the star graph, you can just verify the eccentricity as well as the distance matrices, both are the same. So determinant of the distance matrix of the star graph is different from 0. Hence, the eccentricity matrix is also having non-zero determinant. Hence, it is invertible. Okay. For P4, like you can write down the matrix explicitly and you can compute the determinant and show this is different from 0. Okay. So now for the proof, we need some cases. Okay. So let us start with a tree on n greater than or equal to 4 vertices other than star. Okay. Star is invertible. So let us take a diametrical path. Okay. Let V1, V2 up to Vm be a diametrical path. So let us take a path like this. Okay. V1 to Vm. This be a diametrical path. That means the length of the path is equal to the diameter of the graph. Okay. Okay. Let's give some name. So V1, V2, Vm minus 1. This be the path. Okay. Suppose the quasi-pendant vertices, okay, or the vertex which is adjacent to the pendant vertex, if it is adjacent to one more pendant vertex, okay, let's say some V, okay, if this type of structure is sitting inside your graph, then the eccentricity matrix will be singular for sure. The reason is, if you look at the row corresponding to the vertex V1 and the row corresponding to this vertex, new vertex V, both the rows are identical. Because the set of all vertices for which the eccentricity is attained for both the vertices in V1 and V, they are the same. Okay. Hence, the rows corresponding to these two the rows corresponding to these two vertices, they are identical. Okay. Hence, in that case, your graph, your matrix will be a singular matrix. By symmetry, like if there is an vertex, let's say V prime, which is adjacent to Vm minus 1, then by the same logic, see V prime, Vm, the rows corresponding to these two vertices will be the same. Hence, they will be singular. That will be a singular matrix. Okay. So in this slide, that's what I have written. Okay. So in general, if it is having more than like one neighbor, if a quasi-pendant vertex has more than one neighbor, then that will be invertible. That will be singular. Okay. So what's the next case? So V1 and Vm minus 1, they don't have any neighbors like this. These neighbors are not there. Okay. So in this case, So let us first consider the case diameter equal to 3. Okay. So for diameter equal to 3, if diameter equal to 3, then if number of vertices is more than 5, then for sure either this V2 or Vm minus 1 that should have one more pennant vertex incident with it. Okay. So diameter 3 case is not possible. So the problem starts in diameter 4. Okay. In diameter 4 case, so if you have a diametrical path of length 4, let's say V1, V2 up to V5. Okay. So we can draw that. Okay. So let this be a diametrical path. Okay. So by the previous argument, either if V2 or V4, if they are incident with or if they are adjacent to some pendant vertices other than V5 and V1, then your determinant will be equal to 0. So those cases we are already done. The only possibility here is you may have some pendant or some pendant vertices like this here, or you may have some paths of length 2 here. Since the diameter is equal to 4, you can't extend this path further. Okay. So these are all the other cases. Okay. So suppose V3, the center vertex V3, if it is adjacent to one pennant vertex, okay, let's say W, okay, then you look at the vertices for which the eccentricity are attained. Okay. So look at the vertices V3 and W. Okay. For both the vertices, the list of all vertices which are attaining their eccentricity, okay, at V3 and W, both are the same. Okay. That means that the row corresponding to V3 and the row corresponding to W, one is the linear multiple of other one. Okay. So in that case also, we are done. Okay. So the moment you have a pendant vertex which is incident with the V3, we are done. Okay. The other possibilities are like you may have some paths like this. Okay. So in this case also, suppose, yeah. So just here for the sake of the completion, I'm writing P pennant vertices. Even if one pennant vertex is there, then you will get singular matrix. Okay. So in this case, suppose you don't have any vertex of any pennant vertex which is which is adjacent to V3. Okay. So in this case, just look at the rows corresponding to these vertices. Let me call this as W1, W2 up to WP. Okay. So you look at the rows corresponding to these vertices. Okay. You take the sum of all these sum of the rows corresponding to all these vertices. That will be a linear multiple of this row corresponding to V2. Okay. So these are all the only possibilities for diameter 4 case. Only diameter 4 case is difficult. Diameter 5 cases is sort of really simple. Okay. So these are all the only possible structures on trees on diameter 4. Okay. So we are argued for all the cases. Okay. For diameter 5, so you fix a diametrical path. Okay. So now you look at the draw this. So just the 3 vertices let us look at. Okay. So if you have a vertex which is sitting in this graph, okay, which has distance, let's say k to this vertex. Okay. So this is V1, V2, V3. Okay. If there is a vertex U somewhere sitting over here, its distance from U to V3 is k, then for sure the distance between U and V2 should be k plus 1, and distance from U to V1 should be k plus 2. Okay. So this is a small observation. Using this, we can show that so these vertices V2 and V3, okay, they cannot be eccentricity vertices for any of the vertices. Further, the eccentricity vertices of V2 and V3 are the same. So what are all the vertices for which V2 and V3 are attaining their eccentricity? Okay, so those vertices should be the same vertices. Okay, so that will show that that rows corresponding to V2 and V3, they will be linear multiple of each other. Hence, for diameter, if diameter is greater than or equal to 5, So in this case, we can really complete this proof with only these two vertices. Okay. So in all these cases, we are getting similar. Okay. So hence what's the result? Just I will show you the result. So determinant of so eccentricity matrix of a tree is invertible if and only if it is either a path on 4 vertices or star graph on n vertices. Okay. Okay. So we lost the invertibility. So what else we can expect in this case? Okay. So I think most of you may know the notion of inertia. So if you have a symmetric matrix, by inertia we mean just count the number of positive eigenvalues and count the number of negative eigenvalues and count the multiplicity of the eigenvalues 0. So n plus multiplicity of number of positive eigenvalues, n minus number of negative eigenvalues, maybe n0 multiplicity of the eigenvalues 0. This is called inertia. Okay. So for the invertible matrices, so this part will be 0. Rest of them will be distributed over here. Okay. And for distance matrices of trees, you have something, I think it has exactly one positive eigenvalue and n minus one negative eigenvalues. Okay. So here we are able to show that. So even though this eccentricity matrix is not invertible, it has some nice inertia behaves very nicely with respect to eccentricity matrices. Okay. What do you mean by that? Okay. So you take a tree on n vertices where n greater than or equal to 4. Okay, it's a odd diameter. Okay, diameter is of the form 2d plus 1. Then, irrespective of the structure of the tree, the rank of the eccentricity matrix is equal to 4. Okay, so whatever tree you take, if it has odd diameter, irrespective of the number of vertices, the rank should be equal to 4. Okay, and moreover, so from where this 4 we are getting, okay, that we are able to get a commutative expression. So it should have exactly 2 positive eigenvalues, 2 negative eigenvalues, and rest of them are equal to 0. Because the inertia is 2 plus 2 comma 2 comma n minus 1.
Can you recall the definition of eccentricity matrix?
Yes. So you know the distance. Okay. So you have the notion of distance matrix.
Yes.
Okay. So you just
wherever there is a maximum, you in the row or in the column.
Yes.
That is you keep it.
You keep it. Yeah.
Then you make it a 0.
0.
Okay.
Yes. That's
Why the purpose of that? What is the purpose of eccentricity? What would use it for?
So I'm not really sure about applications, but there are some papers which consider about application. It has some in chemical graph, but I don't know anything about it. So for me, it looks like interesting. That's really studying it. Okay, the proof. Okay, so what about the even case? Okay, even case is much more complicated and it's more interesting also. Okay, so to study about even case, we need one more definition called diametrical path. Okay, so a path in a graph is said to be diametrical path if the length of the path should be equal to diameter of the graph. Okay, that's called the diametrical path. Okay, so let's take a path with let's take a tree with even diameter. Okay, so if it is a even diameter, then you can find a center. Let U not be its center. Okay, so draw a picture. So you have a tree. Okay, just let me focus on one path. Okay, starts at let's say U1 and so on. U0 is center. Some UN. Okay, so it is the center is adjacent to many vertices. Okay? Look at all those vertices. Okay. So we are going to say a vertex which is adjacent to U0 as diametrically distinguished. Okay, okay, it's said to be a diametrically distinguished if that vertex should sit in a diametrical path. Okay, so you may have many paths which passes through this center. Okay, so if there is if you have this vertex here, okay, this vertex if it is sitting in a path which passes through U0 and it is also a diametrical path, then we call this vertex as a diametrically distinguished vertex. Okay, so
any one of them, even the next one,
everything. What are all the vertices which are adjacent to this U0? If they are sitting in a diametrical path, we call them diametrically distinguished vertex. Okay, so this number of diametrically distinguished vertices gives the rank. So that's what we shown. It's a lengthy statement, but basically, like what I said, whatever is in the content of the theorem. So you just count the number of diametrically distinguished vertices. Okay, that will give you the number of positive eigenvalues, and indeed it is same as the number of negative eigenvalues also. Okay, we can show that. So the inertia, in other words, number of diametrically distinguished vertices. Okay, comma, say the number of diametrically distinguished vertices, comma the rest of the objects n minus 2. Okay. So the proof of the even case is a little complicated. Okay, just to the odd case, I will try to give a sketch of the proof. So you start with a tree on n greater than or equal to 4 vertices, because up to n equal to 4, everything is invertible. Okay, so you take the diameter to be 2d plus 1. Okay, so in this case, you will get two vertices u0 and v0, which are centers. Just a partition of these vertices will give a neat proof of this statement. Okay, let's take u0 and v0 to the center. Okay, so now let us remove this vertex. Remove this edge. Okay, so your graph will split it into 2 parts. Okay, now we are going to partition the vertex set into 4 parts. Okay, so in this way. So you look at all the vertices which are at the distance d from the vertex u0. Okay, so that is from u0. What are the vertices here which are at a distance of let's say something like this, which are at the distance of d. Okay, so you call all those vertices, or you collect every such vertices in d1. Okay, so do the same thing for the other side. What are the vertices which are at distance d from the vertex v0 here? Okay, so in the other part, so rest of the vertices other than v1, what are the vertices are available here? You put them everything. You call that v3. Do the same thing for the other part. Okay, so for the vertices belonging to the various classes, this v1, v2, v3, v4, we can compute the eccentricity. Okay, it's very simple. Okay, you can just by looking at it, you can say like if I take a vertex from here. Okay, let's say I'm taking a vertex in v3. Okay, if I take a vertex in v1. Okay, between these two vertices. Okay, none of them will attain the eccentricity. Means any vertex of v3 will not attain its eccentricity in v1, because distance from v3 to v1 is smaller compared to distance from v3 to v2. Okay, so every vertex sitting here v3 will attain its eccentricity in v2. Okay, so likewise you do all possible combinations. So these are the possible entries of the eccentricity matrix. Okay, so this gives us a nice form of the matrix. Okay, so the eccentricity matrix can be written in this nice block matrix form. Okay, so so this is a 4 by 4 block matrix. Okay, so the number of rows here is the number of elements in v1. Okay, so this is a nice form. So now we can use our matrix theory to compute the rank and other things. Okay, so here all the rows of the matrix P are identical. Okay, here J stands for the matrix whose all entries are equal to 1. Okay, so corresponding to this block you will get a rank 1 matrix. Corresponding to this block you will get a rank 1 matrix. And corresponding to this block you will get a rank 1 matrix. So total you will get the 4 rank 1 blocks. Okay, so altogether you may lose something also. Okay, so that's why we have written here the rank of this part will be at most 4. Okay, so just I have given the details. I said verbally what are all the things written here. Okay, so each block is having rank 4. Okay, so altogether they may lose some rank, but we can show that it will not lose the rank. Okay, just there are two approaches. One is you just take a principal submatrix of this matrix. Okay, if I can produce a principal submatrix which is having rank equal to 4, then I'm done. This matrix should have rank 4. Otherwise, you can go for equitable partition algebra. Okay, so in this case, both are basically same. So this is a 4 by 4 principal submatrix. Okay, its rank is equal to 4. In fact, one can explicitly compute the eigenvalues. Okay, by characteristic polynomial. Okay, and by looking at this expression, you can say 2 of them are positive, 2 of them are negative. So hence it has 2 positive eigenvalues and 2 negative eigenvalues. Rest of them are equal to 0. So in case of odd diameter, the rank of your eccentricity matrix is always equal to 4. Okay, and in case of even, it depends on the number of diametrically distinguished. If you have L diametrically distinguished vertices, then rank is 2L. Number of positive eigenvalues is L, number of negative eigenvalues is L. Okay. So the next thing is spectral symmetry. Okay. So So we have seen that if you have a bipartite graph, then its spectrum is symmetric with respect to origin. So this need not be true for eccentricity matrices. Okay. Even for trees, we have an example to show that the spectral symmetry need not hold. Okay. So, but one can show that in case of trees, if you have a tree with odd diameter, then the eccentricity matrix will have spectrum which is symmetric with respect to origin. And in fact, the converse is also true. If you have a if the spectrum is symmetric with respect to origin, then the tree should be a tree with odd diameter. Okay. So yeah, so the first result I stated, like if it is a tree with odd diameter, then the spectrum is symmetric with respect to origin. The second result is if it is having odd diameter, even diameter, then the spectrum will never be symmetric with respect to origin. Okay, by comparing these two, one can conclude that the eigenvalues of trees are symmetric with respect to origin, if and only if the tree should have odd diameter. Okay, so it's an interesting problem to consider for which type of graphs you will have the spectral symmetry. Even for bipartite graphs, we don't know the answer. If you have bipartite graph with the spectral symmetry, if it has spectral symmetry, what sort of structure it should have? Yeah, for the odd diameter case, again the similar type of partition. Okay, just you have to swap the role of VIs. Okay, so just for the odd case, I'm going to give a proof. Okay, so for so let us fix U0 and V0 be the same center edge. Okay, and you partition, just change the name of the partition. Okay, so you take V1 is this one, V2 is here, and V3, yeah, V3 or U3. Okay, U3 is set of all vertices which are attaining the eccentricity for or distance d from V0. Okay, here you take V. Okay, so now you just partition the eccentricity matrix into 2 by 2 block. Okay, such that the first two blocks. Okay, so first two blocks corresponding to the vertex partition U1, U2. Okay, next two are for U3 and U. Okay, so if you take any two vertices from U1 and U2, or here I written V1 and V2. Okay, so none of the vertices of V1 will attain its eccentricity at none of the vertices of V2, and vice versa. So if I take any two entries from V1 and V2, okay, the eccentricity, the entry of the eccentricity matrix corresponding to those vertices should be equal to 0. So in other words, this entire block will be equal to 0. Okay. So similarly, if I take V3 and V4, if I take V3 and V4, so here again, if I take any two vertices from V3 and V4, okay, so none of them will attain their eccentricity in either in V4 or in V3. It's not possible. So here again, I will get 0. So all the non-zero entries are sitting over here, something like A transpose. Okay. So if you have a matrix of this form, then you know that the spectrum should be symmetric with respect to origin. Okay. Yeah. So for even case, I'm not going to give a proof. Okay. So this is all I want to say. Okay.
Any question? I put something in the chat.
Oh, Professor Ajit. Okay. No, Professor Ajit.
Just a second.
Very good talk. And I put two questions. Okay.
Thank you, madam.
Before listening or after listening?
Do you want me to read them?
Yes.
Okay, you see, there is concept of invexity, B invexity due to CR Vector in Canada and RN Call in Delhi and his school, Surjit Suneja, CS Lalita, and many other people took variants of convexity. So
Okay.
maybe since you are considering star convexity, those notions of convexity can also be considered. Have I made my point?
Okay, ma'am. I'll see that. Yeah.
Okay. Now another thing is, you see that edge coloring problems are there, or chromatic number of a graph. So do you relate anything to chromatic number?
No. So, as of now, we didn't relate anything related to coloring or coloring. Yeah, we didn't relate anything.
Because you wrote, the moment you wrote Kn, the whole graph, then I thought of chromatic number. Because for Kn, you need know the exact number of colors needed. Similarly, for a hexagon, only 3 colors are needed. And if you want 7 points, then you can join to the center, and then less colors are needed. So that way, I would like to know if you can relate it to chromatic number of the graph.
Okay.
Okay, thank you, and all the best.
Thank you.
Thank you.
For the eccentricity matrix, if you consider again a graph whose adjacency matrix is that eccentric matrix, I hope that is called the eccentric graph.
Can you repeat?
So the eccentricity matrix, that must be a adjacency matrix, weighted adjacency matrix of some graph.
Yeah, that one possible to.
Yeah. So is there any work toward that?
No. It's not it. The notion is, you can see that it was considered. In 2018 only this notion was considered, and the proper spectral theory for this matrices was started developed in 2018. The second. So this is the paper it was defined. So that is a valid question. So I think one should look into the direction. We can consider this as a weighted adjacency matrix, and then can you do something? Yeah.
Another thing, like from distance matrix, this matrix is actually obtained, like in sort of like some way. So whether there is like this problem that lambda and minus lambda eigenvalues, the symmetric property, whether that is there in the distance matrix or
distance matrix is need not be right. Even for trees, you have, I think for the star graph you have exactly, or for all distance eigenvalues, it has matrices. It has exactly one positive eigenvalues. The rest of them are negative.
Okay.
So trees don't have that. For distance matrices, we don't have the property.
So as is it called, like anti-adjacency, that is.
So anti-adjacency I told, because in adjacency matrix also one can obtain from the distance matrix by keeping only the minimums in the rows and columns. Okay. So here we are going to consider the maximum. So that's the reason people call that as anti-adjacency.
There are no more questions. Thanks a lot for a nice talk.
Thank you, Professor. To express our gratitude, I request Professor Raghavan to honor Professor Kandu.
Our next speaker
is Professor T.S.R.K. Rao, Adjunct Professor Mahe and Shivanadar University. The title of his talk is From Proximinimality Properties Under Finite Dimensional Perturbations. His research interests are in geometry of Banach spaces, vector measures, tensor product cut spaces. He has published more than 100 research papers in these areas in national and international journals. He has been a member of on the editorial boards of Proceedings of the Indian Academy of Sciences, Mathematical Sciences, Indian Journal of Pure and Applied Mathematics, Springer ISI series, Operators and Matrices, Honors Fellow, National Academy of Sciences. He's a Fellow of Indian Academy of Sciences, Fulbright Nehru Academic and Professional Excellence Fellowship 2015-16, Fulbright Nehru Senior Research Fellowship 2011-12, Senior Research Fellowship of the Institute of Advanced Studies, University of Bologna, Indo-EEC postdoctoral fellowship 1991. And without taking more time.
Sorry. I'm not here.
Sir, more important.
Okay, so thank you very much for the kind introduction. And also thanks to Manjunath Prasad and his entire team for these excellent arrangements and the conference they have organized. Wonderful hospitality. As some of you know, I have been with this CERAMS from its inception in 2018. I was at the inaugural function of this special center that the university has established. And it's wonderful for me to see that the center has grown and has a tremendous amount of activity, particularly in winter time. They have several programs and conferences they have organized. And at a personal level, for me, it's very satisfying because I was in the interview committee which selected Manjunath Prasad for his PhD at ISI. So he did his PhD there, and now he is here, inviting all of us to interact in these things. And also at my personal level, I must say that 40 years ago, Professor Raghavan walked into my office when I was a young research scholar and asked me to state the best theorem that you have proved so far. Luckily for me, I had proved some theorems by then, so I could state it and show it to him. So this is how the ISI roots spread. So today I'm going to talk about what is called the best approximations or proximity properties. And these are generally considered, I consider them only for closed subspaces. So you take a Banach space, let us say real Banach space if you don't find complex ones so far. And Y is a closed subspace, and you consider any vector in X, and then consider the distance from X to Y. That is, by definition, infimum of Y belonging to Y of a length of the vector X minus Y. So this distance, since Y I am picked as a subspace of the Banach space X, this distance is actually the quotient now. That's why I'm interested in studying this distance function. And by definition, then you have sequences Yn in K, Y such that distance between X and Y is simply limit of norm of X minus Yn. And any such sequence is called a minimizing sequence for the vector X. So let me note for future reference that the minimizing sequence is actually always a bounded sequence. And if this sequence, for example, is just a constant for some Y0 belongs to Y, then you can clearly see that the distance from X to Y is equal to norm of X minus Y0, because this is a constant sequence. And such a Y0 is called a best approximation from Y to the vector X. So briefly called best approximation. So you can look at the set of all best approximations. P of X is equal to all Y in Y. Say that the distance from X to Y is equal to norm of X minus Y. That's called the set of best approximation. It's not clear in the infinite dimensions why such a best approximation should always exist. But when it is non-empty, you denote it by P of X. And if it is non-empty for all X not in Y, well, for X in Y, 0 is clearly a best approximation. So you would say that Y is a proximal subspace of the space X. So it's a relative notion. So for example, recall the case of Hilbert space that most of you are familiar with. If you take a closed subsequence Y contained in X, and if you take a minimizing sequence, one of the first things you learn in Hilbert space theory is that such a sequence is automatically a Cauchy sequence, and it converges actually to a unique best approximation from X to the point Y. So my comment about a minimizing sequence being bounded easily gives, in general, that if you have a finite dimensional subspace, yeah, so not necessarily in Hilbert space. In Hilbert spaces, we said every vector has actually a unique best approximation by the properties of the inner product. So now if you have a general finite dimensional subspace F contained in X, Then you look at distance from X to F. And I said, of course, take any minimizing sequence, where Fn is a sequence in Y. But I just now said that the minimizing sequence is always a bounded sequence. So this Fn is a bounded sequence in F. F is a finite dimensional space. So you know that there is a subsequence Fnk such that Fnk converges to a finite dimensional subspaces or automatically closed subspaces. So it converges to a point F0 belonging to F. And the distance function is a continuous function. So distance between X and F is actually equal to norm of X minus F. So that any finite dimensional subspace is always a proximal. So since I have a lot of younger audience, this here is something very interesting. If you work in an abstract space, let's say a Banach space, and of course, I prove a lot of theorems saying that let Y contained in X be a closed subspace, something. But you ask me, what is it? What are closed subspaces? I have to pause and say, oh, take independent vectors, n many of them, take the vector space spanned by that, that's a finite dimensional space, and show you that any finite dimensional space is always closed. So finite dimensional space are simplest examples of closed subspaces in a Banach space. If you are in an abstract situation, you have no control about what are closed subspaces. So you would say finite dimensional spaces. Then, all right, is this anything else you could do? You can do something more. So if you start with a Banach space X, there is this nice space, thanks to Banach theorem, called X star, the space of all continuous linear functionals on X. And if X is a Banach space, for example, X star is also a Banach space. So I can take a finite dimensional subspace here. Then I can look at the space Y, if is equal to kernel of F, where F belonging to F, and take the intersection. So you look at the intersections of kernels of F and F belong to F. F is a continuous functional, so kernel of F is a closed subspace. So Y is an intersection of closed sets, Y is a closed. So in general, a closed subspace, Y is called a closed subspace of finite codimension. So finite codimensional subspaces and finite subspaces are the immediate closed subspaces you can produce if you are in an abstract space. Other than that, in a concrete space, of course, you can write down several descriptions. But if you are in abstract, this is one. So most people are interested in how are these things, finite dimensional spaces and finite four-dimensional subspaces are situated in a Banach space because they are the natural objects that you could produce. So since, well, of course, in general, I have just now written down the proof. If Y is finite dimensional, this is always a proximal subspace. So that, of course, if X is finite dimensional, every subspace is proximal. But in general, if we have an infinite dimensional Banach space, a subspace, closed subspace need not have best approximations. We will see examples of this in a while. So in this talk, I want to consider two variations on this best approximation scale and see how they can be used to determine structures of various spaces. And in this example, I'm going to illustrate with you to determine the structure of a C star algebra. It's always interesting to know, look at objects which have an additional structure and then decide that they are really simply determined by something about their geometry than this additional structure that is so useful there. So here is one variation of this definition. This is called strong proximality. So you start with a proximal subspace, and I would say it is a strongly proximal subspace if every minimizing sequence, there is a subsequence and a sequence of best approximations so that the difference goes to 0. So in the case of Hilbert spaces, for example, we saw that minimizing sequence itself goes to 1 point, and it has, that is the point of best approximation. So instead, I'm asking the variation where whenever I have a minimizing sequence, maybe I can take a sequence of best approximations, maybe not for the entire thing, for a subsequence, so that the difference would actually go to 0. But I remember that my thing is already proximal. So I wanted to say every minimizing sequence, well, may not have a subsequence or anything, but will have a sequence of best approximations which are close to it.
Now this other thing is called approximatively compact. So a subspace Y is said to be approximatively compact if every minimizing sequence has a convergent subsequence. And of course, by continuity of the distance function, the limit of that subsequence is automatically a distance. So this is a better thing. You actually have a subspace. Whereas here I am saying there is a subsequence which is close to a sequence of best approximations. But here I am asking that every minimizing sequence has a subsequence which converges. So as you can easily see, that 2 is a stronger statement and 2 automatically implies 1. And of course, subspaces of Hilbert spaces satisfy any of these properties. So clearly, finite dimension spaces, you can again see proximality I have shown, but the same proof is really, I have actually proved that there is a subsequence which converges to a best approximation. So I have proved that it is approximatively compact, and this is a stronger notion, so it's automatically strongly proximal. For example, if you look at all continuous functions in 0, 1, such that f of 0 is equal to 0. It can be it can be shown that J is strongly proximal. But not approximately. So in the infinite dimensions, there are situations where you can have one of the things but not the others. And for example, this example I wrote down, it's a simple exercise to see that it's always a proximal subspace. But one can also show that it's a strongly proximal subspace, and it requires a little more work to show that it's not actually approximatively compact. So let's look at more examples in the infinite dimensions. You look at compact operators for 1 less than p less than infinity in on LP, then again it satisfies the strong proximality, but it does not satisfy the approximatively compactness. So for p is equal to 2, of course, it is the Hilbert space situation. So this is K of L2 inside L of L2. So well, of course, it is well known in operator theory that K of L2 is actually a proximal subspace of L of L2. And more generally, if you take A to be a C-star algebra, one of the first things you learn in Arvison's book is that if you take a J contained in A, which is a closed two-sided ideal, then J is automatically a proximal subspace. So this idea of compact operators being a proximal subspace of bounded operators has been extended. One knows that if you take any discrete LP space for 1 less than p less than infinity, compact operators on LP again is actually a strongly proximal subspace of bounded operators. And one can show it again that it's not going to be approximatively compact. But unlike the case p is equal to 2, which is the Hilbert space case that I wrote down, P.K. Lin and Yao Sternfeld have shown that compact operators on LP of 0, 1 for 1 less than p less than infinity, p not equal to 2, is not a proximal subspace. There is always a operator on LP spaces, which does not have a best approximation, compact best approximation. As I just now said, in a C-star algebra, any closed two-sided ideal, one can show that is proximal, and in fact, strongly proximal, but which very rarely approximately. So now let's consider a general infinite dimensional Banach space, because we saw that in finite dimensional space, everything behaves nice. So take an infinite dimensional space. X star denotes the Banach space of all continuous linear functional. So you take a unit vector in continuous linear functional and let J be equal to kernel of X. It's not hard to show, this is the example that I give you, that J is a proximal subspace if and only if the linear functional attains its norm. So now we are in an infinite dimensional situation. We have a continuous linear functional. There is no guarantee why would the continuous linear functional attain its norm. But the fact that the kernel is really a best approximation, has best approximations for all vectors, is equivalent to saying that the continuous linear function actually attains its norm. So then you could ask, of course, we have merely shifted the problem. All right, you gave me an example to say that continuous functionals attain its norm, then it's a proximal subspace. But where are such things? So this is the basic Kahn-Banach theorem that you learned is this. Given any non-zero vector x in X, there is a linear functional x star belonging to x star, in fact, of norm 1, such that x star at x is equal to norm. In other words, norm of x over x star is 1. X star attains it. So that is the basic Kahn-Banach theorem. Kahn-Banach theorem always guarantees that there are continuous linear functionals whose kernel is a proximal subspace of codimension 1. So, and then of course it took a quite long time, and finally Bob Phelps and Aaron Bishop, probably 60s. Proved that the set of all continuous linear functionals is dense in X. Not only Kahn-Banach theorem you can use to produce such examples, but such examples are plenty. Actually, any continuous linear functional can be in the norm written as a limit of a sequence of linear functionals which would attain its norm. This is the famous Bishop-Phelps theorem, guarantees you that there are plenty.
Is this result true for norm space?
So the next level of thing is
this result true for norm space? This
which one? Bishop-Phelps?
no, this last result you did. J is proximal fundamental.
No, that is which has nothing to do. This is very simple. For example, one way is quite easy to see. Let us say that the norm is attained. And the norm x is equal to 1. Suppose that the norm. So now look at the kernel of x star. Then, so let's say x2. Then kernel of x star plus the span of x naught is really the whole space x. So to look at the best approximation, I merely enough to see if from x naught, what is the best approximation to kernel of x star. Because this is a subspace. So looking at a distance with a translate is absorbs it. So I merely have to look at this portion. And that's a scalar. So I can forget the scalar and look at x naught. But this is simply equal to norm of x naught. Or 1. This is quite, because if you look at the norm of x naught minus y, for y belonging to kernel of x star, by the defining property of the linear functional, this is bigger than or equal to absolute value of x star of x naught minus x star of y by linearity. But y is in the kernel, so that vanishes. No. So this is quite easy, not hard to say that a linear function would attain its norm if and only if its kernel is a proximal subspace. So now we take this giant leap from the theorem of Bishop and Phelps, which said that such things always find a dense subspace. So this is the celebrated theorem of James. Suppose this thing is entire x star. That means for each x star, it attains its norm. So what can you say about the Banach space? And this theorem of James says that if you know that all linear functionals attain its norm, this would be in fact, first of all, his theorem of course says implies what is called a reflexive Banach space. So I will not define formally what it means, but LP spaces. So basic theorem of James can be interpreted as saying that if every hyperplane is a proximal subspace, then the Banach space has to be a reflexive Banach space. Hyperplane is kernel of a continuous linear function. So if a very closed hyperplane is a proximal subspace, then the space is there. So here is something nice that happens. Now, once you have a reflexive subspace, and let us take any y contained in X closed subspace. And let us look at from distance from X to Y, which again our minimizing sequence procedure will tell us that this is now X minus Yn. And of course, I said Yn is a bounded sequence. Let's assume that norm Yn is less than or equal to 1. But now if you have a reflexive Banach space, and if you take a bounded sequence, it always has a subsequence which converges, but weakly. It cannot, of course, converge in norm, then it would become finite dimensional. That is what Green's theorem tells us. So you must have a subsequence, but the subsequence now could only converge in the weak topology too. Why not? And why not would automatically be y. A closed subspace is automatically weak. So why not would naturally come from y. So we want to show that this is the best approximation and go back and look at the proof. In the norm case, I said, of course, continuity of the norm will tell you that this distance between x and y is the actually limit of that sequence yn. But now I look at the proof and say that I don't need the norm continuity. I need the fact that norm is lower semi-continuous with respect to the weak topology. That's what you use. Norm is, this is the observation, lower semi-continuous in weak topology. This would automatically mean that distance from x to y is. So to get that convergence, you don't really need the strength of the norm thing, but you really need one inequality, because you anyway, distance from x to y is always less than or equal to norm of x minus y naught. So you need the inequality that norm of x minus y naught is less than or equal to distance from x to y. And that inequality actually uses only the lower semi-continuity when particularly the convergence is with respect to the weak topology. So that would automatically say that if every hyperplane is proximal implies every closed subspace. So James's theorem, strength of the James's theorem is that if you have the information on just kernels of linear functionals, then you have information on all closed subspaces. All closed subspaces are automatically proximal. So one way of interpretation is that from the hyperplane situation, you have the situation for all closed subspaces.
No, if you take the convex hull of the sequence of Yn.
I'm sorry?
If you take the convex hull of the sequence Yn.
Why not would actually belong to that? So here, for example,
No,
I
that will belong
really
to that.
don't need the subspace.
Then I don't need the, why, if you have convexity.
Right.
The weak convergence and the strong convergence will be same.
Coincide, right?
Yes.
So in other words, you have in fact recovered the old geometric version of the old theorem. That is, if K is a weakly compact convex set, that's what I have used here.
Yes.
Then if you look at distance from X to K, this is X. That's all we needed. But we actually gives you this. That's what also happens in the case of Hilbert spaces. You actually prove that any closed convex, if you remember your book, the theorem would state that any closed convex set, the distance is attained. And you needed, of course, closedness to say that as he was pointing, be closed same as non-closed. So that is. All right. So that is really this part of it is more generally than subspace. So, but here let me stick to subspaces. So this is what is reflexive means. So when X is canonically embedded in its bidual, I will not define this. That means it's an odd thing. So equivalently, X is reflexive if and only if a very closed hyperplane is proximal. So that in spaces like L1, L infinity, and C0, you have always non-proximal subspace. These are good examples of non-reflexive Markov spaces. So let us note that X is reflexive, then any closed subspace. This is what I have written down just now. Using the B compactness of the closed balls, the lower semi-continuity of the norm function would automatically give you that any closed subspace, more generally, any convex and non-closed subspace is automatically a proximal set. So via the James theorem, then I have this nice conclusion that if every closed hyperplane is proximal, then every closed surface is proximal. So here is I think I'll just take a few minutes since again I want to get the attention of my younger audience. So you take a finite dimensional space Rn. And you take k many vectors x1, x2, xk. So I'll stick to my notation. Let us out kernel of xi. That's a hyperplane. And look at intersection. J. So if J is non-zero, then the elements of J are the solutions for a system of homogeneous solution. When J is non-zero, they are non-zero, non-trivial, non-zero vector. Here is the solution system. And in the finite dimensional space, we prove that any subspace is proximal. So what it says is that given any vector x in Rk, there is actually a solution to a system of equations which is closer to the subspace of the system of homogeneous equations. So the natural question here is that you could also ask it for any general x. Look at now x star. Of course, I have to take continuous linear functions, so I have to go to the dual space, and I take an x star. Let's say x star. Then I look at the solution space, kernel of x star. Then I already know that it need not be a proximal subspace. There need not be a best approximation. In other words, given x in x, it is not clear if I can actually get a best approximation which vanishes at the point y, x1 star at y is equal. If you take two things, and now look at kernel of x1 star intersect with kernel of x2 star, and x is infinite dimensional, then you already see that the intersection will always be non-trivial because I have taken an infinite dimensional space. And it's again.
I don't get the last sentence.
So since it is x is infinite dimensional, the intersection is always non-trivial now. Because you have x star is infinite. So the intersection is always non-trivial, and it is again not clear whether you could actually get a best approximation for this. Every point of x, can you get a best approximation from this? In not given any point of x, can you get a closest point which satisfies a system of constraints? I have written for 2, can write it for n, like in the homogeneous case that I am illustrating. So this is the same problem we're solving. And here it turned out to be extraordinarily hard problem. So only a decade ago, that is in 2017, this journal of this problem, they proved that there are Banach spaces where there are no proximal subspaces of 4-dimensional 2 at all. No matter what x1 star, x2 star you take, the intersection will always fail to be proximal. So for years, Banach space theorists have struggled with this thing, and finally there appeared this very nice construction, difficult construction, which have exhibited classes of Banach spaces, not just one, a procedure to construct Banach spaces where you could choose 2 points x1, x star. No matter what 2 points you can choose, you cannot solve this constrained approximation. For 1 point you can choose, namely where the functional attains its normal downside. But the minute you take 2 and you want to say simultaneously, let us look at the constraints x1 star of y is equal to 0, x2 star of y is equal to 0 as your linear equation, you can't find such a y which is closest among all of them. So that's it. These are kind of hard. And this will also show that this kind of a questions, proximality in the infinite dimensions, are not quite clear what happens to the intersection. Even if you take 2 things, the intersection, these examples, among other couple, such examples were known much before. If you take 2 things which attain its norm, but the things would always attain. So let us consider the dual, and here the advantage again. So let me, before I go to that, I'll just take 1 more minute to justify my title. So let us take a space X, infinite dimensional space. So I will take finitely many constraints and look at this J is equal. This subspace. Okay. So suppose J is a proximal subspace of X. Let us take any subspace in between J and X. Let us take J is given to be now a proximal subspace of X. So let us take a subspace in between J and X. What can I say about M and J? What would be the immediate relationship between M and J? J is this intersection, and M is J is a finite 4-dimensional. So M is in between J and X. So what would M be? M be simply J translated with a finite dimensional space. Right? From linear analysis, you see that M is nothing but J translated by a finite dimension. Now we have proved that finite dimensional subspaces are proximal. I am taking in my hypothesis that J is a proximal subspace. It's not too hard to show that if you take a proximal subspace and you translate it by a finite dimensional space, J plus F is again proximal. So this is the nice situation. Once you have this J to be proximal, everything in between is proximal. So in particular, this actually means that all these xi stars attain there now. Of course, you can now linearize any convex combination. So J perp, every vector in J perp is your like your Hilbert space orthogonal or X star, which vanish. Okay.
So X itself is proximal.
Sorry, Y itself is.
No, X. J is subset of M,
M contained in X, so J is proximal in X.
Yes.
So in between theorem says that everything in between is proximal.
Everything in between can include X itself.
I mean, X is proximal in itself. That is triviality, right? I mean a proper subspace. So J would come to X. So M is simply a translate by a finite dimension. And this is my, major thing. When can you translate with finite dimension spaces and get nicer structure? It says that here, if you this is simply a translation, and you can not too difficult to show that this is a proximal subspace. So, but the consequence of this is that if I take anything here, this kernel is in between J and X. So this entire thing is in the set of non-attaining. So not only xi star themselves become norm-attaining functionals, but anything which vanishes on J is now a linear combination of these guys and the missing. So this is again a major problem in this theory. In fact, that is the title of this. So set up for norm-attaining functions. If you look at this set, this is a set. If you have one element, you can show that the one-dimensional span is there. But if you have two elements, can you show that the two-dimensional span is there? That was the problem. Will there be a two-dimensional subspace in this set? These problems are called linearization problems. You have sets which on the base apparently have no linear structure on them, but it is just possible that they contain some subspaces. One can show that a subspace here is necessarily finite dimensional. And so this beautiful example, counterexample, which came around 2017 says that there are indeed spaces where there are two-dimensional subspaces in this setup or norm-attaining. So major achievement in Banach space theory at the time. I have 5 minutes. 10.
3:45, right? Over. Right. 5 more minutes.
Yeah, I thought so. So now I'm going to turn around and ask this question in X star. So the weak star compactness argument, like I did here on the board, the weak compactness argument would show that any closed subspace is automatically a proximal subspace. So you don't get anything extra if you ask the same question for weak star topology and X star. But suppose that X is a Banach space, and that every closed hyperplane, of course, that is proximal. So now I want to put it that it is a strongly proximal subspace. Then when can you conclude that every weak star closed subspace is automatically strongly proximal? So this is the analogy with James's theorem. James had it on the Banach space X, and his condition is hyperplanes are strongly proximal. Then conclusion is all closed subspaces are strongly proximal. I have it now on the dual, and I know that weak star closed subspaces are anyway, James's theorem is about proximality. So weak star closed subspaces are anyway automatically proximal. So I ask them to be, when are they strongly proximal, given that you know that each weak star closed hyperplane is strongly proximal. Finally, a weak star closed hyperplane is simply 0 sets of the vectors of X. You take any X in X, then a weak star closed hyperplane is this, and precisely any weak star closed hyperplane is this set of some X belonging to X. So instead of solving this approximation problem in X star, constraints are from X star. Now my constraints come from X, and I wanted to know if I could solve it in such a way that the thing is not just a proximal. Of course, it's always a proximal subspace. So I would like a solution in the strongly proximal subspaces. So I will just I don't know. So I don't know an answer to when do Banach spaces satisfy infinite dimension, because finite dimension mixed topology is same as non-topology. There is nothing else we need to do. So in the infinite dimensions, I do not know when this kind of a hypothesis would automatically imply that everything is strongly proximal. So I'll just show the result here. But I just wanted to say one more minute. So somehow this approximation theory is very related to differentiability of the norm. And there is this notion of a strong subdifferentiability. So these are what are called subdifferentiable limits, like you say in the directional thing, x plus ty minus norm x by t, limit t goes to 0 plus. So take it from the positive side. And so these actually limits can be computed. They're actually given by a specific formula that limit exists because it's a monotone function, and that limit can be computed. And what I would need is really, again, I have actually some paper in the December issue of Journal of Applied Analysis called Computing Subdifferential Limits of Operators. But what I would need for my final theorem is a beautiful result of Jill Godfrey and V. Iwsmga, who used to be at Pondicherry University. They have proved a wonderful result that the kernel of X star, which we know the proximal if and only if it is attains its norm, is strongly proximal if and only if the point X is a point of subdifferentiability of the norm for the space X. So I'll use this and some other structure theorems to finally prove that if so if you have a C-star algebra such that all unit vectors are points of so the main thing I prove is, let me state this here, so that this question that hyperplanes strongly proximal implies all mixed or closed subspaces is solvable in a C-star algebra if and only if the C-star algebra looks like a C0 direct sum of compact operators on Hilbert spaces for a family. So this seems to be a nice structural relationship between what I'm doing and some C-star algebra theory, which would say that this James's n-log question is actually solvable precisely in the class of among C-star algebras, precisely when you have take C0 direct sums spaces of compact operators. Hilbert spaces, if you remember, my KFL2 is one of the examples of subspaces which are strongly proximal. So in this particular case, it actually characterizes all C-star algebras, which classify.
Any questions? There are no questions. Thank you.
This relation, if J is proximal, if you take any subspace in between J and X, then that M is also proximal, right? Here in the board here.
Yeah. Say it again.
If J is proximal, and if you take any subspace containing J, then that will be also
finite code.
Cofinite, okay.
See, this is my entire crux. If when you do this finite codimension, M is really a translate of J. So you just want to say that whatever property you are pushing is pushed under translations by finite dimensional spaces, then you have this in between here for any property.
Okay. For strongly proximal, it's true.
Sorry?
For strong proximality.
Also
it is true. For approximately compact?
Sorry?
For approximately compact.
Everything.
Okay.
So this is the reason why I made this as my base, because I know that several of the proximality properties in this hierarchy, when you simply translate them by a finite dimensional property, they remain to be so. So it seems to be interesting to know what are the finite codimensional subspaces which would have this property, because then everything in between. So there are some opens, lots of opens in this area. Very recently only this area has opened up. Thank you.
So what next? To go for the tea? Okay.
Thank you, Professor. I request Professor Raghavan to honor Professor TSSR Kera.
Nice color.
We shall have a tea break and next session will start at 4:30.
You know, that's on my end, I thought like my voice is not too. Oh, and
You did not mail, no?
No.
Okay.
Last year I You give brand new beginning for this possible. Yes. So the. Nobody is good. Yeah. No. The next I would recommend.
You don't have.
They can go for a postcard. You were right, locally also.
Copy of it. I have.
More to get them so the promoter. No.
2 more weeks in. Only travel.
I like this topic. Oh, thank you. Interesting. This was interacted. We never met in person. Supposed to come to speaking with you. Yeah, last moment I told you. Yeah. Kristen told maybe in summer we can have something. Can have sure. You interest? Yeah. With Kristen I can come anytime. Yeah, very good. Means I have proposed for a linear algebra. Okay. Because in same time we were thinking of one school in big Hyderabad. When Kristen told you are interested, then we are planning to postpone that to December. So that it will not no interest. Overlapping. Then we will find.
That's next week only.
Yeah.
All the people. Who are the people?
Dave and David. Viswajit Dev.
Yes.
This is not good.
Oh, I see.
Just ask him if he wants to go to.
Great. Yes. Okay, thank you.
You can't take bottle.
What can I take orders?
No,
Oh,
that star may not be able to carry.
Huh?
Yeah, you want to carry that bottle, sir?
You're just on my way.
Yes, sir. I'll give you a plastic bottle. But this is university, sir. They're not allowing us to carry that.
Oh, wonderful. This is good rules. I see, I see. You'll throw that water away because I was
No,
thinking.
it is.
Yeah, I see.
That's a glass bottle, no, sir. They refill it and then reuse it. That's
Oh,
the
I see.
idea.
Oh, recycling.
The idea is
Good.
not to use the plastic. I will be sitting here until the car comes, sir.
You throw the water away, I'll keep it. I throw it?
Yes.
Okay.
Did you do?
Okay, that's fine.
You want
I will finish it. That's okay.
No, it's not thrown, sir. It's just like it says. Did you?
No, I
Yeah,
didn't.
give it to him. I would like to.
I thought I'll finish it.
Yes, sir. So please.
Okay, thank you.
Yeah.
So tell me about you. Come on, sit down. What about you? Tell me, we just see you in. Tell me about you.
I'm Megha. I'm doing my master's from Manipal University here. Like I'm like a volunteer.
Yeah. So are you doing master's in
My master's in data science.
data science?
Yes.
That will be useful for the future.
Yes.
Yes. I think that this is the time that people should do things which are important.
Yes, sir.
Yeah, some people do something which is just easy to do it, but not to do it. Okay. Yeah. Data science is like a computer science.
Yes, sir. Like,
So, but then how do you come here then, to a different department?
it's a no Department of Data Science only is conducting this, no?
Actually, Professor Prasad is professor of mathematics in data science department.
I didn't know. I thought in mathematics.
He is in department of data science.
So your courses are in what? Tell me, describe your source courses. What it is courses?
Well, sir, it is basically based on statistics.
Statistics, okay.
Yeah, and machine learning. Yes, mathematics is also needed,
Yeah.
but little
Yeah,
bit.
to help, yeah.
Yeah.
Okay, but what about other things like hardware engineering, computer science courses, CS plus Pascal
Yes, sir.
language?
Python we did and R language.
Okay,
Yes, sir. And SQL for database languages, database data languages.
so after passing your degree, you will be eligible to take a job in the companies as as what?
As a data analyst.
Data analyst.
Yeah.
And they carry a good job, in fact, 75,000 rupees a month. At least. Am I right?
Yes, sir.
Good luck. Yeah, that's great. Megha.
Yes, sir.
And you are?
Myself, Uma Shankar.
Uma Shankar.
Yeah.
Listen, Uma Shankar, come here. Since we talk to each other so much, but I did not know you. Oh my, he has been of great help to us in the book we published on mathematics in ancient Jain literature. So he just published and he helped us in getting these papers into type, or even in Sanskrit language, you did that also. Uma Shankar, my God, I should have known you had come first day, I should have met you. Okay, so good to Uma Shankar. You are finishing your PhD or what?
Next year I'll be finished.
Your PhD?
Yes.
In mathematics?
Yeah.
So, I'm so pleased to meet you. We have been in for more than 2-3 years. And you got the ticket from Hilda, but I heard.
Yeah, Hilda.
Hilda. And now you want my boarding pass, I thought you said?
Yeah, Savita madam will contact you regarding.
Yeah, she asked me to give me the boarding pass.
Yeah. She will contact you again for the same.
So I had to look for that because that is the boarding pass which I had from Bengaluru to this place, Mangalore. That's what she wants. Right?
Yes.
That's the only boarding pass I
Yeah.
can.
Yeah, correct.
Fine. So what will you help me? Of course, you are right hand of Mr. Manjunathan. Finishing your PhD. So you will have a future in mathematics only.
Yeah.
Not in computer science.
No.
Okay. Okay. That's okay. We need mathematicians. Also. That's good. How long have you been working?
3 years.
And you have a kind of a grant of some company?
Yeah, I had institution fellowship and I had a project also, sub DSA project.
Okay.
So that was over last December, last year December, 2022 December. After that, I had institutional fellowship. This month, last month, it was over.
So that means you have
Now I don't. Currently, I don't. Currently, I don't.
So why without
My fortunately, my financial condition is okay.
That's all right. That's all right. So this is now December.
Yeah.
You will be graduating in what then?
Next June.
Next
July.
year. Then you can get a job here or not?
I don't know.
You are not.
Yeah.
Anywhere near there. That would be good. Have you published anything so far?
Yes, 5 papers and 1 book chapter.
No, there's been a paper. Where did you publish it? Where did you?
2 papers are in Journal of Algebra and Application.
Yes,
Yeah.
good. I did not know even that also. How many? 2?
3.
Oh, you are in good shape then. You are in good shape. That's a good job. Recently, I don't know why, because I
Yeah,
don't
recently, yeah. One is in 21.
21.
Yeah. Next 2 papers are, yeah, last year.
Do good job. The bottom line is do good job. No superficial, not just now we're talking about Raghavan. They define a forest means which is numerous trees. Term number one. This place has only one tree, so it's not a forest. Term number two. This place has two trees, so it is not forest. Term number three. That means they coin something just like that. You will not understand what you understand. Because this is what they just coin some definition and put superficially without any meaning. There's no relevance of that definition, but just to prove something. That is done more than 50% of that is the and people and who encourages them? This system which wants to publish papers. System is not hurting. Then if you have paper, then and the administrators don't know the value of that. So they look at the number of papers, 3, 4, that we have good. That's it. Don't rush. Try to publish it. Is okay. So nobody does that before a PhD. Look at the good problems and try to hit them even partially. Your name will be there, one of them. Okay. Even partial answer, difficult problem. When you have a sign open. So rather than making up your own definition of this, that, and then doing something, then the product of the sign of the idea. Okay, go to the nature. Yeah, we lost.
Okay, sure. Okay.
My expectation is non-community readers. Non-community readers. I did start words of the water long ago. When C.R. Rao was in the New York Times, C.R. Rao, he was the director. He invited me to give some so that is they're nice in so I these two properties. We are waiting for the call.
Yes, sir.
I am supposed to send my talk, but I don't have an email.
Sir, where is it?
Huh?
Hello.
Where is it?
The paper.
It's in pen drive.
Oh, no, it is. I go home and send it from my laptop.
You want Karen's email?
I
Who,
gave,
sir?
I gave it, sir.
You gave me already?
Yes, sir.
Oh,
I wrote it.
Bandra ಈಗ?
Okay, you gave me more.
Yeah, yeah.
Dropping it.
Not
Drop it.
these other.
Okay, I have it. I will mail it. So car has come?
Okay, okay. In 5 minutes it will come.
Okay, okay, do your work. So I'm glad to meet you. And glad to meet my friend Umashankar.
Yeah, thank
Come on, sit
you.
down.
Same here.
I wonder. I used to be 2 years ago also you taught me. And even recently about a ticket, you did all that job. I think Hilda did a good job with your help.
Yeah, she quickly responded.
She quickly at night, same after 1.5 hours. I saw the reservation made already. We're also helping him for his editorial work in doing. Manjunathan, you help him for that also? He's also helping us in the editorial work.
Yeah, sometimes to find the editors, he asked me to search in the editorial board. So for that, sometimes I have to.
So what's your expression? Usually problem.
Even on competition of generalizing the society. Because of matrix. And then the inverse complementary matrix method was then matrix case. Primary scheme. Some associated. Yeah. That paper was published on the party. Then later was recently introduced.
I was in that paper. Who was it?
Yeah, I think so. I think. Yeah.
Okay.
And later we are on secondary transfer that was recently introduced in secondary transfer. So we worked on that one.
Secondary transpose. What is that?
Usual transpose is along the diagonal rows and columns are. Rows will be columns in the but when this secondary will be around the secondary diagonal, other diagonal. That will be another reason.
What does it look like? Let me see. Oh, I don't know. What does it look like?
Yes.
What do you do? A4A1?
Yeah, the secondary transpose of this matrix will be A4, A4. First row will be A4, A4.
Well, I will think. Give it to you. So you are, so in the your transpose, the row becomes column. First row becomes column.
Yeah.
And what does it become in this case?
In this case, last row will be reversed, but reversed last column will be first row of the.
Last row would be the first column.
Yeah, reversed with the reverse.
Okay, the last row,
Last column.
It started becoming the first column. No. Last row becoming the last column normally, but you making the first column.
Last column will be first
First
row.
column.
First row.
Oh, row. Yeah.
With the
Normally the last row would be the last column.
Yeah, correct.
But you will be making it the first
column with the reverse. I mean, these entries will be reversed.
But you don't reverse the entry in the chart.
Yeah, in transpose we don't.
We don't reverse.
We don't.
Yeah.
In this case, we reverse. Actually,
Why? What is the purpose of doing that?
yeah, actually, A transpose, yes, we represent secondary transpose.
ABCD transpose is, I write it down. ABCD.
Yes, correct.
Okay, and then your A, Yes. Yes.
Yes.
Yes.
That
Would be.
will be equal to
Yes.
dB will be the first row. dB. Reverse
The
the
last
last
column.
column. Yeah.
The
Reverse
last
the-
column. dB.
Yeah, dB. And CA.
And-
Second row will be CA.
Second row will be.
CA.
No, first. The
First row is dB.
no, here comes the second row become the first column. Right? The second row, this become the first column. Is it not?
No.
No, 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 no. This row then become first column, last row. Last row become the first column, not correct. No, no. Yes. So you are telling me the S of that is what? First you tell me what S of that is. So
First
give me the
row
answer.
will be dB.
dB
And CA.
and C. That means dB. Okay, no, it's a B, it's not dB. BD has become icon, just like BD. This way, BD this way, BD, and this AC is this way.
What it
What
is
they call it?
nothing.
What they mean?
If this matrix is A, AS will be B. Suppose B is the matrix.
AS is equal to what?
First I will tell the expression.
Uh-huh.
B A transpose, right? Capital B, capital B. A transpose.
A transpose
into B.
Okay, where
Where
B
B is the matrix with secondary diagonal ones. All other entries zero. Secondary diagonal all entries are ones. Yeah, correct. That is yeah.
Okay, why purpose? What?
That is
Just write a paper or what?
so actually, with reference to this information, we have defined
Push
movement rows involves also.
I see. Oh, I think I want.
Forgotten now.
Go now.
Oh my God.
Sorry, car. Yeah, I know. Yeah. Okay.
It's okay. So he's there.
He's there. Yeah.
Secondary transport for decades and ಯಾಕೆ studying?
ನೀವು
ಇಲ್ಲ ಅವರೇ ಕೇಳಿದ್ರು ಎಂತ ಯಾವ್ದ್ರ ಮೇಲೆ ವರ್ಕ್ ಮಾಡ್ತಾ ಇದ್ರು ಕೇಳಿ
ಹಾಗೆ ನಾನು ಕೂಡ ನನ್ನ ತಲೆ ತಿಂತಾರೆ ನಾನು ಬಿಸಿ ಇತ್ತು ನಾನು ಈಗ ಯಾರು ಹೇಳಲಿಕ್ಕೆ
ಇವರು ನೆಕ್ಸ್ಟ್ ದೇವಿ
Welcome back, everyone. So the next invited talks will be from Professor Biswajit Dev from Sikkim Manipal Institute of Technology, Sikkim, and David Raj Michael from Vellore Institute of Technology, Chennai. May I request Professor Armugam S. to chair this session? Sir, please.
Welcome to this session, where there will be a talk by Professor Biswajit Dev. He is from Sikkim Manipal Institute of Technology, Sikkim. And his areas of interest include spectral graph theory, graph algorithms and geometric algorithms, motion planning program, etc. He has already guided one student and 4 students are working with him. He is also working in chemical graph theory, packing and domination graphs, and signed graphs. So today he will talk about graph products preserving balance and canonical consistency of signed graphs. So welcome.
Thank you, sir, for a nice introduction, and I'm thankful to the organizer, particularly Professor Manjunath, for giving me this opportunity. So I'll be talking on graph products that preserves balance and canonical consistency of sign graphs. This talk is based on work that is done with one of my research scholars, Chitri Chetri. And already some of the works are published. The outline of the talk is we'll discuss preliminaries, and then 2 products we are going to discuss, but basically 2-path sign graphs and D and T-modal sign graphs, and references. So let's go through the preliminaries quickly. So, what is signature on a graph? When you assign weight 1 or -1 to each of the edges, that means it is a function from the edge set to the set of 1, -1. It's called signature, and any graph that is with which if you assign one signature is referred as a sign graph. So we denote it by pair G, sigma. And G is referred as the underlying graph of the sign graph. And as you see, it is simply vertex set. When we say vertex set of the sign graph, it means the vertex set of the graph G. And for any edge E, by sign of the edge means its image from the set 1, -1. Sign of a subgraph we defined in this way. So if we take a subgraph of a sign graph, say this, right. So what is sign of a subgraph? You take a subgraph H of G, and the restriction of this sign of the sign graph sigma to the subgraph H is referred as the signature, and accordingly you get a sign subgraph. And we define a sign of the subgraph itself, and it is actually the product of the sign of the edges that are present in the subgraph H. A sign graph is balanced if every cycle in it has sign +1. So you take a cycle from the graph and take the product of the sign of the edges, and if you find that every cycle has the same sign, that is +1, we call it a balanced sign graph. And the sign graphs as a model to study psychological problem was introduced by Heider in his paper in 1946 probably. But formally it was introduced by Harare in 1953. And after that, lots of research works took place in this area. But the first characterization of this balanced sign graphs was given by Harare itself in his 1956 paper. So a graph, sine graph is balanced if and only if you can partition the vertex set into V1 and V2 such that every negative edge connects a vertex from V1 to a vertex from V2. So I'm referring this because in most of the proofs we have considered this theorem, and basically the partition out of this theorem as a basis of our proof. So we refer such a partition which as a of a balanced sine graph as Harare's partition. Now, what is mark graph? So you, instead of now defining assigning weights from +1 -1 to the edges, if we assign weights to the vertices, such a function is called a marking, and a graph with a marking is called mark graph. And if there is a marking as well as signature to assign to a graph, then that is referred as mark sine graph. By mark of a subgraph, we define it to be the product of the mark of the vertices in that subgraph. Just like sign of a subgraph we have defined. And a mark graph is called consistent if every cycle in it has a mark +1. So it was also introduced by Harare and Cartwright in to model a social problem in 1956 itself. And after that, many characterization is there for mark graphs, I mean consistency of mark graphs as well. So some of them I have listed here. Any mark graph with mark of each vertex to be +1 is consistent, and that is bound to, because if you take it any cycle, so every vertex in that cycle will have +1, so product going to be +1 only. Then any mark graph with mark of each vertex -1 is consistent if and only if the underlying graph is bipartite. So bipartite means every cycle is going to be even. So every number of vertex in any cycle going to be even. So if you take the product, it is going to be consistent. So that's why the other way also you can see, because every vertex is -1. So if the product is +1, then the number of vertices must be even. So it means every cycle has even number of vertices, so the graph must be bipartite. So that comes from there itself. So one quick corollary of this is a mark graph is consistent, then the subgraph induced by its vertices with mark -1 is bipartite. Because if a graph is consistent, then its subgraph is also going to be consistent. Okay, because every cycle in the graph is consistent. So in the subgraph also, if any cycle is there, it should be consistent. So if I consider only the subgraph induced by the vertices which receive -1, that need to be consistent. So that's why it is. So a mark graph is consistent if and only if for any spanning. So these are all actually results of that Bink and Harare 1978 paper. A mark graph is consistent if and only if for any spanning tree T, all fundamental cycles are positive, and all common paths of pairs of fundamental cycles have endpoints with same marking. So if there are two cycles sharing one common path, so the vertices common to them, they should have the same sign. These two vertices should have the same. Suppose these two are fundamental cycles. Now, what is canonical marking? So, given a sine graph, you can actually define one marking on the graph naturally. So, in this way, so you just take a vertex. So, you want to assign sign to the vertex. So, you already have a sign to the edges incident with it. So, you take the product of the sign of the edges, and that sign you assign to the vertex. Okay? So, that gives you a natural marking. We call it a canonical marking. And a graph that is consistent with respect to this canonical marking is referred as canonically consistent marked graphs. Now, I think the idea of the talk is clear. So what we are going to discuss is graph products that preserve these two properties, valence property as well as canonical consistency property. So for that, we started recently. So we have actually worked on two different graph products. We'll come to that later. So all sign cycles are canonically consistent, because if you consider any cycle, whatever signs are there on the edges, if you consider any edge, it will contribute its sign to two of its end vertices in the canonical marking. So when you take the product of the sign of the vertices, actually it is square of the sign of the edges. So that's why it is always going to be consistent. So all sign cycles are canonically consistent. Now we will concentrate on this two-path sign graphs and see when this two-path sign graphs of a graph going to preserve this valence and consistency property. We have identified some classes of graphs, means solve the problem for some classes of graphs, not for all. So what is two-path sign graph? So we can generalize it n-path sign graph, g to the power n. So where we connect means two vertices. So vertex set of that two-path sign graph will be same as g, and two vertices in this gn are adjacent if the distance between the corresponding vertices in the original graph is n. Okay. So two-path sign graph means this n is 2. So this is in the two-path sign graph, we are considering the underlying graph to be g square. That's all. Now, how we are going to assign the sign? There are different way of assigning sign. We are taking it as this. So if you are taking an edge uv in the two-path sign graph, so the edge is due to actually a path between u and v in the original graph. So there are some signs due to the sign function, signature function sigma already in that path. So if all the edges in that path, in each of the path has sign -1, then we assign it to be -1. Okay. Negative means -1, and otherwise we assigned it to be +1. So what I'm saying is that suppose I have two vertices in the original graph, and all edges on the path between them, whatever how many number of paths, it doesn't matter, but every edge has -1. Then in the n-path two-path sign graph, this is two-path sign graph, we will assign -1. Now, if anyone is having +1, then we will assign +1. So this is one sign convention. There are other sign convention also are there in literature. We actually worked on this. So this is one of the examples. So if you consider the two-path sign graph of this, you will get it like that. Say between 4 and 2, if we have one path and all its edges are -1, so between 4 and 2, the corresponding edge herein is -1, like that. For writing the results, we need some notations. These are the notations we are defining. So SBC, let us call the collection of all those graphs that are balanced and canonically consistent. Here CC stands for canonically consistent, and SBC hash means the collection of all those graphs whose two-path sign graph is balanced and canonically consistent, and SB hash means balanced collection of graphs whose two-path sign graph is balanced but not canonically consistent, and so on. So this means the collection of graphs can be divided into these four sets. So our question is, what if I take any graph? If I take any graph, so in which set it will lie? So I take any graph from SBC, means it is balanced and consistent. So what is the status of these two properties in the two-path sign graph? So that's what we investigate. One quick remark: if you take G plus actually means the graph G in which every edge is assigned with +1. So then there is nothing. Actually, every edge is +1, then everything will be +1 only, even the vertices and all. So this is going to be balanced as well as canonically consistent. It's two-path sign graph. So that's why we can see that SBC hash is non-empty. Okay, but okay. If you go to the example that I gave, if you look into this example, given graph is a tree, so there is no cycles, so it is not violating the definition, so it is balanced and canonically consistent. But when you come to the sign graph, two-path sign graph, you can see that it is not balanced. You have a triangle, this triangle 4, 2, 5. Whose weight is 1, 1 and -1, product is -1. So balance is not preserved here. Okay. It means this observation that SBC is non-empty is a good observation. And then again, I have a graph which is not belongs to SBC hash. That is another observation, motivation for us to see the graphs which are going to be inside SBC and which are going to be outside SBC. Yes. So now this quick remark: if you consider this a two-path sign graph of a cycle, you will get either a cycle or a paired disjoint cycle. It is not that easy because not that difficult. You can make it out, because if I consider any cycle, say like this, so two-path sign graph of this will be, because these two vertices are going to be adjacent. Okay, so in this case it is not going to be cycle. But if you consider, I forgot to give that. So 5 vertices, if you consider, these two are adjacent, then this is going to be adjacent, this is going to be adjacent, this is going to be adjacent. Alternate vertices are adjacent, so you are going to get a cycle out of it. So odd cycles will give you odd cycles, one cycle, but even cycles will give you 2 pair of cycles for n greater than equal to 6. For n 4, you will not get, you will get a pair of edges. So if you take say 6 vertices, 3, so these 2 are adjacent, these 2 are adjacent, these 2 are adjacent. So if you consider these 3 vertices, you get a cycle, and the other 3 again giving you a cycle. So when you consider two-path sign graph of a cycle, you will get a cycle or a pair of disjoint cycles. And that's why if you see, if I consider one odd cycle will give me 1 cycle only. Two-path sign graph will be 1 cycle, and that suggests that we will always get a member of this SC hash, means canonically consistent set. We will always get non-empty. We can say it by assigning sign to the edges of a odd cycle suitable. So this is again one motivation, that SC hash is not empty. So some of the graphs may lie in SC hash also. So with this remarks, yes, we have an example that this C2n minus, if you consider, this belongs to SC hash if and only if n is odd. Because it consists of 2 cycles, each with n vertices, n is odd, so every vertex has -1 mark, so the product going to be -1. So it is going to be it is not going to be canonically consistent. No, sorry. It is going to be canonically consistent, but not balanced, because number of edges is number of vertices is odd. So number of edges is odd. So every edge got -1 side. It is not going to be balanced, but canonically consistent, because every cycle is canonically consistent. We have made the remark earlier. Now, for odd n, this if I want to talk about whether this sigma for any sign assignment is going to preserve the both the properties or not, we can say it in this way. Suppose we consider the subgraph induced by its negative edges. So if it has k components of order 3 or more, then this two-path sign graph of this sigma will be in SBC or SBC hash or SC hash, according as this summation ni is even or odd. Because we can count this how many negative edges will be there in the two-path sign graph very easily, and from there we can make it out whether it is going to be in canonically consistent or not, balanced or not. So you can see that this term is already even. So if it becomes even, then even number of negative edges, so it will become positive, right? So and if the sum is odd, then definitely this is odd. So the product number of edges, negative edges will be odd. So product going to be negative. So only thing you have to count how many negative edges you will get in the two-path sign graph. Finally, we have sum up all these results, and this is for even n. So if it is a bit lengthy because we need some notation to be defined. So if n is even, then what is the status of this sigma? Suppose sigma star is the subgraph induced by its negative edges of sigma, and let k be the number of components in E sigma. So definitely it will have some components. So so let k be the number of components in E sigma, which has its size congruent to 0 modulo 4, and TEI and T0I, they are actually number of components in E sigma which are congruent to I modulo 4 with n vertices labeled by even or odd vertices. Then we can say that this E belongs to SBC sigma hash if this k plus T01 plus T03 and k plus T03 plus T1 they are even, and it is in SC hash otherwise. Okay, again this proof can be constructed counting the number of negative edges in the in different cases. Yeah, I'm not skipping the proof. And this is for star graph. When a star graph could be in any of this set. So if T is the number of negative edges in the sign graph sigma, then if it has only one negative edge, then only it can be inside SB has SBC has, means it will preserve both balance and canonical consistency, and it will preserve canonical consistency but not balanceness if because if you consider a star graph, you will always going to get a triangle. You will always going to get a triangle. So if you have say two negative edges like this, so these two vertices are going to be adjacent, and one more negative edge means these two vertices are going to be adjacent, these two vertices are going to be adjacent, and you see all of them are going to have negative edges in the two-path sign graph. So the product going to be negative. So it is not going to be balanced. Okay. So that's why the second result comes. Balancedness is will go, but consistency will remain if T is equal to 2k plus 1 or T is 2 or n is equal to 3. And in all other cases, it is neither balanced nor canonically consistent. How much time I have?
It's over.
Sorry. Okay, I will finish with two-path sine graph only because so many things are there to explore. I'll just finish with this. Two-path sine graph, let tree be a tree, then this two-path sine graph is balanced if and only if sigma does not have a subgraph isomorphic to K13 with 2 or more negative edges. So if you have a subgraph which is K13, again you will face this type of situation. Okay, if you have 3 negative edges, so you will get a triangle and it won't be balanced in that case. So if it is free from K13 with 2 or more negative edges, it will be balanced. These are some notations for stating the statement for the class of trees. So where n minus v is the set of vertices which are adjacent to v and having the edge negative sign. Similarly, n2 minus v is second adjacent vertices which has sign -1. And this small n minus v and represents the cardinality of n minus v, and n2 minus v represents the cardinality of n2 minus v. Forward. Okay. Now, this gives you the characterization of all trees. Let T be a tree and sigma be a sine graph over this with T as the underlying graph, and let W be the vertices which are inside the vertex of the tree which has degree 3 or more. Then this set, this graph, two-path sine graph is canonically consistent if and only if each vertex V in W satisfies the following two conditions. Okay. This gives you the characterization of trees. So characterization of trees only for canonical consistency. So if we combine the previous theorem as well as this theorem, so we can actually give you the whole picture about trees. So when this tree will be inside each of these sets, depending upon this 3 properties, so which are actually inspired from the those theorem only. So we have just defined these 3 properties P1, P2, P3. So if first case, if sigma belongs to SBC has, if P1 is true and either P2 or P3 is true, it is in SB has if P1 is true and neither P2 or nor P3 is true, and it is in SC has if P1 is true and either P2 or P3 is true. Otherwise, basically, if you look into this theorem, previous results are actually step by step. So we have just combined it and then got the final result. So we have solved the problem for two-page sine graph only for trees. So the problem is open to take. So next is, if you are interested, you can try it for other graphs. Say next definitely is unicyclic graphs. Next target. So we are working on it. So I wanted to discuss one more product. I think it's going to be so. Thank you.
The questions we can spend 2 minutes. Switching equivalence plays any role here, like any class of any proof or anything?
Yeah, we have used that switching equivalent for observing some of the properties, but yeah, because when you take switching equivalent, the graphs, matrices, actually you get similar matrices, the preserved determinant, eigenvalues and all these things.
And so
Balance sign graphs means any two balance sign graph over a graph, they are going to be switching equivalent.
And all the trees are balanced graph, I guess.
Because no cycle.
Yes, so it's have no cycle. So you told that this is still open for the other classes. So even for the unicyclic case, are you like also consider that balance or unbalanced things also you will be considered or not like?
Our objective, you can think of many problems here. So our objective was to take balance and canonically consistent graph, and then to see whether it preserves the same thing or not. Somebody can think of only say balance is there, but canonical consistency is not there. Whether the product graph has both the properties or not. So many combination you can think of. So that's why I said there are plenty of scope. And even this product, we have taken two-path sign graph, but you can take any product sign graph and work on it.
I have last question, like all the graphs which are balanced, is that any type of theorems or any like characterizations?
As you told me that it's switching equivalent. Any two balance sign graph whose underlying graph is G are going to be switching equivalent. You can get one from the other. And it is very easy to see. They will have many spectral properties, also similar spectral properties.
Okay, thank you.
Any question?
Thank you to the speaker for his nice presentation on time the last. Congratulations.
Thank you.
I request
Start,
Professor, please.
I just wanted to tell something about this khada. Actually, we call it khada. It's a Buddhist way to welcome and as well as when you are living, they give you this. And if you see, there are 8 symbols scripted over here. So these are 8 symbols of different for different regions in Buddhism. So it has actually very high value among in Buddhist culture. So they keep it as a secret. Thank you for.
Speaker is David Ross Michael, who is almost a part of this conference. So he'll be talking on computational aspects of core EP inverse. So his area of specialization is mostly generalized inverses, data science, and image processing. Here is PhD with Professor Manjunath Prasad, and he has already started gaining 4 research scholars.
No, it's making
Has good
noise.
number of publications and book chapters. So I invite you to deliver his talk now.
Okay.
It's fine, right?
Yes.
Good evening, everybody. Myself, Dr. David. I am actually, I did my PhD under the guidance of Dr. Prasad. So I started my research career with generalized inverses. So I'm going to actually pursue some of the talks on the generalized inverse. Okay, fine. So at the outset, I would like to first of all thank the organizers who have given me an opportunity to actually present my. So I'm going to talk on computational aspects of core EP inverse. And so for most of them actually who doesn't know what is the generalized inverse, it's a kind of counterpart of inverse. Right? So you can ask this question. Suppose if you have a system of equations Ax equal to B, then what would be the solution of this equation? Or in other words, in general, when will this solution exist for that system? And the answer for that is, if suppose you have the B, which is actually lying in the column space of A, then the solution will exist in general. But the question which actually originally answered was, if the matrix A is non-singular, then the solution exists. That's how the theory has started. Then the people have started working on saying that it's not just like the matrix A has to be singular, it just have to have the B has to have it in the column space of A. That's how the theory evolved, and then they found different inverses for the same purposes, and therefore they said there are many solutions are also possible in that regard. Okay, fine. So here we just concentrate on this particular aspect, that if the matrix A is non-singular, then the solution exists. So what is that actually contains? That if the non-singular matrix exists, then X will be A inverse B itself, and that itself will become the solution. So the question was posted in this manner, that instead of, let's say, suppose A inverse, as I told, any matrix G, which actually can be acted as a solution, then what can you say about that matrix? Right? That was the question. So the question was asked in that manner, and we define in this fashion. So we expect a matrix G such that G times some Y will be the solution for the matrix equation Ax equal to B. So in this case, we call that as a generalized inverse of A, just because it is generalizing the inverse of A itself in general, that if you replace your G by A inverse, it does the equation satisfies by the X itself. Y can be actually just, I'm sorry, Y can be just B, and A inverse is just the G. Yeah, that can be done. So we define the generalized inverse as this person. Any matrix A, which is any matrix G, which satisfies this equation, AGA equal to A, will be the generalized inverse of a matrix A. Okay, fine. Of course, it's not really extending the inverse itself. It is just actually just giving me a bunch of people actually who can be generalized inverse. That's how it works. So the question was, what if you have another aspect of generalized inverse itself? You see that A inverse A was actually A. That's how this definition evolved. Now, what if you look at A inverse A inverse? What will that be? That will be A inverse. So we expected that property, and any matrix which satisfies that property instead of A inverse was also called as an inverse. So we would like to call that as an outer inverse. So people started calling this as inner inverse because it is inside. That's how it works, and that is an outer inverse. Okay, fine. So our work is actually sitting on this outer inverse. Now, it is not just only the outer inverse was expected in the literature. It was expecting that the outer inverse, which was having a specific column space and specific row space. There are inverses like Moore-Penrose inverse that can be actually dealt with a generalized TS inverse. They call it as like that. That will have a special column space, meaning that Moore-Penrose inverse will have a special column space and special row space. That's how it works. So in general, we want to look at what is the outer inverse, which will have a particular column space and which will have a particular row space. This is very important for an application because the people will be searching for a solution which will actually sit on a particular space. That's what we want. Okay, fine. So in that line, they have defined so many outer inverses. One of the very famous is actually Drasin index. Drasin inverse. And after Drasin inverse, Professor Prasad has actually defined something called a core EP. Actually, these are some notation that I'll be using it. But before that, Professor Prasad actually defined something called core EP inverse, where the column space of the outer inverse, which I look at, and the row space of the outer inverse, all should be same, first of all. And then it also should be same as that of the column space of the A to the power D, where D is the index of the matrix A, right? Well, what is the index of the matrix A? if the rank of A to the power D is equal to rank of A to the power D plus 1, we call that D as a index of the matrix A, right? Okay. The D should be the smallest possible such index. Okay, fine. Hopefully that linear algebra is known. So we look at this matrix, meaning we look at this co-repeat inverse, and we would like to find out whether this exists or not, all of them, right? So in 2014, I remember Professor Prasad and Mogana, one of my senior, they have actually sat together and then found that this co-repeat inverse exists for all the matrix. I'm sorry, for all the matrix whose actually index can be found. Okay, fine. So if the index of the matrix A is 1, then the same co-repeat inverse is called as co-repeat generalized inverse of A. In fact, there is also a new notion which is actually there, kind of generalized co-repeat inverse of A. It's not to get confused with that notion. That's slightly different. In fact, I think yesterday I was discussing with one more scholar who was working with generalized co-repeat inverse of A. They discussed for a rectangular matrix as well. Here we actually look at square matrix itself, because we expect that A to the power D should be valid, and also we wanted the spaces should be same, so it's only valid for the square matrices. Yeah, fine. So here co-repeat generalized inverse is just simply co-repeat inverse for a matrix whose index is 1. Okay, fine. So how to find generalized inverse? There are numerous methods. In fact, a couple of them we have already discussed in the workshops as well. One is rank canonical form way. Just you take rank canonical form of it and then find the corresponding blocks and then replace the random arbitrary matrices, you will get the generalized inverses. And similarly, you can also find the outer inverses as well using the same technique. Okay, fine. And SVD and all the stuff and all, everything is there. We have already discussed in the workshop, so I'm not going to discuss any of that. So I'm going to specifically discuss an outer inverse. In fact, more specifically, I'm going to discuss co-repeat inverse. Okay, fine. In fact, I was looking at the analogous formula for the co-repeat inverse in this fashion, but somehow actually I settled up with some other formula. Yeah. So I settled down with this question for this talk: how to find the co-repeat inverse computationally. Okay, so I'm going to actually discuss two different methods if time permits. One is a bordering method, the other one is iterative method. So I'm just not going to discuss any other methods which are already available in the literature. So first of all, if the co-repeat inverse exists, then the co-repeat inverse will look like this. This is very key point. Like the Moore-Penrose inverse general case, you see that the Moore-Penrose inverse can be expressed using the generalized inverse case, right? The same thing over here, but here the index plays a crucial role. That whenever the co-repeat inverse exists, then it will be first of all unique, and that's what makes this study is very important. And it is also given by A to the power D into the generalized inverse of A to the power D transpose. I just use star over here, you can assume it's transpose. So A to the power T transpose into A to the power D plus 1 and its generalized inverse into A power D transpose. Yeah, this is the expression for it. Okay. Obviously, this is very, very difficult to compute in the computers. If you ask for any computer science people, they will say that what nonsense formula you have given, man. Actually, it is taking too long time to compute in the computer. So we want to look at some of the methods for which was actually easier for computers to do it. Yeah, one of such things is called as iterative method that I will discuss later. But before that, theoretically, we actually also have developed some of the methods for computation, which actually gave an idea for us to compute this co-repeat inverse using neural network as well. Yeah, that was our current work that we were actually right now doing it. So here you see, we look at a new technique called a bordering matrix, a bordering technique for finding an inverse of a matrix. Then later we'll develop the methods from there. That's how we do. So here you call a matrix T, which is written in terms of blocks as a bordered matrix. Whenever this particular matrix T is invertible, given that the A may not be invertible. Okay, any matrix is actually called as a bordered matrix. Here we want to look at specific border. I'll tell you what is the order actually it comes over here. You see that the P I was looking at that it should be of order M by M minus R, and Q should be of order N minus R by N. That's a specific order I look at, and that was actually giving us the index as well at the end. That was the idea. Otherwise, this construction was not really important, but this was actually trying to characterize the Dawson index in another way. That's why we need it. Okay, right. So can you put it off? Thanks. So, for example, you take a matrix like this. It's a rectangular matrix. There's no way that you can invert it, but you add on row like this, then that matrix actually becomes a invertible matrix. Okay, without knowing anything, it just actually is matrix is bordered. That's all, and so the matrix actually is getting invertible. Yeah, fine. For example, the other example is just you add a column instead of row this time. Now, if you have even a square matrix like this, then you know that the second column and the third columns are same. That means that the matrix is not singular at all. But still, actually, you can add one row and one column, and then you make the matrices actually non-singular in this fashion. Yeah, fine. Yeah, this technique is not new. It's actually quite old. I remember it was. Even actually before Iwsmga sir was working, even actually when Prasad sir was doing his research itself, he has actually touched upon this kind of bordering technique. Now, specifically, if you look at the bordering that I have chosen right now here, the T, which was inverted later, was giving me a block over here, right? So this is the matrix over here, and I took the counterpart of the counter block for that. So this was kind of a block which I had in my A. But now I look at the counterpart of this A, and this matrix surprisingly actually was giving me the generalized inverse of A. That was the breakthrough. The breakthrough was just simply you try to find the bordering suitably in a way that while inverting the T, you get a generalized inverse of A. Yeah, fine. So what KMP sir has done before even I born was that he has proved that, along with Namaguchi sir, any generalized inverse of A of a rank R over a complex field can be obtained by looking at the inverse of a suitable bordered matrix. That's what he proved. Yeah, the proof is very difficult right now to look at it, but it is settled now. Yeah, and the size of those bordered matrix, I call it as bordered matrix, PQ or all, should be of this R. Yeah, because the R actually plays again a crucial role, which is in the proof, rank R. Now, followed by again, Professor Sir has actually proved some more results. He said that the existence of such bordering has been actually already related with the rank factorization of I minus GA and I minus AG, where G is a generalized inverse. Yeah, because AG and GA are idempotents, and I minus AG and I minus GA are also idempotent, and then they give us projections, all of them, you know, right? We have discussed in the workshop, so I'm not going in much into it. So in 1991, Iwsmga sir has actually shown that any outer inverse of A also can be obtained by such a bordering. That's what sir has proved. Yeah, fine. So we use that technique to get an outer inverse specifically for us what we wanted, right? So what's the outer inverse that we wanted? We wanted an outer inverse whose column space and row space are equal to the column space of the A power D, where D is the index of A, right? I'll actually illustrate the method by an example. I'll leave the proof as an exercise to you. You can look at my paper. It's there. It's available in the online. If you are not able to getting it, then mail me. I will give you the paper. Yeah. So here is the matrix A. I've just taken a 5 by 5 matrix, and A square and A cube was actually settling with the rank of A square equal to rank of A cube. That means that the index of the matrix A is actually 2. Okay, fine. Therefore, what I look at here is, now I have to actually, now I'm actually trying to find out what is the P. So you choose P, I told you, you have to find a suitable border P. That's all. So the suitable P is this. You choose P such that the column space of P is actually orthogonal to the column space of A to the power P. That's all. Yeah. Look at that. And of course, you take any basis. Just take any basis for that and append that with the T over there. And you also take that the P transpose, the same thing, P transpose, you put it over here. and you just fill up the rest of them with 0, 0, 0. That's all. So all that we wanted was just construction of 1P. And what is that giving us is the T inverse. And surprisingly, what happens here is that block which is corresponding to the A over there has become a co-repeat inverse of A. That was the novelty in that work. We identified which P has to be chosen and which Q has to be chosen, which R has to be chosen. Yeah. Okay. Yeah. I'm sure actually this doesn't really play any role on this. You can actually change it to, you can play with that matrix as well. Yeah. So this is the generalized inverse of A. I'm sorry, this is the co-repeat inverse of A. You can verify it. I just put up that verifications. You can also verify that what happens here is the low reduced echelon form of G is this. That means actually the rank of this matrix is 2, and therefore it will be actually equal to the column space of A square, etc. So it verifies that this is a co-repeat inverse of A. Okay, fine. So what we did is we have actually come up with the theorems, couple of theorems, just to settle down with the result. The first one that we did is for any matrix, for any square matrix A, there exists a positive integer D and a matrix P such that the column space of P can be chosen as an orthogonal complement of corollarism A to the power D, and the matrix that you do construct using this A, P, and I have written P star here, you can assume P transpose here, 0 is always invertible. You can always actually keep finding T, D such that actually the process ends at some point of time. That's what I'm trying to say. Yeah. Okay. Initially I would have defined it. I actually skipped the slide. I defined such a collection as actually as a BK of A. Yeah, I have 5 minutes, probably 2 minutes, maybe he's saying. So the proof I'm skipping it. Just such a bordering is always exist. Yeah. Now all that left to prove is that bordering will actually give you the co-repeat inverse, and that's what actually I have done it here. Yeah, yeah. In fact, actually we have actually in between. Actually, we have given. I think this one we have given as a lemma, then the theorem. Here I am put as a theorem, but you can actually check that this one actually will finally actually give you some K of I, and that K of I will become the index. I'll skip the proof. So what actually is also giving you is an alternative characterization for the Drasin index of Drasin index of a matrix A. So actually I was not finding the matrix index. If you notice very carefully that while I'm trying to find out the construct a matrix T, I keep actually raising the powers of A and then try to find out the column space of A to the power D's complement, and then I append it and find out that when this matrix becomes invertible, and that point of time I stop there. And the D that I have used to actually make this T is invertible, I'm claiming that is what will be the Drasin index of A. Yeah, okay, that's what is the work. Then the iterative method, probably I may not have much time. Yes, sir? I have 5 minutes. Yes, great. So if you take any, actually I'll skip this preliminary portions, the initial portions. This was one of the core thing that we have used it, is that you take any block matrix, meaning partitioned matrix, then the generalized inverse of A actually can be as listed as when it can be given as a partition matrix like this, but I can also tell you what is this each block can be. So that first block can be, the first block will be this, yeah, this B minus A inverse, meaning A minus B whole minus, and the X will be this, yeah, okay. So I actually just did the extension of that with removing K columns and adding K columns. That's all. It's just fancy stuff. Very sorry. So, so what we wanted to do here is, this is the idea. You take any xk, you start with any xk, and then keep proceeding forward, and then you finally end up with co-repeat inverse. That's the idea. So for which what we have to do is, we have to find a suitable sequence of numbers, Ck, such that this process is happening. This was the case when you have a non-singular case. Like you try to actually find an inverse in the non-singular case, this is what. So we try to actually use we try to actually imitate the same process and try to find out what will happen for the core-EP inverse here. Okay, fine. Remember, actually, in the inverse case, actually, I already know that where to find the projection and what to find the projection. So everything I know. So it was probably easier to find out the iterative method without actually you start with anywhere. Actually, it will be there. It's very simple to find out the sequence. But here the difficulty is how to find the projection of the column space of A, and also actually it has to be in the column space of A to the power D. How do we have to find out? That was the question, and that question actually is answered by giving a suitable projection matrix like this. You simply find a P, which is actually on the column space of A, and we have like actually this is what we wanted, and for which actually what we chose here is that CK that you take the projection in the case of in our case, so what we can do is actually we can just take simply the identity itself, and then you take the AX. Yeah, so X is happen to be the previous iterated matrix. I mean XK happened to be the previous iterated matrix. What we wanted was essentially we wanted this XK to be the core EP inverse. That's all. Okay. Yeah. So this is the theorem that we proved. What we did is you take any X naught. You start with the initial matrix. That X naught should be in the R of A comma A star. I define R of A star. Actually, it should be something like this. I hopefully I think I did not define what is this R of A comma A star. Actually, I have written here. So R of A comma A star means that the X naught matrix should be actually written as A B A star for some B in for some B. That's all. And what I expect also, I actually expect this rank of this R naught to be less than 1 for my convergence to be working well, because I will use the convergence. Like what is that? The norm of A. A inverse exists only when rank of 1 minus A is actually less than 1. I wanted that. Sorry, norm of them is actually less than 1. That's what I wanted. And spectral radius to be less than 1. That's what I wanted. So here I have actually used the spectral radius. Sorry, my mistake. It's not rank. So spectral radius R naught should be actually less than 1. So the sequence, whichever I have written over here, which I have constructed in the previous slide, will actually give you the core EP inverse as we actually proceed forward. Okay, that's the work.
Sustainability, maybe just to take one classic example. So in sustainability, what we had is we had almost 3 solution tablets by developed by guided development ones as well. So 3 guided development.
That's not mine. Okay. Profile escape. So currently what we are trying is using the bordering technique. I don't think so it works.
Oh, yes, right.
So currently what we are trying is, I haven't actually put it in the slide right now. Using the bordering technique, which was giving us an idea to actually find the invertible matrix, we are trying it to look at a neural network technique to find the inverse of that matrix. And along with that, we also would like to find out that how is that P matrix can be easily adapted, meaning easily made it adaptive to the neural network itself. That's what the work that we are right now doing it. I didn't actually add it in the slide right now. Currently it's working. Yeah, that's all. Any questions if you have? Yeah, please. These are my references. Thank you.
That presentation is very nice and interesting. Actually, I want to know some basic question about this.
Yeah.
Actually, for any rectangular and square matrix, then we can find its more Penrose inverse, right?
Yes.
What is the motivation to study Drazen, Poripi, generalized Drazen, and other generalized inverse?
Yeah, I think in the middle itself I mentioned something. Like finding a more Penrose inverse is actually equally finding the inverse itself. The question started with, do you really need a matrix which has a least square property, which has a minimum norm generalized inverse property, which has a outer inverse, which has a which happen to be inner inverse, all of them, right? So it's too much. If as a mathematician, if you look at it in this perspective, you need that 4 equations has to be satisfied for a Moore-Penrose inverse. Yeah, and that's too much for it. So now what I'm trying to say is, for some systems, for example, you just want one solution for an AX equal to B. Just want one solution for an AX equal to B. So what will, I just actually shown in the first slide itself, any generalized inverse will do the job. Just AGB will be equal to B. That's all will do the job. So computationally, what it becomes is, it is easier for us to find the solution, first of all, and then actually you can ask more questions. Maybe you don't want just a solution. Probably I wanted a least square solution. Then you go for just 1-3 inverse. That's all. I don't need to be outer inverse. I don't need that to be an outer inverse. I don't need that to be a 2-4 inverse. I just wanted that to be in 1-3 inverse. That's it. So it really depending on your application. When you wanted to solve a system, or when you wanted to actually find really an invertible, when you wanted like linear model and other stuff and all, what do you need? That's all. You may not need the complete matrix, meaning as an inverse, but you will just need small properties. So here what we are doing is, theoretically we are developing center. Okay, these are all some opportunities that logically you can develop, so that in the applications, whenever you need matrix which has this property and also its column space lies in this particular space, then you can use it. That's it.
Also, is there any map to define which is the relation of all the generalized inverse, which is subclass of other which is big? That means if given the system of matrix equation, then how to know which inverse give the better solution? That means is there any comparison study of all the generalized inverse?
Actually, that's what I'm trying to say. That the better solution is actually in your hand. Do you really need a least square minimum norm generalized inverse? Then Moore-Penrose inverse is the only option. Otherwise, let's say you need, I wanted a Moore-Penrose generalized inverse kind of one, but I wanted that column space to be this T and the row space to be this S. Then A2 TS is the best generalized inverse. Hopefully, I convinced you.
And also, I've seen literature vector Moore-Penrose inverse. You are find any rectangular square matrix, you can find its Moore-Penrose inverse. I've seen in literature they are studying weighted Moore-Penrose inverse.
Weighted Moore.
What is the motivation?
Actually, I haven't studied weighted Moore-Penrose inverse, but I know that it's just actually adding two weights in that M and N along with the inverse and finding it. I think I may not be able to
Find
answer
any
it.
rectangular matrix, it's Moore-Penrose inverse. What is the motivation? Weighted, you just multiply and.
I think it's a kind of actually it's logical, no? Like when there is when inverse is actually we can find out. Then the another question, like you have a graph, then adjacency matrix I can find out. Then what if there is a weight on the edges? So weighted adjacency matrix find out. So similarly, the analogous has come. So you have a matrix. Then what if actually I have another matrix? So I may not be the right person to answer that question because I haven't studied weighted Moore-Penrose inverse at all in my research career itself. Because I worked on outer inverse on a semi-group. Given two elements in the semi-group, given an element in the semi-group, how does that outer inverse will look like? That's what my whole area was there. Then as a special part of the my work only, this co-reef inverse. So I didn't really actually study generalized inverses in terms of matrices in general, just mostly analysis.
Okay, thank you.
So I may not be knowing different kind of generalized inverses.
I put some things in the chat. You see, Saroj Malik and her Spanish co-authors, David and other person, they have papers on co-reef inverses.
Yes, ma'am. Yes, ma'am.
Okay, and I hope you know them and you have seen the work.
I think I haven't.
Okay, you can get in touch with her. I can send you her email. And then another thing is she has a book with S.K. Mitra and P. Bhima Shankaran on partial orders induced by generalized inverses and applications to linear models, etc. That was published in 2010. I guess you know that.
Even if you go or maybe share, I will have to go and find it. It's sustainable.
Yeah.
Okay, and plus I will send you my talk on injectivity versus subjectivity given at Windsor University several years ago, if you give me your email address.
Please, I think maybe.
Okay, very good talk. All the best.
Thank you, ma'am. Thank you.
Okay, I had a question very similar to yours. What is the purpose with this, really? Because in some way, I would just think about if an interesting solution, I look at the null space and want to find a basis in the null space.
Yeah.
And we know, I think you said also that all kinds of generalized inverses will give you the general solution to a problem. So then the question, why on earth one should choose something pretty complicated? And there must, from my point of view, I would like really to understand the property, what is positive, because usually a problem where you don't, if one not is able to generate all solutions, that is in some way, we have to understand why we cannot generate all solutions. And why is one solution better to another solution? I think, and this must be a problem, I guess. Or...
Yeah. It's usually a problem. Actually, and I happen to work with computer science professors for past 2-3 years. Now, what I understood actually from their perspective is theory has answers for almost all the problems that we have right now. But when you wanted to implement it in the computer, then that becomes a problem for us. So your numerical errors will accumulate it. Then if you want to actually solve 2 equations, the question is, can I not be able to solve it in 1 equation only, so that it is easy for us to give the answer immediately. So the world is actually expecting the answer immediately. So the time complexity comes into the place. All this actually is giving you an idea, giving you actually posting you a logical question. How can you solve the same 4 equation into single equation, which is definitely not possible in mathematics. So the another in-depth question was, what is the thing that you needed at the end? Then from there actually you started, and then from there actually you generate some generalized inverses. That's how it works. Actually here, the work whatever we have done here is actually started with something called EP matrix, which has the column space and row spaces are same. So what we had done here is we also wanted to look at the index of the matrix C and column space of index. Column space of A to the power D also should be same. So it was kind of actually one more conditions on top of it, and still it becomes an outer inverse, and therefore we can use bordering technique to actually sketch this outer inverse, and hence it becomes easier for us. So our current work right now, what's going on here is how do we actually find this inverse using a neural network. Once I accomplish that, then it will become so easy for the people to actually use the core EP inverse itself in their applications itself. Yeah, that's
But I was thinking, if you think about the null space, you just generate the basis in the null space, and then you have at least all solutions or some of the solutions.
Yeah.
Is that complicated? I don't do computation. Is it complicated to generate the whole null space?
Like again,
basis there.
Yeah, it is, I'm saying. In general, when you wanted to compute a null space, you have to solve a system of linear equations. That's the first question that we post and then solve it, right? So it again boils down to how do you solve a system of equation. So it is computationally very costly. So we don't really wanted to compute the null space. Still, we wanted to have some idea about the solution space. I think I convinced you. I know. The idea is very simple. Actually, I know that any solution can be written as a particular solution from a solution from the null space. However, what if I do not want to compute the null space? That's the answer. That's what is giving.
Thank you. Thank you, Dr. David, for a nice talk. Okay, I request Professor Vinay Madhusudanan to honor Dr. David. Thank you, David, for your continued support for Carums.
He's my good friend. I'm honored. Thank you.
So we will conclude the invited talks of day 3 of ICLA 2023. We shall now have contributory sessions. So I request all the participants who are participating in Best Paper Award for Young Scientist Junior to go to NLH 303, Young Scientist Senior category NLH 305. And the contributory talks A will be held at NLH 403, contributory talk B will be held at 404, and C will be held at 405. Thank you for your continued support.
Maybe for the pouring it.
Yeah, actually, that's you can actually do meaning actually the proper EP is literature column space and
Then they are
so and the core is you're going to contribute. You have you take any maths, please take it. Then you can actually decompose those mathematics core and nilpotent. So we call it as core nilpotent decomposition. So for such a kind of mathematics, the nilpotent formula has so it is a core equation. You have matrix A. So to make it invertible, you are appending it to constant rows. And if you are choosing a particular column matrix, so that you are going to get P numbers in such a way that you are going to get EP that EP. Yes. So now I can invert the matrix by adding some other positions and you are going to get some column or row. Now is there any relationship between EP for yours and me? I quickly change that slide. You take any such a logic technique, no? Then the outline that you get is actually very with respect to that. So you will not get it. Whatever the